I think we should move on. Yes, not make her to wait. So, good morning. Good morning, everybody. Let's please take a seat so we can start today. So we're going to start with our guest. Was supposed to join us on Tuesday, but due to some timing issues and synchronization, we didn't manage. So we are very happy to have her with us this morning. So before that, as you may know, so the CNRS, so the Scientific National Research Center in France, is composed by different institutes, right, at different topics. So the Computer Science Institute is one of the largest one. We're talking about thousands of researchers. And so it's our pleasure today to have with us Adeline Nazarenko. She's the director of the Institute of Computer Science, CNRS. Adeline was, before taking this responsibility, she was a researcher and a professor in NLP, where she was working on analysis of semantic information in text, also information retrieval. It's a very important topic in these days. So it's a great pleasure to have her participation in this workshop. Adeline, merci beaucoup d'être avec nous aujourd'hui. Donc c'est un plaisir de t'avoir là. Donc la parole est à toi.
Merci beaucoup. Hello to everyone, and thank you for the invitation. At a time when we are celebrating the French-speaking world, I will speak in French, okay? And of course, I apologize for those who do not understand me, but I'm sure that you have developed all the tools you need to translate my words. And I'm sorry, of course, also that we missed our appointment on Tuesday, but thank you for giving me back the chance to express myself and to express the support of CNRS. Le traitement automatique des langues à l'ère de l'IA générative, des sciences cognitives et des transformations sociétales, c'est un sujet important, non seulement pour la communauté scientifique, mais aussi pour la société dans son ensemble. C'est pour ça que je suis contente de m'exprimer aujourd'hui, et je ne m'exprime pas en tant que chercheuse, mais justement en tant que directrice de cet Institut des sciences informatiques au CNRS. Alors, vous le savez mieux que d'autres, tout le monde le sait, mais vous mieux que d'autres, le TAL et l'IA sont des domaines en pleine expansion, portés par des avancées technologiques qui sont continues, mais qui sont sans précédent sur la période récente. L'IA générative en particulier ouvre des perspectives en matière de création de contenu, de traduction automatique et de compréhension du langage humain. Ces technologies, ce sont plus seulement des outils et des objets de recherche. Elles sont de plus en plus intégrées dans notre quotidien. Elles transforment la manière dont nous communiquons, dont nous travaillons, dont nous interagissons avec le monde. Donc, anticiper et mesurer l'impact, en particulier l'impact cognitif de ces transformations, est un défi majeur qui, à mon sens, relève aussi de la responsabilité collective de notre communauté scientifique. En plus, les sciences cognitives nous offrent des insights précieux sur le fonctionnement du cerveau humain, permettant de développer des modèles d'IA plus performants et plus proches de l'intelligence humaine, et aussi permettant toujours, par un phénomène de boucle, de mieux comprendre la manière dont le cerveau, la compétence, le langage humain fonctionne, et comment nous apprenons et comment nous utilisons cette capacité. Cette convergence entre le TAL, l'IA et les sciences cognitives est essentielle pour relever les défis actuels et futurs de notre société. Alors, vous savez, peut-être le CNRS, en tant que navire amiral de la recherche scientifique en France, joue un rôle crucial dans ces domaines. Notre engagement se manifeste à travers plusieurs initiatives et actions qui illustrent aussi notre détermination à être à la pointe de la recherche et de la collaboration internationale. Alors, quelques mots, mais je ne vais pas développer. Le CNRS participe très activement à la stratégie nationale en intelligence artificielle en France. Vous savez qu'il est partenaire de tous les centres IA et maintenant de tous les clusters IA. On copilote un programme structurant à l'échelle nationale avec le CEA et INRIA, etc. Nous opérons aussi, ça c'est quelque chose que nous faisons en propre, mais nous opérons le supercalculateur Jonzet, Et nous organisons aussi tout le réseau des ingénieurs support qui aident les équipes de recherche à porter leurs calculs et leur développement sur ce supercalculateur. Alors peut-être un mot plus spécifiquement sur ce qu'on appelle l'IA pour les sciences. Vous savez que ce sujet est un sujet qui est reconnu comme phare aujourd'hui à l'échelle internationale. Et c'est une priorité depuis plusieurs années déjà pour le CNRS. Depuis, en fait, on l'a affiché depuis 2019 comme vraiment une des grandes priorités pour le CNRS. L'idée, c'est de s'intéresser à l'IA comme paradigme de la découverte scientifique. On voit émerger des nouvelles pratiques de recherche dans beaucoup de domaines, les sciences des matériaux, la biologie, les mathématiques, les sciences humaines et sociales, et j'en passe. Et ces autres sciences, en retour, questionnent les algorithmes d'IA, leur performance, leur garantie, leur transparence, etc. Voilà, donc toutes ces recherches interdisciplinaires sont portées au CNRS par le centre Essai, AI de SAI, AI for Science, Science for AI, qui est un centre qui a été créé et qui s'occupe d'animation sur ces sujets-là et qui développe des liens très particuliers avec Ivado au Québec. Alors, voilà, de manière plus spécifique, le CNRS soutient activement aussi les projets en traitement automatique des langues et à la frontière avec l'IA, avec le développement de modèles de langage avancés, capables de comprendre et de générer du texte de manière plus naturelle. Nous avons lancé il y a plusieurs années un groupement de recherche ou un réseau thématique autour du TAL, qui vise à fédérer les forces dans le domaine et à animer la communauté scientifique, mais aussi à faire un travail de prospective pour identifier les défis de demain et proposer une organisation, au moins à l'échelle nationale, qui permette de les relever collectivement. Et vous le savez, c'est un enjeu important étant donné la manière dont la recherche est organisée en France. Nous n'avons pas un grand centre pour le traitement automatique des langues, mais beaucoup d'équipes, souvent visibles, mais de taille cependant modeste et qui sont en difficulté pour porter des grands programmes structurants de manière isolée. En traitement automatique des langues, aujourd'hui, il est évident qu'il faut jouer en équipe à l'échelle nationale et je pense aussi à l'échelle internationale. Voilà, aujourd'hui, le CNRS veut aller plus loin. Depuis plusieurs mois, on recommande de lancer un grand programme autour du français, des langues de France et des langues au contact du français. Alors, vous voyez, je m'exprime en français aujourd'hui. Ça résonne avec cette idée qu'on inaugure là ces journées de la francophonie. Et je n'ai pas besoin de vous l'expliquer en détail, mais c'est un enjeu majeur pour notre société que de permettre à chacun et chacune de continuer à s'exprimer, à réfléchir, à travailler dans sa langue, tout en prenant part, évidemment, au dialogue interlinguistique et interculturel. Donc, il ne s'agit pas simplement d'IA générative, de modèles de langue ou même de données et de corpus utilisés pour leur entraînement. Le programme que nous voulons lancer comporte aussi un volet important sur les enjeux épistémologiques, cognitifs, sociopolitiques, économiques associés au déploiement des technologies de la langue sur le moyen et le long terme. Voilà, donc c'est un grand programme que le PDG du CNRS, Antoine Petit, porte. Et vous le savez, ces technologies de la langue diffusent depuis longtemps dans l'ensemble de la société. L'IA génératif donne un formidable coup d'accélérateur à ces transformations, mais il est essentiel de garder la maîtrise de ces outils, de continuer à les perfectionner, parce qu'ils sont loin d'être parfaits encore. Il faut aussi en analyser les impacts cognitifs, sociaux, culturels, éthiques, pour pouvoir penser, anticiper et accompagner les transformations qui sont en cours et qui vont continuer à s'accélérer. Alors, si je pense aussi maintenant au volet plus international, vous savez que la collaboration internationale est au cœur de la stratégie du CNRS parce que c'est le carburant de la recherche fondamentale, donc c'est normal, ça fait partie de la raison d'être du CNRS. Le CNRS participe à de nombreux projets de recherche internationaux, aussi bien en Europe qu'en Amérique et sur les autres continents, avec des institutions de recherche de renom, et pour promouvoir la recherche, pour développer la recherche à l'échelle internationale. Ces collaborations nous permettent de partager nos connaissances, d'apprendre des meilleures pratiques, de développer des solutions innovantes, de répondre aux défis mondiaux. Donc ça, c'est vrai dans le domaine du TAL et de l'IA tout particulièrement. Alors, Pablo dirige ce laboratoire international ILS qui associe l'université McGill, le CNRS ainsi que ses partenaires de l'université de Paris-Saclay. Et c'est une incarnation très concrète de ce que je veux dire sur ces collaborations internationales et je peux vous assurer que c'est une destination très prisée des scientifiques français. Voilà, le centre essai dont je parlais tout à l'heure développe des partenariats avec des institutions internationales renommées qui lancent des initiatives similaires. Et je vous l'ai dit, la première d'entre elles, ça a été et c'est Ivado. Et puis nous, voilà, si nous arrivons à avoir un appui politique autour de ce programme que nous voulons lancer autour de la souveraineté linguistique du français et autour du français, je pense que ça sera intéressant de le déployer aussi à l'échelle franco-canadienne parce que nos collègues canadiens connaissent bien ces questions de contact linguistique et culturel. Voilà, donc vous voyez, les défis scientifiques à relever sont grands, nombreux et complexes. La compréhension du langage naturel, l'éthique de l'IA, l'interdisciplinarité, l'impact sur les humains et les sociétés des transformations induites par l'IA et par le TAL. Pour relever tous ces défis, le CNRS s'engage fortement dans le soutien à la recherche fondamentale, dans la promotion des collaborations internationales, dans l'interdisciplinarité que nous encourageons au quotidien, et puis pour attirer les talents. Et du coup, j'en profite pour vous faire un tout petit coup de projecteur sur l'appel Choose France Rising Talents qui est ouvert et qui permet à des chercheurs talentueux qui souhaitent rejoindre la France pour monter et diriger un programme de recherche en IA, au sens assez large du terme, dans un laboratoire du CNRS et pour une durée de 4 ans. Voilà, sur tous ces sujets, sur tous ces défis, vous trouverez le CNRS à vos côtés et nous sommes prêts, avec toute l'équipe de l'Institut et au-delà, à réfléchir avec vous à ce dont la communauté scientifique a besoin pour avancer. Voilà, pour finir, je voudrais remercier Pablo Piantadina de son invitation, tous ceux qui ont œuvré à l'organisation de cet atelier qui vous rassemble, et aussi et surtout, merci à tous les chercheurs et les chercheuses qui se mobilisent au quotidien pour faire avancer la recherche dans le domaine de l'IA, du TAL et des sciences cognitives, des deux côtés de l'Atlantique. Merci à vous tous qui nous rappelez combien la recherche fondamentale est essentielle dans ces domaines et qui contribuez à la mettre au service de nos sociétés.
Un grand merci à Adeline pour ces mots, pour avoir si bien résumé toutes les actions que le CNRS fait à l'international et en particulier conjointement avec le Canada. L'importance d'intégrer nos cultures et notre langue aussi dans ces modèles d'IA génératifs qui sont en cours en train de se développer et aussi de contribuer à la sécurisation des outils-là qui sont loin d'être parfaits. Hein. Et on n'a pas prévu d'avoir des questions, mais en fait, je ne sais pas s'il y a des questions, two courtes questions, just one question, if somebody has a short question, that's possible. No? Okay, that's great. Merci beaucoup encore. Au revoir.
Merci à vous et travaillez bien, c'est important.
Merci.
Au revoir.
À bientôt. Au revoir. So I'm going to give the speech to Jackie, that is going to take care of the next two sections.
Yes, thank you very much, Pablo. So it's my pleasure to moderate this session. So the theme for today is broader impacts and societal impacts of AI. To start this off, we have a session with 3 distinguished speakers. So it's my pleasure to introduce our first speaker, Professor Dilek Haqqani-Tur. So feel free to come set up. So Professor Haqqani-Tur is a full professor at University of Illinois Urbana-Champaign. Actually, this marks a return for her to academia after a long time. She has been at all of the top AI companies. So previously, she's been at Amazon Alexa, and Google, and Microsoft, and AT&T Labs. She is highly distinguished and renowned for her work in conversational AI and dialogue systems. Her achievements are too numerous to list. I'll just say that anytime I read a good paper in that general area, the chances are very good that her name is on it. So I'll pass the floor to her, and we'll be very lucky to hear her talk today. So thank you very much.
Thank you very much for the kind introduction. Can you guys hear me? I guess we're better now. Okay. So I'll mostly be talking about aligning with the goals of this session. I'll mostly be talking about alleviating over-reliance to AI systems through accountability modeling. So with the recent advancements in AI, thank you, people started using large language models as tools for multiple purposes, and we are seeing more and more applications every day. And as Jackie has mentioned, I've worked in industry for a long time. Usually when you build an application, having a frictionless approach is usually the most preferred approach, and friction can be a good thing. Hopefully I'll be able to convince you throughout the talk. So the issue is large language models do make mistakes, they do have assumptions, and so on. And their outputs, though, usually sound very convincing, even when they make mistakes. So users are inclined to believe, trust what AI presents them, and then do things based on that. The issue is, depending on the situation, there can be catastrophic outcomes, or things could be just simply unpleasant. I'll show some unpleasant outputs, not catastrophic ones. But imagine interacting with an embodied agent that uses large language models. The user may just simply say, make me a salad, and it can go and then do something, comes back with some salad. So no assumption is revealed in this case, so it isn't told, I think these are the ingredients. It hasn't asked any questions, it hasn't shared any reasoning or anything like that. It took a short time, maybe frictionless on the user's part throughout the interaction, but at the end, user may get something that they didn't ask for, they didn't care for. Similar interactions for information requests. These are some of the things I was actually trying last night. I'm asking about things I can grow in my backyard, or the timing, and then it's all, and then in one case, I don't want to just bash on OpenAI models, so I tried with Llama 3.2 as well. Making assumptions, not asking me, where are you really located? There's a lot of dependence on where you're located on the advice that I'm going to give you. Doesn't makes an assumption, again. Or task completion. This is, again, something I was trying. I'm just looking for restaurants in Champaign area, and it suggested me Zorbas. Sounded like Greek, not really Italian, not what I was asking for, but I said, okay, let's go with it. And I asked for the website, I asked for the address, it sounded all very convincing. I checked it on Google Maps, it's not there, the website doesn't exist, and so on. But luckily I checked, so what if I had been there without checking all this information? So currently we do have a project at UIUC funded by the DARPA Friction for Accountability in Conversational Transactions program. We are collaborating with the Northeastern University and University of Southern California, thanks to our collaborators. And we are trying to see whether friction can help in these conversational interactions. And when I say friction, mostly has some negative connotation, but actually friction can be a good thing. For example, imagine you're deleting a file, which is important, but you didn't notice it. The operating system comes back and then asks you, are you sure you want to delete this file? And you're like, oh, well, okay, no, I don't want to delete it. This is an example of a positive friction. It prevents you from doing a big mistake. So the idea is friction can reveal implicit assumptions between the parties of the conversation and then force the sides to think more critically about what is being proposed, whether they should take the suggestion, and so on. And our goal is mainly studying what kind of friction mechanisms can we use in conversations, and how do we trigger them, how do we introduce them for better experiences, for better task completion, for more truthful interactions. So the idea is not new. There has been a ton of work in the AI-supported decision making. For example, one team from actually UIUC has proposed slowing down technology can help prevent errors. They looked into what if we delay the decisions from AI so that the user has some time to think about it? Or what if we tell the user how confident the AI is on the decision that it is making? These are some mechanisms that can help. Others have looked into, can we put explanations? Would they help when AI makes a decision? One finding is explanations can actually do the reverse, because once the model starts explaining the wrong thing that it has proposed in a very convincing way, it can again have bad outcomes. But it can actually do more cognitively forcing interventions. So they have found things such as checklists or asking the user to explicitly rule out some alternatives could be useful. And then others have shown that explanations are not necessarily always bad. When the user has to rely on AI, doesn't have any other source, then actually explanations can help. But this is mostly on the decision-making literature. People have looked into introducing confirmations, implicit or explicit confirmations. Explicit would mean, did you say this? Or implicit would mean, I heard you said this, but like something else. And this is like something that has been studied a lot earlier in the dialogue systems. People have introduced these when the model is not confident on its outputs. Back then, speech recognition errors were an issue. So a lot of people looked into how do we better predict confidence scores, word or phrase confidence scores on ASR outputs, including some of our work. For example, we looked into word posterior probabilities or ways to generate multiple hypotheses from the ASR system and then marginalizing word posteriors to get better confidence scores. And in the case of embodied AI, we have done some work to add dialogue. For example, you may ask the agent to go reach the bed. This is in the framework of navigational instructional systems. And the agent comes to some point where it can see two beds. And it can make an assumption going in one direction, but it may be wrong. A better approach would be just going back and then asking the user, which bed did you mean, or which direction should I go? And so we tried to figure out when would be the best time to ask such a question for an agent. Looked into uncertainty estimations, mostly inspired from the earlier literature in dialogue systems, but we also looked into learning the conversational actions in addition to the navigation actions by assigning them some cost, and then we have seen that we could get pretty good results in terms of better task completion, although at the cost of maybe 1 or 2 turn interactions with the user. So now, going back to my earlier example with the embodied AI, here's an example on the right, which is actually collected from crowd workers who are playing the role of a user and a robot. And in their interaction about making a salad, you do see, like I highlighted with orange, you do see a lot of turns that are actually about the task. I don't like to call dialogue as friction, but in some contexts, it can be seen additional dialogue that you didn't need to necessarily do, can be seen as some form of a friction. So it's both very natural and expected for humans to actually ask questions in a situation that it doesn't know how to do the task. And it should be similar for an agent. So in this case, there are some questions that are exchanged about what the task is, revealing of assumptions that gives the user an opportunity to correct if the agent is doing something wrong, to think about it and then to correct it. And at the end, hopefully the user gets something that they actually wanted. So with this in mind, we have been looking with our colleagues at Northeastern, we have been looking into what could be ways to improve these systems' correctness and reduce people's over-reliance. So they have defined a set of types of utterances that they have observed in multiple dialogue corpora for embodied AI or for task completion. For example, the agent can reveal its assumptions, as we have seen in the previous dialogue. It can add some reflective pauses. This happens pretty frequently, actually, in the embodied AI case. And it was also what was shown to be useful in the AI for decision support work as well. It can reinforce, meaning it can, in 2-3 turns, after 2-3 turns, it can repeat what it is doing, remind the user what it thought it was doing. It can overspecify, although it could be boring. In certain cases, it can actually be useful. It can tell the user what it is doing, especially when it is not confident. Or it can just ask back to the user. So while they are analyzing how to introduce these, or which of these would be more useful or more common in human-human interactions, we are looking into how do we introduce them in task-oriented conversations and then embodied AI interactions. So our task-oriented dialogue system is basically built on large language models. This is, in a way, kind of similar to tool calling or function calling literature in the LLMs these days, but for dialogue people, for a long time, we have been actually calling some backend APIs to retrieve the accurate information to present to users. So the first task for dialogue systems, this type of dialogue systems, is dialogue state tracking, which is basically, given the conversation context, figuring out what should be in the API called for the backend, what attributes should be present, which API should be called, and so on. And once these are obtained, a dialogue system calls the API, gets the results. With those results, then generates a response to the user. So if there is nothing that is matching the user's request, it can say, sorry, I couldn't find anything. Do you want to change any attributes? Or if there are too many results, then maybe it can ask the user, do you want to reduce the space a little bit so that I can present you some options? And we do use LLMs, basically just ask each of these as questions to the model, and then it generates answers. And so from the task-oriented dialogue perspective, then there is a lot of reliance on this dialogue state tracking. And if you want to hold the system accountable, then you should be able to tell you like what issues it has in its assumptions or what it thought that you had said in its beliefs, and so on. And there could be many reasons or multiple types of dialogue state tracking errors in dialogue systems. For example, it can hallucinate slots and values in certain cases, or it can miss some of the things that the user has specified so far. And each of these would result in a mismatch between what the user has asked and then what you're returning to them. So maybe let me give some examples. Imagine a very simple example. Imagine a user asking for expensive restaurant in the south side of the town. This example is from the multi-voice corpus, which we use in some of our experiments. In this case, there are two arguments for this intention, expensive and south. Imagine this is some visualization of the restaurants that we have. So what the user wants are these three that are highlighted in the green oval. If the system makes an error and then it misses a slot, let's say south, then it's going to have all these other results in addition to the correct ones. And then if it picks to present one of these to the user won't understand, and they may pick something that is not matching in terms of error. It's in the opposite side of the town. It can introduce additional slots, which would result in no availability, which would again be a mistake because the system would say to the user, I couldn't find anything that matches your request, then again misleads the user. Or it can misunderstand some value, then it totally gives some random set of results, which again doesn't match what the user is asking for. So we targeted both of these types of, all three types of issues in the output of dialogue state tracking. And once we detect those issues, then we add a model for introducing additional, let me call it additional friction. So basically, we get the results from the database, but then we also get confidences or some annotations of what errors the system may have possibly made, and then ask them to the user, and then just correct them in the follow-up dialogue. So that was our initial proposal. And so for this purpose, we looked into can we estimate the confidence of dialogue state tracking output? So in this case, the dialogue state tracking output is a set of values of is a sequence of slots and their values. And we would need some confidence related to each one of them, because if there are many values, that would be tricky to keep confirming them with the user. And we looked into the literature. People have been looking into using language model probabilities with open source, open weight models. People have been looking into asking back the model, how confident are you? Or generating multiple hypotheses with the model, and then estimating confidences based on those. So we basically tried each of these methods, combining them and so on. So the one limitation with this form of confidence-based method is it can detect false alarms or value errors, but it will fail to detect if the model has missed something, because it's not in the output. We don't have any confidence on it. So based on this, we thought of, can we actually have additional shallower accountability models for dialogue state tracking? So in this case, again, we do have an encoder-decoder architecture. So context goes as input, and then the dialogue state or the belief state comes as output. But we added a simpler head to the last token, for the last token of the input, that would determine whether for each of the slot, whether that slot should be in the output or not. And when we train, we actually minimize both losses, weighted combination of both losses. And this additional slot detection actually provides us first some confidences, additional confidences, but it also tells us, like, this slot should have been in your output, but you're missing that. So how do we use to recover from any of the errors? The simplest thing could be use the confidences to filter out things that are spurious. That's something that we have tried. Give some improvements. We have also tried asking the model, without any friction yet, asking the model, can you go back and then look at your result? And then we force it to generate some value for the slots that we thought it is missing in its output. And then it can still generate none, which would mean that slot should not appear in the input, but it can actually sometimes generate values based on the context, so we recover those values. And the third approach would be just going back to the user and then asking, I thought you said this, but I missed the value, can you say it again? So what happens? These are some initial results on the multi-voice corpus. So if we don't, and then these are using Llama 3.1, fine-tuned using the multi-voice data set, which actually results in the highest quality outputs for us, and then highest quality confidence scores as well. So in dialogue state tracking, we basically measure the quality with joint goal accuracy, which means everything in your output should be accurate. You will get a score of 1 if that is the case, and then even if one thing is wrong, then you will get a score of 0. So if we don't do anything, we just fine-tune these models, then we do get 64%. If we actually jointly train it with the accountability model, we do immediately get some improvements, going about 5% relative. And then once we start correcting, using some form of a threshold on the probabilities from the accountability model, then our accuracy, joint goal accuracy, improves even further. The issue with this approach is, after some time, like as you reduce the threshold for checking things or asking the model to put things in, your performance can start degrading as well. And then if you just add one turn of dialogue in about like 8% of the cases, then your actually joint goal accuracy improves further. So this is assuming a cooperative user, meaning you ask them something and then they give you the right answer. But at least the dialogue opens up way for correcting the results, and actually it doesn't go down, it can go all the way to 100%. But that would mean asking too many questions to the user, which could make the system usable. So that's probably not the ideal situation. So moving on from task-oriented interactions, which were the initial studies that we performed, towards embodied AI. So as I mentioned, in embodied AI, these forms of questioning or interactions, which we call friction, appears naturally in human-human role-playing interactions. So back at Amazon, we did collect the data set we call as TEACH to study this form of interactions. And we mainly use that in order to analyze what sort of frictions can be introduced and when can we introduce them and so on. But here is some example from there. So user asks, can you make me a coffee in a mug? Then the user, the system can easily ask, where is the mug? And an actual human does. Because there are several cabinets in the environment, it will take a long time to figure out, and then maybe it will annoy the user. So friction occurs naturally in many of these dialogues when the agent fails to execute what the user wants, or when there's some ambiguity in the environment, it just consults the user and then asks such questions. The degrees could be, of course, varying. So we started working on this topic using React, Reason and Act. I should have added a citation, apologies for forgetting that one. But basically, React asks a model to reason, to decide whether it should reason or act. And Act would be doing some action in the environment. And it has been shown in, for example, AlphaWorld or other data sets that it actually helps task completion. So we have extended this framework to actually introduce some speaking actions. So the model is asked to decide between reason, speak, and act. When it gets into confusing situations, then it can ask the user what it should do next. For example, here's an example from our data set where the model first reasons and then speaks and asks the user, there are multiple options, which of these I should look at first. Then a user can give an answer. So this is actually a user simulator in this situation, which is suggesting the true result, but it ends up with task completion at the end. So to follow up on some of the results that people got with the React approach, we experimented again on AlphaWorld. So at the bottom you see their original results. Our results are slightly better with just React because we just simply use a better model. But when we add a speaking turn, again, less than one, on average, these are less than 1 turns per dialogue, then we can improve the task completion or task success rates significantly with respect to the original re-implementation of the original React approach. So to conclude, introducing friction in interactions can be helping the user to make better decisions, can help the agent to make better actions, better decisions also. It can, as we have shown in these 2 cases, it does improve the task completion. It could be tricky to balance the introductions of frictions. Like nobody wants a dialogue system that constantly keeps talking. So it's important to identify the ideal situation. And for these things, for example, tracking the conversation state is important. This is one area that we keep pushing. And enabling control over a dialogue system or over a model, language model, to realize some of these frictions is also another important area that we are looking on as part of our future work as well. So thank you for listening, and I'll be happy to answer if there are any questions.
Thank you very much for the talk. So yeah, I invite you to come to the stations for the microphones. And I think we might still have volunteers who can run the microphone over to you if necessary.
Thank you so much for the talk. It was very clear and super interesting. So I have some questions around the data you collected with human users. When you showed your typology of different types of friction, it made me think about how I use these very differently depending on who I'm talking to. So if I'm talking to a child, I use a lot of these, but some of them would be inappropriate if I was talking to an adult. And so I wondered what the assumptions were of your users when they did create this data that you collected. Did they think they were talking to a bot, or did they think they were impersonating a bot? And did you find that that changed the quality of the types of frictions they used and when?
Thank you very much. Great question. Most of the data that we use were collected before we actually even started studying these forms of frictions so far. And the assumption is they are just like they are suggested they are talking to an agent. And then the agent is suggested that the person playing the agent is suggested that they are talking to a human. But no information is specified, and then that's a very good point, depending on who you talk to, or also depending on the situation. Because if you see the user is in a rush, well, just like minimize whatever would make the most impact, or whether they're calm down and so on. Or it can depend on the personality. Some people may adapt. So I think we need to better assess the situation, so that is something that we are looking into too. But unfortunately, we don't have any results yet, but I do agree with you that these things should be super important when introducing these forms of turns and frictions.
Hi, thanks for the lovely talk. I was a bit curious about the spurious states, like usually when you have human-to-human interaction, so we have other ways to understand what someone is looking for. But when it's machine and human, so machine might ask many questions, just like this example, like what kind of food? There can be thousands of food. Should there be a limit, like how many states it's considering, or how much follow-up questions it should probe?
Yeah, absolutely. So in some of our earlier work, we actually assigned some cost to each of these conversational actions. It's just a heuristic, like we don't know what the exact cost in what situation should be. But we were able to minimize, like we were able to make the agent learn through reinforcement learning when it should ask these questions, and without introducing too much cost. So it was just like sometimes you can maybe take 3 turns around the house. You would figure out what the user is asking for. It may be less expensive than asking the user. Yeah. So ideally, there should be like some form of a balance and then learning. And then confidence is one feature, let me call it that way. Model certainty. Certainty of the user when they are performing their actions or requesting these things could be like one other factor. The situation in general could be one other factor, and then ideally one can actually learn or adapt to the situation to ask the questions, and then it should be possible to learn. That was our earlier work.
Thank you.
Thanks.
Yeah, thank you, Dilek, for the talk. So I just had a question. So in the pre-LLM era, the big problems with the task-oriented dialogues was open out of domain, queries, or when the user was starting to talk outside of what was planned by the SLU and the task manager. And with LLM, you have at last, this possibility to have a more human-like dialogue, because you can have this, mix of chit-chat and task-oriented, which is basically what we do, when we talk with each other with humans. But on the other hand, then you have the disadvantages of this, mix, because you can have hallucination, like you show, and everything. So do you think we can really tame the LLM and keep it within the dialogue state that you define in advance, and keep also some mix between chit-chat and open domain, interaction that would make it really feel that it's like human-like dialogues?
Very good question. I think we do need to be able to have some control over what the model generates, because it can just generate long things that it's not supposed to, or things that may not be reliable. But limiting it too much towards what exactly the API can handle, I think was never too great, in the sense that users don't necessarily know when they come to talk to an agent what is covered by the API and what is not. So they try it once and it doesn't answer because they have misalignment between what they think the system can do and then what the system actually does. And then it was, I think, in general, a bad experience. So I think it's very important to be able to benefit from what the LLMs are bringing in terms of like handling the chit-chat, handling even like slightly different, or even being able to explain what it is doing, what it can do, what sort of API it has. But I think it should be very non-opaque in terms of like telling the user, like maybe I'm like looking at this API, this is what I can get, or in certain cases, I don't really have APIs, this is what I found on the web, and maybe it's not reliable, you may want to check it, and so on. So maybe that is going to be the solution to having like some more natural interactions. But that said, I think we do have some more work to do. Thank you.
Thank you for the talk.
Thanks.
In the beginning, you talked about users' over-reliance on dialogue systems. So what measures are taken here in this context to avoid users' over-reliance?
So our idea is basically being more clear to the user in terms of what we understood about what they said. So they can immediately correct, like, oh, that's not what I was asking for. Or we do provide, like, we don't rush the interaction, or we provide some confidence, like this is something that I found on the web, may not be fully reliable. You may want to check their web page, like providing some additional support to the user. So they don't immediately say, okay, book me. Because if you say some of these models, well, things have changed a little bit, but some of these models, when you say, like, can you book me a table? They'll say, okay, I booked you a table. Well, when did you book it for? How many people? You didn't ask me all these questions. You may be misled into thinking that that has happened. So there should be like some form of clarity. And then that's our approach. Like, can we do that through dialogue? Like, not just rush into things, but provide some clarity to the user, some visibility to the user, hopefully without necessarily boring them too much by explaining everything. Yeah. Thanks.
Thank you for the next talk. I have a question that is mostly a curiosity. There is a recent line of research that for now is mostly on paper, mostly theoretical, that where people is trying to explore, LLMs that could be used to evaluate all those LLMs in a specific context, but the LLMs that is doing the evaluation has access to create a dialogue with an expert, with a limited amount of questions, of course. For now, this paper has been looking at what is doable in terms of scaling of computational evaluation by using this process, but I wonder whether some of the work that you're doing here could also be used in that context.
You mean for evaluating whether the system was?
Yes. Yeah.
It could be, especially if another agent was maybe like doing some more reasoning of what is the user wanting, what do I have in the back end, is it matching what the user is asking for? There could be, I can see some. And then it could also be useful like when the system returns some response, like to evaluate whether the system response is necessarily matching what was being asked. So I think it could be used for evaluation for multiple purposes. So I'm mostly thinking about, like, can we use the approach for, if the system introduces some frictions, that I need to think a little bit about it. I mean, it could be.
That's the question. What is your thought? You think this is, relatively promising, or it's something that is not the right way to go? Yeah.
No, I think it could be promising, because if a model makes assumptions, if it is not explicit those assumptions, via friction it can make them explicit. That would provide some useful information to some evaluation also. So that could be, I think, so providing more visibility to a user could mean providing more visibility to another model with respect to the results and so on. So I think it could be, but we haven't tried, but that's I think, an interesting idea.
Thank you. Yeah.
Thank you.
Hi, sorry, thank you for the talk. I was just curious, because to avoid or actually try to limit at the maximum the friction, you need a large amount of data and very specific to each situation. So what are the kind of limits you can actually, what are the limits, the technical limits you can go now? And also the question is about the ethical side, because if you need to collect data all the time to be sure to be able to respond to the user rightly at the right time, how, what are the limits nowadays for this kind of tool?
Fantastic question. Actually, it's good that I have this slide open because we do use data to analyze what sort of friction happens, what sort of friction humans use, which ones are useful, and so on. But for training a model, we do actually rely more on user simulators because for training any dialogue system, you would need a lot of data. But these days, and then in this work, we had used user simulator. It was simple in the sense that it would always give you the right answer, whichever is the easiest way to reach the target. But we were introducing some noise because humans don't necessarily always know. And then we were seeing that we can actually learn to be robust to this type of noise and so on. And then this was like very simple, like very earlier work. But in the current situation, we do actually use LLMs to build models of users also, and then create user simulators and then let them interact. So we do have a ton of sessions. And then from each one of those, given the user goal, we can see how long it took to complete the task in terms of the number of turns. And then we can also see how long, what percentage of the times the task was successful. So we can compare two systems with the same model of the user to see whether system 0, which doesn't include anything in terms of friction, is better than system 1, which actually introduces this type of friction. And then usually user studies come after that, and then we just use the actual humans for evaluation, not necessarily to collect training data, because like you say, that could be very expensive, and it could also be torturous to the users if we do to introduce too much friction. Yeah. Thank you.
All right. Well, thank you, Professor Hakanat, for the very stimulating presentation.
Thank you very much.
Thank you.
Thanks.
So our next speaker is Professor Mirko Ravanelli. So Professor Ravanelli is an assistant professor at Concordia here in Montreal. He is also an associate member of Mila, and he also previously did his postdoc here as well. He's very well known for his work on deep learning for conversational AI, and you probably have encountered his package, SpeechBrain, which is an open source package for conversational AI. So thank you very much for being here. We're looking forward to your talk.
Thank you for the introduction. So yes, today I would like to talk a little bit about multimodal LLMs, and in particular how we can build multimodal LLMs that support the audio modality using the so-called discrete audio tokens. So we were joking also before, so language models is not something new, right? So language models have a long, very long history. And they were not originally designed for generating text. At least this was not the main purpose. The main purpose was like to assign a probability to some sequence of words. So if you have sequence of words, right, W1, W2, W1, you can factorize this joint probability in this way, and the task becomes predicting the next word given all the previous one. Okay? So the first approaches, like back in time, were n-grams models, were just methods based on counting and smoothing these kind of statistics. They were dominant, I think, until 2010, very roughly. But at the beginning of 2000, people like, for instance, Yoshua Bengio, realized that we can learn a very good language model using neural networks, where instead of counting, you use representations, high-dimensional representation that you learn from data instead of counting occurrences. This work was unnoticed for, I would say, approximately 10 years. Then, people started to see very good results with the recurrent neural networks, which, are better than NLP because you can use like arbitrary long context if you want. And now the dominant approach is transformers, which, are kind of changing our world because of their performance. There are different ways you can use transformers for building a language model. For instance, you can use bird-like architectures, or these days, a very popular way to go is these autoregressive transformers, where you have your text, you tokenize your text in tokens, and your task is predicting the next token. So to every input token, you you assign an embedding, right, that you learn. You feed this embedding into a transformer, and on top of the transformer, you have a linear classifier, which estimates the next word. You feed the next word into the next step, and you move on this way. So this is actually a kind of very, let's say, simple and straightforward architecture, but it's enough to achieve the impressive performance that we are observing today. And in particular, what we discover, I would say in the last couple of years, is that if you use a lot of brute force, right, and you massively scale up this architecture, your results are impressive. So that was a kind of shocking, right, to many of us, including me. So I couldn't think than just like scaling up this straightforward architecture, rather straightforward architecture, and this simple task will lead to this level of, let me call it, intelligence that we are observing these days. But that's a matter of fact, and a big trend these days in language models is scaling up, right? Just applying brute force. I'm not sure how long this like things will last, because at some point we will reach some kind of physical limit of the world, energy limits, etc. But for sure, this is one of the trends that we are observing. There are other trends going on. One is like multiple agents, right? Like instead of having a single neural network, having multiple neural networks that kind of interact with each other, like for instance, for making better reasoning. And the other big trend that we are observing these days is multimodality. So yeah, all their most recent models, right? Also Llama 3.1 or 2, they support multiple modalities. And this is a big trend, right? So we don't want any large language model that only work with text, but now we want them to support images, videos, audio, and in the future maybe other modalities. And why multimodality? Multimodality is the key to achieve even higher level of artificial intelligence. Because with multiple modalities at the same time, you can have a deeper understanding of the world around us, right? So you can correlate modalities and learn in a more direct way than just than learn the world around us through text only. This might lead to more robustness, better generalization, hopefully fewer hallucination, even though maybe this is not still clear. And in general, this will help users. It will give more flexibility to the users, right? And inclusivity in the sense that the users, they can choose their preferred input and output modalities. So how can we train, how can we create a model which is multimodal? So one strategy, very popular these days, is not the only one, but I'm just telling the most popular these days, is to tokenize all, right? So we not only tokenize the text, that's very easy, right? But we also tokenize the other modalities. For instance, we tokenize the audio modality, right? So one possible architecture here is to every time step, right? You have in input one or more modalities, for instance, the text token and a corresponding audio tokens, right? And in output also, you have multiple modalities. This is a pretty convenient architecture, right? Many people are working on that because, it offers interactivity and also duplexity, right? If you have an architecture similar to this, you can speak, right? And in real time, the system can provide some text output, or you can speak and, the system can reply while you are speaking with a little bit of overlap that makes the overall architecture a little bit more, the overall system a little bit more natural. This is the architecture that many people are using, and here is an example from Qtai. You may have seen this demo.
Hello, how are you today?
Hello, can you tell me your name, please?
Hi, my name is Moshi. How can I help you today?
Hi, Moshi, can you tell me more about yourself?
Certainly. I was created by the non-profit research lab Qtai, which focuses
etc., etc. So you have seen here this kind of chatbot is multimodal in the sense that you speak, right? The robot replies and also provides some text output. And that's done with an architecture which is essentially very similar to the one mentioned here.
Hello.
Okay. What's the problem though, right? So we said that tokenizing text is very easy, right? So you can take some words, and tokenize with BPE, for instance, and other rather simple algorithms. But what about the other modalities? There are modalities which are continuous. For instance, the audio and speech are natively continuous signals. So think about the waveform, the original waveform. It's not really continuous because in the end, the original signal is continuous, but then we do some kind of analog to digital conversion with sampling that discretizes the signals in time, and quantization that discretizes the amplitude. But the number of samples and the number of bits per sample is so high that we can approximate the waveform as a continuous signal. Also, sometimes on top of the waveform, we compute some kind of features. For instance, we can compute a spectrogram, which is derived from applying the Shor-time Fourier transform. And also, this representation is continuous because every time frequency point is actually a real number. In some cases, like we want to downsample properly the frequency axis, and we apply the MEL filters, but also in this case, even though the representation is more compact, it's still continuous. These days, we are also using a lot this self-supervised representation, right, from popular models like Wave2Vec, Hubert, WaveLM, but also these models, which provide state-of-the-art performance in many tasks, they provide continuous representation. So a problem that is emerging in the community is the following. So how can we discretize audio and speech without losing too much information? That's a relatively new problem, right? So before we were just using continuous representation, but now stimulated by this need for multimodal LLMs, this problem has become central in the community. And I think here what we would like to do is to eventually create this set of universal audio tokens which works very well for multiple tasks. We can expect that people will use multimodal LLMs for a large variety of tasks, speech recognition, audio editing, etc. And we want to support them in a proper way through powerful and robust audio tokens. So I said this is a relatively new problem. The community is a couple of years. We are working on that. And in the literature, we can find approaches which refers to two main categories. One is called compression tokens, also called audio codec. And it's very simple. So they start from the original waveform. We encode the waveform with an encoder, for instance, a convolutional encoder. Then we apply some quantization blocks, typically multiple blocks of residual vector quantization, where there is a codebook, right, composed of a limited number of learnable vectors. And then we try to reconstruct the original signals with a decoder. So pretty much this is the case, right? And normally in the system, they also use an extra loss, adversarial loss, which makes sure the reconstructed signal is indistinguishable from the original one. But that's pretty much all. And systems like SoundStream from Google and Encodec from Meta, they work like that. Another category is the so-called semantic tokens. So as I said before, there are already very powerful models like Wave2Vec, Hubert, WaveLM, and many others, which provides high-quality continuous representation. So these representations are continuous, so it's natural to take a look at the rich information that we have in these models and try to discretize. And normally this is done by applying a clustering operation in different layers. So that's easy to say, but hard to do. We studied this problem quite a bit, right? And we recently presented this paper at Interspeech where we explain how, what are the best practices to extract discrete audio tokens from this self-supervised model. So more specifically, so what we do, right, you start from a SSL model let's say with LM. This model has several layers, right? We figure out that it's very important to properly select the layers that you discretize. The biggest error you can do is to discretize only the last layer. That's a big error because there are some tasks that instead rely on low-level information and you don't have any more low-level information in the final layers of the architecture. So it's very important to discretize early layer, mid layers, and the last layers. You discretize, you apply k-means, and you create some sort of discrete representation where every cluster corresponds to a token. There are many important problems here that we try to understand. So which are the layers to cluster? As I said, it's important to discretize different layers. What is the optimal number of clusters? On which data set do we have to find these clusters? How can we train a vocoder on top of these discrete tokens? So sometimes we want to go back, in generative tasks, we want to go back to the original waveform, so we need to train a vocoder. So how can we initialize these embeddings? I will show some results later. And also, can we learn universal token? This way, can we learn universal tokenizers that works for both discriminative and generative tasks? So this is our approach. So our approach is this. So we discretize different layers. Then we put together the continuous representation associated to the tokens through an attention model. And then we apply these tokens to specific downstream tasks, which can be discriminative, like ASR. In this case, we just feed these tokens into the ASR model, for instance. Or can be generative, where we use these tokens to generate audio and speech. In that case, you need a vocoder, and we also propose a scalable vocoder based on hi-fi GAN, a modified version of hi-fi GAN that, given the tokens, goes back to the original waveform. So, as I said, so in the paper you can find all the details, but what we found is that it's very important to select the layers that you distill. Is very important because there are some tasks like, for instance, speech recognition, which benefit from the information of the last layers, and some tasks like TTS and speaker verification, which instead prefer low-level information. So a good practice to create universal audio tokens is to kind of, at the same time, provide both low-level and high-level information. So here are some results. About, for instance, what is the best number of clusters? Okay, that's empirical. We found that for most of the tasks, 1,000, 2,000 clusters is fine. If you have more cluster, you increase the bit rates without having a performance improvement. If you have less cluster, fewer cluster, you lose performance. And also, here we also studied another aspect. So what happens if we, every token should be associated with a vector, right? During the downstream architecture task, you can decide to randomly initialize this vector or to initialize this to the centroid, the position of the centroid that we derived with k-means. And the result is that, okay, leaving the model learning from scratch the mapping between the token and the embeddings is the best way to go. Also, on which dataset you have to compute these clusters, these like tokens, there are two scenarios. One scenario is when you compute the tokens on the same dataset that you use for the downstream task. That's a clear in-domain condition. But the more realistic condition is when you compute these tokens. You learn these tokens on one dataset and you test on others. That's out of domain. Unfortunately, there is still some gap between the in-domain and out-of-domain performance, but I would say overall the gap is not huge, and even with this out-of-domain performance, you can have you can have tokens which are usable. So and then we ask ourselves one question. So now we have found a strategy to extract properly these audio tokens from SSL model, but are these semantic tokens better than the compression tokens that I mentioned before? So we tried to take a look at the literature, but we didn't find a clear answer. So we decided to create a benchmark ourselves, which we called the discrete audio and speech benchmark. And yeah, so in this benchmark, we consider different tokenizers. The most popular open source one that we could access. So we consider both semantic tokenizer, the one mentioned before, with the approach that we studied in the previous paper, and also compression tokenizer like encodec DAC, and speech tokenizer, which is a hybrid tokenizer. Then we tested these tokens on a variety of tasks, both generative and discriminative. So we tested on automatic speech recognition, speaker verification, emotion recognition, intent classification, keyword spotting. We also tested them on generative tasks like speech announcement, speech separation, and single speaker and multi-speaker text-to-speech. So we did tons of experiments. We tested many different downstream architectures for every task, and we pick up the best results. So we did really tons of experiments to have something which we think is as fair as possible. And we created this big table which summarizes the performance we achieved with discriminative tasks. So it's a lot of numbers, but what we found is that these semantic tokens tends to outperform the compression tokens in different tasks. We also noticed that, unfortunately, these semantic tokens, they do not capture well speaker recognition. They do not work very well for speaker recognition. They do not capture that well speaker information, so there is room for improvement here. But the sad news is that there is still, even though we have kind of decent performance with these tokens, even with the best tokens, there's a big gap between the performance that you have with the discrete audio tokens versus the performance that you can have, the state-of-the-art performance that you can have with the continuous baselines. Here are the results for the generative task, which are similar. Also in this case, semantic tokens outperforms compression tokens, or tend to outperform. That's a bit surprising for the community, because there was like a common belief that compression tokens are better. Instead, we didn't find that. We find that still semantic tokens are better. And still, unfortunately, there is a big gap with continuous baseline. So we did tons of experiments, and who is the winner? The winner is the discrete wave LM. So here you can find the ranking aggregation, right? For all the tasks, right? We computed the ranking, and here is the average position in the ranking. And it turned out that wave LM is the best tokenizer that we found among the open source available. And you can also see in this table, confirm that these are the semantic tokens, these are the compression tokens, and the gap is significant. Just to give you an example, a couple of examples, here is the performance that you can achieve using the text-to-speech, right, using the best tokens.
The fact was, he did not keep the classification of prisoners on first arrival in his own hands, or even in that of his officers.
This is another example.
She was a most charming person, but she was 10 years older than I. She was my sister's governess. He quietly said, she was the most agreeable woman I've ever known in her position.
Etc. So you can see that these are generated samples, so not original recordings. So you can hear that even though the voice is not perfect, it's still kind of usable. So unfortunately, our conclusion is that we are still far from an ideal solution, even though I think even in the current version, these audio tokens are good, but I think we are far from an ideal solution. These semantic tokens are not perfect, right? They are computationally expensive, for instance. Like here, you can find comparison between compression token and here, and semantic tokens here, in terms of encoding time and encoding memory. And it turned out that because you use big self-supervised model, these semantic tokens are very expensive. They do not preserve identities well, and unfortunately, there is a big gap with the continuous representation. All the models that I discussed here, including the DASP benchmark, are available on SpeechBrain. SpeechBrain is this kind of large open source toolkit that I'm leading, and we put all this research there. Everybody can go there, right? And everybody that has like a tokenization algorithm, right, can go into the proper recipe of SpeechBrain and replicate the results and compare the results with our ones. So let me conclude just saying a few words about the future. I'm optimistic. I think we will solve this problem quite soon. So the community, I would like also to contribute to this field and study solution for learning universal audio tokens. I think there is a way to do it, right? So if you, as you have seen before, compression-based tokens are still pretty simple. They were mainly designed for compression, streaming, storage. They were not really designed for multimodal LLMs. So I think if we revise this architecture with, for instance, massive multitask learning, which involves self-supervised tasks, supervised tasks, I think also tasks which involve some kind of human perception, I think we can definitely fill the gap and have better, or at least more universal audio tokens soon. Another project that I would like to, other ideas that I would like to explore are this, my lab is working a lot these days on interpretability, and we would like to learn, to see if we can learn interpretable audio tokens. What I mean with that? I mean that if you take a look at the text tokens, they are kind of interpretable because they are connected to a specific and deterministic piece of text. This is not the same for audio tokens, right? So are not very interpretable, and we would like to study if we can kind of learn universal audio tokens where every codebook is connected to some kind of specific patterns in the original signal. That's another interesting project, which hopefully we will publish something when we have good results. That's it. I would like to thank you for your attention, and also my collaborators for working with me on this exciting project. Thank you.
Yes, questions? Oh, joint question.
Oh, sorry.
Thank you for the talk. So I have kind of a two-part question. The first question is, in your second model where you do clustering, did you find that when you cluster, the tokens are kind of separated based on phonemes, or like did you find any relationship?
Yeah, so there is evidence that when you cluster the final layers of the architecture, you tend to identify cluster which roughly corresponds to high-level information like phonemes. But it doesn't happen when you cluster low-level layers, where instead you cluster low-level information like some kind of spectral things altogether. Yeah, but you need both, right?
Okay. And so based on that, like you said that we're on a path to multimodality, but we're also on a path of like multilingual models. And I don't know, at the end, like you mentioned, okay, maybe you doing a lot of tasks can make the models more robust, but also exploring multilingual might make it even more robust. I'm thinking, like when you were talking, I was thinking like in Vietnamese language, I don't speak Vietnamese, but I know like even like a certain phoneme, like a vowel, with just different tones can mean a completely different thing. So I wonder if you think that like, what would be in this case the approach of like making these models like robust to even specific languages that are not like English, that every like little changes can mean a lot?
Yeah, I think it's good when you train a model like that. So you should train on multiple languages, right? So, and hopefully, if you train on a sufficient number of languages, the model is generally enough to support a languages not seen. But that's actually a very interesting topic. So I think the solution here is mainly natively when you train, for instance, compression-based tokens, do not train only on English, but train on multilingual dataset natively. So hopefully the model will capture also some language-specific patterns.
Thank you.
Thank you.
Yeah, thank you, Mirko, for the presentation. So just had a question, about the last part you were talking about interpretability. So before we had very interpretable models because we were based, on speech science. So we had the phonetic representation, we had some, vocal track trait, and so on. So now, with this unsupervised token, we lost a bit this interpretability level. And in the same way, like in text, we do probing to try to find out, what models can really master, in terms of linguistic properties. Is those people, trying to see in this kind of unsupervised units, what can we find from the previous, work was done to describe, how speech is generated by humans with our, vocal track and everything.
Yeah, actually, that's a very interesting topic, interpretability, and it's I will say an open topic, right? Nobody knows how to make deep learning really interpretable, and even don't know if it's possible. In my lab, we are working on that pretty much. We have like a couple. We had a paper at SCML, now a paper at NeurIPS about that. How can we build audio classifiers which are interpretable? And it turned out that to some extent it's possible, but specifically here, what we would like to do is to train tokens which are interpretable. So our idea is to add some kind of constraint. When you learn this model, this like big supervised model, we would like to study proper constraints such that every vector here that we learn is mapped to some kind of concentrated pattern, right? So instead of being mapped to some kind of random thing, we want, our idea is to make sure that every vector is like connected to some kind of clear pattern, and not a pattern which is also local, not just necessarily spread out. That's our idea, and I'm not sure it's going to work, but in general, I think these things is missing. As you said, we are going towards more and more complex system, and we are losing this interpretability. So I think will be very interesting to at least try approaches that restore, at least in part, the interpretability that we are missing.
There's curiosity, how does this kind of units work, for overlapping speech? Because it's always been a big problem, we have two voices which are mixed together. So can you manage to disentangle when you have this?
Yeah, so we want to include here in the task that we are addressing, we always include the speech separation thing. So our goal is to train this tokenizer also on challenging tasks where you have multiple voices, right? And you try to extract information from both speakers. Yeah.
I guess I have a quick question. I was wondering, isn't it expected that with semantic tokenizations, it should not encode speaker identity, or is the speaker identity part of the semantics of?
So historically, this like SSL model that were mainly used for speech recognition, right? And then people started to use for many other tasks. My experience has always been that they are critical for speaker identification, right? So speaker recognition, it's not super easy to use this model. So somehow this model, they kind of, during training, they are not giving enough importance to the speaker information. So I think this is something we should definitely fix. It's expected, a little bit expected, considering how hard it is to train a good speaker recognizer on top of this continuous representation. So it's easier to expect that even for discrete representation is harder. But yeah, that's a problem we need to fix, and probably just a matter of like modifying the training losses or something like that. Yeah.
Right, thank you. Any other questions? All right, well, thank you very much.
Thank you.
So our final speaker of the session is Dr. Roland Memisevic. He's a researcher at Qualcomm AI Research in Toronto. His research is on making AI systems more human-like through audio-visual interactions. He's done a lot of impactful work, including fundamental contributions to learning, and also more applied and practical ones. So for example, he was on the Theano project, which was developed here for deep learning. So with that, I'm excited to hear your talk today. So we'll just wait for it to switch. And yes, away we go. Thank you very much.
Thank you. Okay, thank you for the introduction. I'm going to talk about end-to-end learning of camera-based situated interactions. And some of the slides are based on a webinar that I gave recently, so they're kind of very polished and a little bit glossy. But bear with me. So what is the basic idea behind this? The idea is that you want to build models that are able to interact with humans naturally, fluently, and in real time by utilizing the camera that you may have on your device, like on your phone or a laptop or wherever, maybe also the microphone, and then just have an interaction with you in real time, just right here, right now, basically. So that's obviously a kind of product vision, and it can be useful for things like humanoid robots and maybe less humanoid robots, but also mobile phones that you can interact with that can teach you things, help you to prepare recipes, tell you what to do next or how to repair your faucet at home or whatnot. There's also a scientific reason, though, behind doing all of this, and that is that if you try to build a model that can do that can interact with you in real time, then while you're doing it, you sort of implicitly have to solve pretty difficult and deep problems like grounding, perceptual grounding. So the model has to be able to attend carefully to what's happening in the scene in front of it, and all the words that it uses have to be linked to that perceptual input stream somehow. And so this can't work, I would argue, unless we somehow figure out how to fix grounding and all of these problems along the way. So it's a very, very challenging scientific problem. And I'm going to talk about some approach to go about this and a very specific narrow target application alongside which we have been building such models, which is fitness coaching. And I'll explain in a little while why. So here's the glossy part of the glossy slide. So this work is going to be rooted in end-to-end learning, like hardcore end-to-end learning. And so it's based on the insight that a lot of progress has been made through the years, maybe through the decade, 1 or 2 decades now, by taking the complicated modular pipelines that we have been building for various tasks and then just replacing them by a neural net and then training that neural net end-to-end on the task if data is available. And so that started actually pretty much with speech recognition in around 2008 when people realized neural nets trained with backprop worked very well. And then Ilya from back then at Toronto took this and with Jeff Hinton and others and said, okay, let's try this for vision. It seems to work well for speech, let's try it for vision. And then it tried it on ImageNet and it worked very well. Then Ilya again and some other folks, Dmitry here from Montreal and others tried to apply this to translation end-to-end, also worked very well. And so on and so forth. Later instance of this is models like GPT, where you try this to do generative modeling of text, etc., etc. So what we're asking in this line of work here is, what if we take this end-to-end learning type modeling approach to its very end, which means we want to train a model end-to-end to operate in real time, have some kind of perceptual input coming at a certain frame rate at it, and act accordingly. And so if we had our hands on end-to-end training data, which is the perceptual input stream, whatever nature that might take, like vision, say, and the actuator or language output stream, and if they are aligned, then in principle we should be able to train a model to just do this kind of thing end-to-end. So that's kind of the idea behind this. Okay, and that's what we're going to try, and we have made quite some progress, I would argue, in this lately, us and the community overall. So first thing that we would need to do this, so I'm going to go just very concrete now, how we go about this, is a model that can take ingest a perceptual input and can generate some kind of outputs and do this in a streaming fashion. And so a natural choice of model that sort of the community is converging on is this type of system here that has an autoregressive language model as the backbone, and that's convenient because it's already a streaming architecture in some sense, right? It just generates one token at a time and it just goes along. It's a little bit of a cheat in the sense that it's functionally like a recurrent net, but it keeps the context at least for a certain amount of time, so it kind of memorizes everything so far. That's a convenient cheat for the time being, because if we want to have a model interact with you for like 30 seconds or 2 minutes, then that cheat is actually perfectly viable in applications. If the model is supposed to have long-term memory of what you did yesterday and so on, then there needs to be further research and modeling based on recurrent states and whatnot, right? And some kind of memory and whatnot. So anyway, so now we have a recurrent-like language model that can just generate tokens one at a time. And then attached to that, we can, via some kind of adapter, project visual input. So in our case, it's going to be vision. Perception is just going to be vision. And then the model can be trained to take that visual input and stream tokens out, essentially. That architecture has become quite common in the community, but the way it is currently used mostly is for image captioning and these sort of things. So there are models like Lava, Flamingo, earlier ones, and many, many, many others that do this now. But they usually take one input image and then generate a sequence of tokens in response to that. And so that's not streaming. That's image conditioned generation, essentially. That's not what we want to do. We want to do real-time vision comes in, real-time tokens come out. And so what's missing here is what's listed on the bottom right here. So if we want to have a model that streams, we need to have a freely interleaved sequence of tokens that the model generates and visual input, whichever form it takes. We need to be really careful about the frame rates. So if the camera streams somehow, you need to ensure that it streams at the right frame rate, or the model is trained to deal with some kind of glitches because maybe the system is not running perfectly and delivers frames at a very fixed rate and so on. So you have to freely interleave them and make sure that you figure out an architecture that can somehow deal with these guys coming in sequence, maybe not perfectly ordered and so on. And then the third thing, and the biggest challenge, is data. We need to have this aligned data of tokens paired with a camera stream. Yeah, I'm just going to continue. So here's an architecture that is a little bit more in detail, describing what this looks like, what this can look like. And so this is the model that we use for our fitness coaching test case. So in this case, the visual information gets ingested by the language model backbone through cross-attention. So imagine, when you generate the next token, you do self-attention to the tokens generated so far, or to the context. And so this model also enabled Llama model from Meta has a cross-attention mechanism and so on. Okay, so projecting, it's pretty trivial. There's a bunch of MLP layers between the vision encoded input using a convnet or whatever it might be. And then you just generate tokens just as usual, just always cross-attending to the visual input. There's one more aspect to this in this interaction scenario that's important. So in this case, when the model is exposed to a camera stream, it needs to know what to say and when to speak to you. And the way that we are solving this, or addressing this challenge here, is by having two types of tokens, essentially. Either the model can generate tokens as usual and say something back to you, or it can generate a next token, which is an indication from the model to the system, the surrounding script or whatever, to give it another camera frame of input. So when we train this end-to-end, we train the model to, by itself, come to the determination of whether it needs to continue watching, whether it just wants to keep watching silently without saying anything, or whether it wants to tell you something. Whether it thinks, okay, now I should, you just made a mistake, so I'm just better call it out on you. A lot of exploration is going to have to go into this kind of architecture and this, deciding when to look and when to talk and so on and so forth. So this is just one first stab at it, essentially. When it comes to the vision input, so I said you can take any kind of convnet or whatnot. In our case, we're going to look at fitness coaching. So we're going to watch a person do exercises right there in front of the camera. And that means that the vision model has to be able to understand motions, human motion patterns and stuff. And so it turns out 2D CNNs are not very good at that. And neither are VITs and whatnot. So what we do here is use a 3D CNN. And that 3D CNN is very, very small. It's based on efficient net, or mobile net. We have various versions of this. It doesn't really matter what the model is, essentially, but it has to be, in this case, a 3D CNN. And there's some trickery that we use to make this efficient. For example, when a new frame comes in, every time the camera gives you a new frame, we don't recompute all the 3D convolutions over time in the model, but we only update the hidden state for the latest frame coming in. And in order to make the model, prevent the model from cheating, looking into the future during training, the convolutions are causal. So there are temporal convolutions in the model, but they're only allowed to look backwards in time. And so there's a bunch of these kind of tricks to make it work, and then it runs in real time and fluently, and then the model can basically take in a real-time camera stream of pixels and at the output generate a stream of features. And that stream of features is then taken via cross-attention to the LLM backbone afterwards. Quick note, so that model is open source, and we have been working on this type of architecture, this kind of streaming real-time situated stuff in a startup that I worked on until we joined Qualcomm a few years ago. And so we open sourced this model, and it's called Sense, and I can take a look at it. And we pre-trained it on all kinds of motion patterns, so the model can be used for gesture recognition and all kinds of stuff. And it's all end-to-end, so it's always pixels in, use case out. Okay, so then we need data to train this type of thing. And for that, we actually, starting already at that startup also, created a data set that is based on fitness coaching. So as I mentioned, it's going to be an application very, very well-defined and crisp and simple. The user is standing in front of the camera and doing jumping jacks and squats and push-ups and various other things, like around 100 different types of exercise. And the model should tell you if you're going too low into your squat, not low enough, if you should get your knees closer together, what kind of mistakes you're making, or it just recognizes occasionally, if you're doing really well, that you're doing well. So it cheers you up and says, wow, this was a very deep squat, and keep going, and wow, you're pushing yourself, et cetera, which is actually really good to have when you're doing exercises. Having somebody, quote unquote, acknowledging that you're doing it, so being seen while you're doing it. So, so some entity notices how well you've been doing, and that's actually very nice when you exercise, at least for some of us. It's also good for this type of embodied, quote-unquote embodied AI research, because the fitness coaching session is extremely structured. So in our setup, we're using 30-second blocks of one exercise after the other. Within the exercise block, you are asked to do your exercise, and so the user has the expectation, okay, I'm supposed to do push-ups now, so I'm going to do push-ups for 30 seconds. And I would say nobody would expect, if you do weird things and just do the wrong exercise, walk away, or do something else, would expect the system to perfectly follow and call it out or whatever. People are more forgiving when a model is a technical system that is not perfectly grounded in every possible thing. If you suddenly climb up the wall and the model doesn't mention it, it's okay and you don't expect it to. It's still very useful if while you're doing your exercises, it actually recognizes and coaches you. So there's a it's almost like a game. There's a very structured interaction, yet the interaction is, besides all of those constraints, very freeform. So you can do fast, slow, you can do slightly wrong and whatever, and it has to be in real time, and it's real world pixels, right? So the user is just doing stuff and the model has to respond. So it's at the same time, it's sort of the perfect combination of very structured and controlled scenario, game-like scenario, but a very, very challenging task for vision models to get right, because it's real time, and a camera, it might not be perfect, and lighting might not be perfect, and so on. So the model has to deal with all of this. A few more details on this data set. So there's two types of data. There are short clips that are really, really critical to provide grounding to that vision model so that it understands what little nuances in your motions mean. So like what kind of mistakes did you do? How could you do better? And so on. And then the more recent thing is on the right side, it's the long-range videos, which are, as I mentioned initially, aligned sequences of tokens, that things you should say or could say, aligned with what's happening in the actual scene right now. The data is pretty substantial, so there's a couple 100,000 videos of clips for these across these different exercises, and then there's a few hundred exercise sessions long range, and each session has a bunch of exercises of these 30-second exercise blocks, essentially. So there's in the low thousands of long-range exercise interactions. Here's just one more view of this. So on the left, you see one example of a long-range video. So a person is doing stuff, and on the bottom, you see things that a reasonable coach would say as they're watching you. And on the right, there's the clips, and the clips are annotated with all kinds of stuff. And it comes in various formats. One of them is question and answer. So you can train the model in a pre-training phase, as I'll talk about in a moment, to answer questions. So you can ask it, hey, is the user going fast? Is the user going slow? Are they doing well, etc.? And then the model has to answer that question. And that way, we backpropagate into the vision backbone the ability to discern such things from the live camera stream. Video data sets are proliferating, have been for quite some time. But I think this interactive type of data is fairly unique. So this is a comparison to all kinds of data sets out there. And so there's all kinds of video action recognition and procedural data sets like YouCook, etc. There's a small number of data sets that are really about live interaction. And so to the best of my knowledge, it's only these three right now. So it's on the very right, it's our fitness testbed. And then there's two others. One is called Holo Assist, and the other is called WTAG. So that one is about preparing cupcakes, and Holo Assist is about a variety of tasks in the real world, like repairing things and so on. A difference between ours and the other two existing ones is that those ones are first-person view, so they are made to enable a system to watch through your own eyes, through your AR device, whereas ours is third-person, in that you're expected to put your camera in front of you and the model watches you as a third person. And so I'm excited about that one because it's a real situation of facing an AI system and asking the AI system to be situated and interact with you in a reasonable fashion live right now. How much time do I have? I know that we started a little bit late, and I know that I'm between lunch and the talk, so 11 minutes, okay. I'll go a bit quicker through this. So there's two good things about this kind of use case, right? The first one, it's an interesting application, and it's worth doing to build models that are able to interact with people. It can provide a lot of value. The other reason is a more scientific one, which is the grounding part. And I think one can take this argument further. So I think you could argue that language has a similar dual role like that. Can be useful as a way to communicate things right now, and that way provide value in this particular app. But it is also a very good sneaky way to get common sense into the model. And the reason for that is that a sequence of tokens is a very flexible and general way of encoding stuff. And that can be stuff that you want the model to be able to understand or recognize in the visual scene. So for example, you can use captioning and say, these are glasses on top of a laptop, and these are glasses besides a laptop, and so on. And if you expose a model to enough such data, then you would hope that the concept of glasses maybe might emerge because of the features that are conveyed through the pixels looking at glasses. But they're also going to learn things like on top of, left of, fast, slow, etc. So there might be a way to use end-to-end learning to instill some kind of grounding in vision models or vision language models, simply by taking a vision language model of the nature that I showed before and training it on such captioning tasks, for example. I mentioned this startup where we started this kind of work. Actually, back then, we had a model that was doing exactly that, and we had a data set called something something that was literally consisting of these kind of concepts. So we had people showing concepts to a model, like putting things on top of things, left of things, etc., and then trained the model on that. And the task can be conceived of as a classification task, say you classify the verb or something like that, but we could also conceive it as a captioning task, where you have to make a detailed description of what's going on, maybe with adverbs and adjectives and so on. And if we do that, we need a language decoder as the model that's attached to some vision backbone. And so this is a pretty seasoned model now. It's from 2017 where we tried that. And then we were actually able to show that if you train a model on an increasingly fine-grained task, where you go from classification into more classes, to simple captions, to more complicated captions, to full-fledged captions with adjectives, adverbs, etc., and then use that vision backbone, only the vision backbone, as a feature extractor in some unrelated or related downstream task, then the more fine-grained the pre-training task was, so the more sophisticated your captions were, the more you asked the model to go into detail about describing the scene and so on, the better those features were in generalizing to a downstream task. So it's exactly just using captioning as a way to ground features in real-world concepts, essentially, but doing that end-to-end rather than using some kind of architecture specific for that. So we took this model, and that was actually the model that I showed a little bit earlier. So we took it into 2023, and instead of the LSTM-based vision decoder, we put in a transformer-based decoder, and it was pre-trained. So it's like a GPT-type pre-trained model, and then tried it on a whole bunch of vision tasks, and that led to the model that I mentioned earlier on. So here it's the model running, trained on various visual skills, and then trying to tell you details about what it sees in the scene. There's a pretty big set of benchmark tasks out there, and the model does really well on that. And so it's basically end-to-end training, but the model instead of just being trained on the task, is also trained on a bunch of surrogate tasks that ask it to position things, tell you details about the scene, etc., etc. And it works really well. Last technical aspect of this, before I go to some results. One way to conveniently utilize this grounding trick, so training the model on captions for the sake of grounding, is that we can basically distill this kind of capability into the language model features without having to make this grounding process explicit at inference time. So what I mean by that is we train a model on a bunch of data that has tasks like questions, like you say, what is the user doing right now? How fast are they going? Are they going deep enough in their squat, etc.? So we train the model on an actual downstream task, which is this aligned teaching coaching type scenario, but we also train it at the same time on these question tasks. And whenever a question pops in, the model has to answer it. And after doing so, the features that the model acquires during that pre-training are able to encode a lot of details about what the user is doing without having to spell it out explicitly. So what we observed is that you train the model on a downstream task, but also on Q&A, etc., grounding tasks. The model does better on the downstream task because now its features are grounded in what's really happening in the scene. And so if you apply this to these synthetic data sets to assess the level of understanding and so on, it works really well. But then we applied it in the fitness system as well. And so that's the questions that you saw initially that are coming along with these short form videos. And so now I encourage you to take a look at the bottom part of the slide here, because that's the latest model that has that grounding in it and so on, that responds now to the user in real time. So this is really hot off the press. So the data set is released. It's actually going to appear at NeurIPS this year. This model is very new, and it hasn't been really published yet. But you see that the model responds in real time. This is actually running a bit faster, so you can cram more video into my talk. But it learns to know when it should tell you something, and it knows what it should tell you, and it's on point and contextual and so on. It also learns to count, interestingly. So it's getting at end-to-end counting, which is actually a pretty difficult task. So you have to understand the periodicity in the motion and so on, right? And there's a lot of traditional work on trying to make counting work. It's not perfect, so it gets it off by a few still. But I think it might just be a matter of training more and having a little bit more data. I think we already had that one, yeah? Okay, I need to go to the next slide. Okay, here's another one. So there are a few cases in there where we actually have people walk away from the camera, blocking the camera with their hand and doing all kinds of weird stuff, drinking a sip of their drink and so on. And then it's easy to have the model understand or say something sensible in that situation. So it can see when you drink and it can say cheers, and it sees when you disappear and then it can tell you to come back and so on. So that's all easy. Having this really broad, so you can do anything and the model understands it, would be a much more difficult effort because there just needs to be data for that. Okay, a few more qualitative results and some quantitative results. So since this is an emerging field, this real end-to-end training of this type of interaction, metrics are still evolving in this area, and so the whole community is trying to figure out how to measure this properly and so on, and then basically compare model performance to one another and so on and so forth. There is a lot of related efforts, so similar to this. One is robotics, so this is something that's also happening in our group, where the model is actually linked to an actuator, and instead of just talking back to you, it can also control a robot arm and do simple manipulation tasks with a similar philosophy of end-to-end grounding behind it. Okay, I can't resist to just make this final comment in the discussion. I would argue that what's happening with foundation models right now, so taking one model and training it on as many tasks as possible, and then just using it for different but similar downstream tasks, was foreshadowed a long, long time ago, specifically in a community that sometimes referred to as cognitive metaphor, and also analogy making. So there's George Lakoff and Douglas Hofstadter and so on, who have been arguing through the decades that analogy making is really what's at the heart of a lot of cognitive capabilities. And foundation models are sort of bringing this to practice because they really try to cram everything into a model so that concepts emerge that link various other concepts to one another. And I wrote a little essay, if you're interested in this topic. It's very, very dear to me and has been a motivator for research that I've been doing for many, many years. I wrote a little essay that's on arXiv now, where I argued that it's weight sharing that links these two things together, and it was sort of inevitable for foundation models to emerge if these guys were right, and I think this proves that they were right all along. To conclude, and I think this is also growing out of this kind of philosophy, vision can benefit language because perceptual signal can ground concepts all over the place. So you know what above means because you have seen enough instances of something above something else and heard the word or read the word, etc. So that's why you know what above means. You know what on top means and so on. But through some kind of metaphorical extension, you also know what on top of the world means, or he's on top of the field, and so on. And so the argument behind this, the cognitive metaphor school of thought, let's say, is that this is not accidental, but this kind of low-level grounding is key to basically all our language capabilities and so on. But it's also the other way around. So language can benefit vision because it is a way to encode tasks using captions or Q&A, etc., interactions and so on, that force the vision model, the vision backbone, if you will, in this type of architecture, to have features emerge that are very broad and generic. And so if we want to train a model what above means, we train it on captioning tasks, exposing it to many, many situations of above, and lo and behold, the model learns to use the word above in the appropriate way. Okay, I'm going to conclude here. Thank you very much.
Questions?
Hi, thank you. It's a lovely application. I was wondering, can it be used as an assistive application for blind people? We are seeing a lot of apps for the people who have visual challenges. So this looks a perfect suit for people who cannot see, maybe.
So that type of application, assisting the blind to get information about their surroundings is actually a very nice application that grew out of the many years of captioning type research that was done, right? Captioning models have been around for many, many years, and if you care about taking a picture of a scene and then having it described, then that type of data is perfect. And so it was a very thankful application that was then suddenly growing out of this capability. I haven't thought much about the extension of that in the context of such a real-time vision system, but it's imaginable. I mean, you can directly extend upon the image captioning scenario to live video captioning and understanding what's going on. There's somebody in front of you is trying to pass, et cetera, et cetera. So there's almost certainly a benefit in going from images to video and specifically to this like detailed understanding of, like situated understanding of your surrounding. But beyond that, I don't know. I don't know what kind of work is there. Maybe.
Thank you.
Yeah, thank you for the interesting talk. I'm wondering, since you have been working on this for some time now, so we do have a very clear picture of what may be working, what may not be working. So what is missing to make these interactive models better? It's just data, which I think is, of course, an important resource, as you said, or we are missing something much more deeper than that to model interaction?
I think it's mostly data and a little bit of tweaking of the architectures. So we have this learning what to say and when to say it and so on. There's probably lots of variations that are better and faster and so on. But maybe depressingly or maybe optimistically, I think the key challenges in front of us are tweaking of the architectures and broadening the sheer number of concepts that we convey to a model this way through end-to-end learning via data. So, and I think both are, maybe you could argue, not very deep research challenges. They're basically growing data, tweaking models. But I think that's where we are right now. So that's my personal belief, right? I don't know. This is the way I would bet.
Thank you.
Yeah, I wanted to ask about that when you mentioned end-to-end, because I think you use that term a lot in the talk. I was wondering if you think that that's the way to go for maybe for most or all machine learning applications, or if I guess I'm wondering about that, especially because now that there are multiple modalities, there are more and more interactions. But I guess do you still believe that end-to-end is that's what we can do best, and that's what we should aim for?
I think so. I think especially if it comes to applications that are long-standing philosophical idea of artificial intelligence, right? Like a human-like cognition, understanding situations, and being like life-like, human-like in some way. For that, again, it's like the way that I would bet is by saying let's do more end-to-end learning, because a lot of abilities emerge, and they seem to also emerge in some way in living systems. And so there seems to be something very sensible in going about it with end-to-end learning. But that being said, there's a lot of superhuman capabilities and applications and so on that can probably benefit from taking a completely different approach, right? Like becoming superhuman in a very, very, very narrow task of whatever it might be, analyzing a certain kind of data and so on, in which case it is an open playground to develop all kinds of models and so on. But I think for this real AI, the schoolgirl's dream of building intelligence like us and so on, yeah, the way I would bet and the way I'm betting is figuring out how to put end-to-end learning into that approach.
Any other questions? All right, well, thank you very much for the great talk.
Thank you.
Okay. Yeah, so thanks a lot for everyone for being here. So we're going to take a break now until 11:40.
All right, mic 3. Ensuite, micro podium. J'ai mon micro 1 ici. Sweet. Et micro 2.
All right, please, it's time to start. Just get one of your seats, and so we can start. We have two very interesting talks before lunch. And so, yeah. So our first speaker is going to be Serena Vilata. She's a senior researcher. She has been working in artificial intelligence at large, but in particular focusing on computational argumentation, considering both reasoning and computational models of arguments, meaning natural arguments from text, argument meaning. And she's particularly interested in applications to medical, to the legal domain, and so to the political debates as well. So, Serena, it's a pleasure to have you with us. Thank you for coming.
Thanks, Pablo. Thanks for the invitation. So, what I will talk about today is natural language argumentation. So that's the research topic we developed in my team since some years. And my goal is also to explain you how this field evolved over time. And now, of course, I will end with what's the role or the impact of LLMs in this domain. So first of all, just a quick focus on what is argumentation. So argumentation has been proposed since many years. As you see, I put strong references till Aristotle. It's a reasoning framework which aims to justify decisions, okay? When we talk about decision making, when we say we need to take a decision, possible good decisions, but also informed decision. So the goal of argumentation is to use arguments to help humans to take decisions and to justify this decision through arguments, to explain them. And so you can see also a link with this research area, which is explainable AI, which is so popular nowadays. So it is an interdisciplinary topic. We have the artificial intelligence part, which is those which concerns most what I will be presenting. But then, of course, there are contributions in philosophy, in psychology, and in linguistics on this topic. And a number of existing applications. At the beginning, it was mainly applications in medicine, for instance, where we have evidence-based medicine, such that a doctor can take a joint decision based on the arguments, they can deliberate. And also a strong impact in the legal domain, where actually there are argumentative decisions based on court, based on the previous cases. Then with the rise of the web, there has been a number of online debate platforms that have been proposed. Of course, sometimes they are just debate platforms, not argument-based debate platforms. So not all arguments are sound arguments, let's say, with respect to the meaning that I will provide to this word. So just to explain you overall what we mean when we talk about argumentation, we start with what I call the two knowledge bases of, let's say, two agents, okay? We build the arguments from their knowledge bases. We identify what are the attacks between these arguments, so kind of conflict relations between the arguments which are proposed. We could also have positive relations, like the support relation. And then from all that, the goal is to select what are the good arguments, okay? What are the arguments which are well-grounded, well-justified, which are reliable. Of course, I will go more into the detail of what good means, because this is very complex to be defined. And then from that, we want to raise a conclusion. So now I will go more into the task of what is the task of argument mining. Argument mining can be defined as a task to identify the argumentative structure that is underlying in a text, okay? So let's take, for instance, this complex argument structure, this text. What we want to obtain from this text, this unstructured text, is this structured version of the same text, okay? So what we want to identify is what we have here in blue, in the blue square, which is the claim, what we call the claim, or the conclusion of the argument, which is living and studying overseas is an irrepressible experience when it comes to learn standing on your own feet. And then from that, we have different, what we call evidence, premises, which support or attack the other argument components. In this case, we have one evidence, which is the one we learn living without depending on anyone else, is an evidence supporting the claim. And then we could have evidence which actually attack the claim, like one who's living overseas will, of course, struggle with loneliness, living away from family and friends, okay? And then this is attacked at its time, okay? So what we want is to automatically move from the unstructured version to what we call the argument graph. That's what you see there. So argument mining is a task which became important, or better, which has his birth date in 2014, okay, so 20 years ago, 10 years ago, sorry. And the task was to analyze the discourse and apply a certain argumentation theory. There are many, okay. I will present you some of them, but of course it could be much more complex than what I will present you today, and analyze this data. So why 2014? On the one hand, there were many resources which were becoming available on the web, okay, from different sources in the medical domain, the legal domain, but also a lot of user-generated content due to the rise of debate platforms online. And then, of course, we have the advances in computational linguistics, which also led to the growing of the field. So what I show here is the first, the ancient pipeline of argumentation, of argument mining. So what we have is that we start with text, and then we have two main tasks, okay? The first one is to identify argument components, so to identify evidence and claims in the text. And then once these components are identified, what we want is to predict what are the relations linking these argument components. So we want to predict whether it is like a support relation, an attack relation, and then we can go into more fine-grained relations, okay, of course. And the result is the annotated text. So that's what we got at the beginning. So here there is an example. We start with the argumentation theory. We can take what is called abstract argumentation theory. So we have the arguments and just one kind of relations linking the arguments, which is an attack relation. So we define the annotation scheme, of course. We define the three elements that has to be annotated, meaning the claims, the evidence, and the attacks between these argument components. And then we annotate data. For instance, one of the most known data sets in the field is the Wikipedia one, created by IBM, where the argument structure has been annotated. Okay? Then, of course, we applied machine learning methods, in particular in the field supervised machine learning, just to be precise, and of course we evaluate. So let's have just a quick focus on the three main tasks that are, let's say, behind this field. The first task is the argument component detection. So we want to identify what is the text snippet which we can say it is argumentative, okay? Then we will say whether it is a premise or a claim, okay? But first we want to identify the boundaries. This is quite complex. So we have this segmentation task. We start with a text, and then of course we want to identify all these text snippets. In general, the models are sequence labeling models. And what are the challenges? The challenges are still related to genre, okay? So still now, okay? I'm not talking about the ancient age, okay? I'm really talking about now. So the point is really to identify these. It's different if you work on Twitter, if you work on persuasive essays, or if you work on political debates. And we will see some examples later on. Then once you identify the text snippets that are there, that are argumentative, you want to classify them. You want to say whether they are evidence or they are claims. So for this we used mainly supervised text classification methods, which could be feature-based or neural, okay, it depends. And in particular, we are now interested in end-to-end approaches. So most of the approaches are of this kind. So three challenges still. The first one is that positional information could play a role, but only in certain kinds of text, meaning that, for instance, if you analyze clinical trials, you have that the structure of the clinical trials is always quite, let's say, fixed. First you have all the evidence, and then almost at the end you have the claim. Okay? So that helps, but as soon as you move to another domain, which I will be investigating more later on in the talk, like political debates, where that everything changed, okay? The positional information is not really playing a role. Then, of course, you can have fine-grained classes, because, again, as I said, I'm presenting you the task overall, but then, of course, we could have more difficult tasks, which is finding classes like statistics in the evidence, anecdotes, and so on. And then, of course, there is all what is about the structured information and the semantics in terms of knowledge which could be conveyed. Finally, we have, so here we identify the text snippets. To each text snippets we have provided a label, which is a claim or or premise, then we want to move to the relations, okay? Because these arguments, when we discuss the one with the others, I provide some arguments, and then the people I'm discussing with is providing other arguments, which of course could be in support or against my own arguments. So here what we want is to predict what's the relation between two argument components, and of course we want to learn the argument graph structures, because the point is not only to identify the pairs, meaning the two argument components and the relations linking them, but to have the overall view of the whole argumentation graphs. In particular, this makes sense when you have huge graphs like in the political debates that you will see there. So the challenge is, again, the idea is to have, in particular, end-to-end pipeline where we have the argument components, detection, classification, and the relation prediction in one single step. And then, again, the fine-grained relations, because as we said for the components, the same holds for relations. So we want to have these fine-grained relations. And then the notion of support is kind of controversial in argumentation since the beginning, meaning that there are different viewpoints. You could have viewpoints in which the support holds only between evidence and claim, but it cannot hold between different arguments. So it depends on the viewpoint you take. And now, so these are still the tasks, okay? And these are still challenges, okay? It's challenging. We cannot say that this is solved. But now, what's the status of the field in 2024? So this is what are the new topics, the topics which are really attracting a lot of attention. The first one is argumentation quality, of course, because not all the arguments are the same. As I was saying, you can take online debate platforms. There are many arguments which are put forward. Not all of them are sound, not all of them are reliable. Then we have argument retrieval, argument generation, of course. We have these LLMs, so of course we can go towards that. The problem of integrating knowledge is still an issue, okay? Common sense knowledge if you want, but also specific knowledge depending on the topic. And then all what is multimodal, multi-domain, and multilingual argument mining is still really a field which remains quite unexplored. And then, of course, there are all the ethical considerations linked to the fact that argumentation can be used to convince, can be used to persuade, and so on and so forth. So, let's say, my path during this talk will be the following. So first, we will see some examples of argument mining text, and then I will move to how we assess quality of the arguments, and then finally I will conclude on the generation aspects and the main challenges. So what we did in the team, we worked a lot on identify argument structures from clinical trials. So we worked on the PubMed data. So we collected the abstracts of PubMed, and here holds what I said about positional information. So actually the fact of being at the beginning or at the end of the abstracts play a role in the classification of the argument components. So we built a data set because there were no data sets for the medical domain for argument mining. And we actually identified premise and claims and the relation of supports and attacks. So we stay on this standard pipeline. And this is, in a way, the architecture of what we did in this work, where we also classified, to add information to all that, to the arguments, what is the effect of an outcome. So we also labeled these arguments saying, okay, in these arguments, then it is shown that a certain outcome has been increased or decreased, which are all information which are useful for doctors to aid in the decision-making process. And the result of all that is kind of, let's say, an online demo, which you can all test with multiple elements, multiple different elements. Here there is the part concerning pure argument mining, Then there is a medical T5. There are many components in this demo. But just for argumentation mining, the result, this is the thing. You query the online PubMed system. You select what are the articles you want to analyze, and then these articles are, the abstracts of this article are analyzed, the premise and claims are identified, the relations as well, and this is the resulting, the result of the analysis. And then we moved to kind of the usual suspect, because we said, of course, when we talk about, argumentation, in a way, the natural scenario is the political debates, okay? So we say, okay, let's move on. We get kind of good results for the medical domain. We go to the political, we will do even better. Well, no. So the point is that political debates are very difficult, very complex from many points of view. So first of all, the point was to start collecting the data. So we worked on all the transcripts of the political debates in the US for the presidential campaigns. So we collected all of them, as you can see here. So we span from 1960, Nixon-Kennedy, to 2020, Biden-Trump, okay? So we collected all of them, we annotated them. Here you have some statistics about the number of speeches, sentences, and tokens. So this is how the argument components look like in these debates. So here I take Bush-Kerry in 2004. We have that Bush says, we've been effective. So this is the claim, okay, in bold. And then in italics you have the premises. We busted the AQCAN network. This was a proliferator out of Pakistan that was selling secrets to places like North Korea and Libya. And then there is another evidence, which is we convinced Libya to disarm. Okay? So given these two premises, we conclude that we have been effective. And then this is what we have for the three terms. So this gives you the idea of the fact that these debates are really huge, okay? That, which is kind of an issue when we want to address relation prediction, because then the argument component is one step, but then the relations could be between components which are quite far in the debate. So here there is always the same debate going on. And then this is what results in. So we build these argument graphs, which are very complex in terms of number of relations and components. These are the statistics on the data sets in terms of claims, premises, and supports and attacks. And as you can notice, which could be maybe surprising, is that the attacks are really less numerous than the supports. This is because in general, in these debates, the attacks holds only between the arguments proposed by the different candidates, of course, but then all the supports holds between the premise of an argument and the claim. So you get much more of that in the single debate of one candidate. So this is what we put in place. This is a kind of a standard pipeline where we do component detection and classification task, relying on BERT, and then the relation prediction task, relying on the BERT. And here as well, you can find an online demo that you can all test. You can check the data, which is kind of interesting because it's a huge data. You can check what are the topics, for instance, which are mostly discussed by one or the other candidates, and sometimes there are surprising discovery from the data. And then you can check also the fallacies, which is something I will be talking later on. So this is also available. So let's say that we identify the arguments like that, and then we move to argument quality. So argument quality is kind of a mess, okay? And it was a mess so much that this year with some colleagues in argument mining, we said, okay, let's sit, okay? And let's try to make a kind of a survey or a state-of-the-art, because there are different, the issue is tackled from multiple points of view, and it was difficult to have an overall view. So that's the idea. If you take a sentence like this one, in Huckleberry Finn, Twain captured the essence of everyday Midwest American English, then you could have different kind of assessment. If you're an expert in African American literature, you could think this is not in a way a good argument. But if you have no knowledge about that, you can find that this is okay, a kind of a good argument, a reliable argument. So what we did is that we organized the argument quality, let's say, works, approaches proposed in the literature along different pillars to evaluate it. And one of them is the pure notion of quality with respect to what, for instance. So quality with respect to reaching an agreement, quality with respect to establishing a preference or to deliberate. And then we took into account what are the factors which impact quality, and finally, how we can assess, so through reasoning, through generation, through interaction, and so on and so forth. So what we worked on in the team in this context was over three main attributes of quality: cogency, reasonableness, and argumentation rhetoric. So rhetoric is ethos, logos, pathos, as in philosophy. Cogency is really looking into the argument, okay? Looking whether the argument in a way is sound, so it's the relevance and sufficiency as a notion. And reasonableness instead looks at how this argument, what's in a way the position of this argument with respect to the others in the kind of, let's say, the text, the debate, the essay, and so on. To do so, we actually relied on a work on social science, because of course that's difficult to analyze all that, and it's not just a pure computer science work. So we worked on a sociological work about students' persuasive essays, defining how we could assess cogency and reasonableness along different features. So for instance, here you have that a claim is scored 25 if it provides multiple reasons for the claim, and reasons are sound and acceptable and free of irrelevancies. Of course, this is complex, okay, to assess. I'm not saying that this solves everything, but still it's kind of a guide to go all through that. And the same is done for reasonableness, where we take into account on the one side counter-arguments and on the other side what are the rebuttal claims. And this is how we assess it. So what we put in place, this is for argument rhetoric, we annotated the very well-known dataset on student persuasive essays, which was annotated with argument components and relations. We annotated a new layer for the quality facets, those that I was presenting. And this is the kind of architecture we put in place. And what I want to underline in this architecture, which is the originality of this work, is the fact that we rely on graph embeddings for the reasonableness part. And this is very important, okay? Because we cannot look at the argumentation just looking at each argument by its own, because of course the argumentation is how the whole, let's say, in a way, debate and decision-making is takeover in the text. And this was, so we put together on the one side reasonableness and on the other side cogency. These are the results we obtain on that. So when we talk about quality, we could talk also about fallacies. So here we have some examples that we found in what's our datasets on political debates. So we could have appeal to emotion, so which is a kind of one of the most used fallacious arguments. Just as a quick note, fallacious arguments are not false arguments, okay? Are not fake arguments, okay? It could be true, okay? But the way of conveying the information is intended to mislead the audience. That's the point to keep on that. So, for instance, let's take Trump. If you go with what Hillary is saying in the 9th month, you can take the baby and the baby out of the womb of the mother just prior to the birth of the baby. Okay, so all these details just to raise empathy towards the public. And then we have ad hominem attacks, which are precise attacks towards the other candidate, not towards the political arguments of the other candidate. So Typical politician, all talk, no action. Sounds good, doesn't work, never go to happen. And then loaded language. The loaded language is kind of easy feature. So we have, for instance, here, I was so tired of seeing such foolish things happen in our country. And then we have more complex, let's say, ways of identifying fallacious arguments. We have appeal to authority, okay? For instance, here we have McCain saying, if we suffer defeat in Iraq, which General Petraeus predicts we will, okay, if we adopted, and so on and so forth. So the general is saying so on a war topic, so he's reliable, okay, so trust me. Then you have slippery slope. Slippery slope is from a small event, you raise this to a huge conclusion, okay, kind of a general conclusion. So what Nixon said is that what do the Chinese communists want? They don't want just Kemeny and Matsu, they don't want just Formosa, they want the world. Okay? So that's really the way of going on. And then the most difficult kind of fallacy, which is those on causal reasoning. That's very difficult to be identified and so on. So for instance, here we have, the lesson was that the aftermath of World War I, we kind of turned our backs and left them to their own devices, and they brewed up a lot of trouble that quickly became World War II. So that could be correlations, but it's not a causation link. Okay, so that's another example. I would remind Senator Kennedy of the past 50 years. I would ask him to name one Republican president who led this nation into war. There were 3 Democratic presidents who led us into war. I do not mean by that one party is a war party and the other party is a peace party, and that's the conclusion. So what we did is that we take our datasets, we re-annotated with these 6 kinds of fallacies. These are the statistics over that. You can see an hype in 2016 and other hypes in 2000, for instance. And here you have also the fallacy frequency. Here there is the kind of, let's say, the architecture we put in place to address this classification, where argument components and relations actually play a role. And these are the results we obtain to the detection and classification of fallacious arguments in the text. So identifying the text snippets and classifying it. So let's move to the generation part to conclude. First of all, we were working on generating explanations in the medical domain. And given that this is a very sensible scenario, and it was before ChatGPT, I don't want to lie you. We were working more on combining, let's say, arguments extracted from knowledge bases, from medical knowledge bases like HPO, and generating pattern-based explanations. So we have explanations about why a certain diagnosis is a good diagnosis and why the other options that are provided to students, so residents in medicine, are not the good options. And for doing so, we take the general diseases in the HPO. Then we use generation in, I would say, a quite original way, which is to enhance fact-checking systems. So we are not doing fact-checking, okay? That's just to clarify. What we do is that we have taken state-of-the-art fake news classification systems, and we actually generate argument-based summaries, okay, to support then the fact-checking system, okay? And actually, providing these, so retrieving the evidence and structuring the summary through arguments, okay, and not just text, okay, it actually improves the ability of the system in identifying the fake news, okay, and that's a kind of a nice result with respect also to these evidence written by humans, by fact checkers. And then on fallacies, we were saying, okay, very good, we have the fallacious arguments, that's annoying. It would be nice when for instance, a politician is talking, that we are able to say, this is a fallacious argument, look, this is how the non-fallacious argument would look like, okay? So that the people can learn, so that we can enhance critical thinking. So that was the idea. we have taken some fallacies, in particular appeal to fear, loaded language, flag waving, appeal to pity, and appeal to popular opinion. These are the fallacies we took. And then we asked language models to, in a way, reformulate the argument in a non-fallacious way, okay? Sometimes it means just that some words are deleted, okay? Sometimes it's more. Of course, to do so, and then to evaluate, we had to in a way, write ourselves the non-fallacious arguments, and this was done with the help of people in political science, working in political science. And then finally, the counter-argument generation, we also worked on that on hate speech. So you have a hateful message. It's good to write counter-arguments to fight the hateful message, okay? And then now we have also an additional issue, which are these with these guardrails on some models. So what we tested is that we tested Mistral with guardrails, without guardrails, over the generation of counter speeches, with targeting either the conclusion of the hateful message, either the premise of the hateful message, or what we defined as the weakest premise of the hateful message, okay? And we addressed both a human and an automatic evaluation, showing that, at the end, with guardrails is less impactful, okay? It's less useful, okay, in a way. So it's more protected in a way, but then less useful. So what are the open challenges, just to really to conclude? So language models are used, as I showed you some examples in my team, but are used, of course, in the community. When we ask them, if you want a state-of-the-art, a survey on the topic, Chen and colleagues in 2023 did one which is quite good, which really provides, of course, in 2023, so it's not updated to the latest results. When they have to identify claims or stance detection, that's doing pretty good. But then going into more complex tasks like the quality and so on, still there are still some issues, and it depends a lot on the application scenario. So when we talk about fallacies, when we talk about political debates, that's more difficult. When we talk about medicine, it's working pretty well, for instance. That's what we have observed in the team. And then, of course, there are many points to be raised. I don't want to lie here. So why these fallacies? Okay, because are the easiest in a way, because these are those mostly based on sentiment, on the emotions, and so on. So it's easier to move from a fallacious argument to a non-fallacious one. But then, as soon as we want to move to causal reasoning, to inferences in this kind of applications, this is getting more and more difficult. And we very rarely touch upon topics like subjectivity, the cultural differences, because the way of argumenting is not the same, okay? And so that's something which should be taken into account. And then what we have is that at the beginning, with argument mining, this is really my last slide, when argument mining was proposed, it was said, okay, we extract the argument structures from the text in such a way that we can reason upon them. Well, this never happened, okay? 10 years after, we extract the arguments, but then there is something missing between these and really make reasoning over all that. So this is about the dynamics of the argumentation, the cultural diversity, multilinguality, and so on and so forth. So that's really something which the community has to tackle and to face right now. And thanks a lot for your attention.
Thank you, Serena, for this great talk. So we have time for a couple of questions. So please, yeah, go ahead.
Hi, thanks very much for the talk. I really enjoyed it.
Thanks.
I wonder if either your group or other groups have considered using this framework to predict dependent variables. So an example would be, can you use your framework to predict the success of a debate?
That's a very good point. And actually, so there are not really works on that, not yet, but that could be the end of what I'm saying here, in a way. Because the overall goal of our argumentation at a certain point is to decide what are the accepted arguments, the winning arguments in a debate, okay, through what we call the argumentation semantics, which takes into account multiple notions on the content of each argument, but also on the whole relations of the arguments in the graph, okay? And this is still a bit missing because, in a way, either we look at the graphs or we look at the semantics, but still making them together is definitely one challenge, and there are many people working on that, but not still results on that.
I see. I guess I'm interested whether you can use the quality and the quantity of good arguments, for instance, in a debate to determine the success or outcome of a debate. I mean, given that you have data to, of these presidential debates or any other debating contest, it might be possible to train a model and figure out what kind of features that will be informative about the outcome based on the quality and quantity of the arguments.
Definitely, this is definitely a good idea. And also, the one other point which could be important is to look at the source of the argument, meaning that that's also another dimension which is tangent but important, because we cannot just take an argument by its own as it is. That's
Great. Thanks very much.
Thanks.
Yes, thank you for the talk. So I just had a question. At the moment, we are struggling to try to assess the capabilities of LLMs, to produce texts which have a narrative coherence, which have an argumentative also coherence. So do you think this kind of models can be used as well in trying to evaluate, the capabilities of text generative tools, and try to give a score of argumentative quality on the generated text?
Yeah, that's a very good point. So we try to do so, but still the results are not that satisfying. So what we tried to do at the beginning was to use LLMs to generate synthetic data, okay, to enlarge our data sets, because all the data sets that I presented, in particular the one on political debates, it's huge. It took many months to be created in order to validate, assess, and so on. So the generated arguments are very good in certain domains, again. So for instance, they're I would say, very good also with respect to what the doctor said in medicine, okay? Whilst, for instance, in the legal scenario, they are really reduced quality, and for what concerns certain topics which concerns political debates, are not that good. But definitely, that's the idea. The point is, let's say, how to use these LLMs to evaluate really the argumentative part, not just the dialogue, not just the fact how good they are in producing each single natural language argument, but really in following argumentation, which should be ideally sound and consistent, and so on and so forth. So yeah, that's definitely a topic.
Thank you.
Thank you for the nice talk. I'd like to go back to the generation of the counter arguments, your EMNLP 2024 papers. Can you expand how the automatic evaluation is done? Yeah. What are these metrics?
Yeah, so that was very, very complex. So we have the repetition rate, which is one of the features. So how much there were repetitions. SAF is a matrix proposed by OpenAI to, in a way, to assess how harmful is a text, okay? And RGJ is another matrix looking. It's based on a BERT model to assess how good is the counter argumentation, really in terms of rebutting and undercutting in terms of these relations. But then, what we actually we thought it was very, very important is that just a pure automatic evaluation was not, in a way, that meaningful, okay? because for most of these topics, you really need an evaluation from humans. So that's why we had the chance to work with ONGs to do so, and so they were involved in in establishing how to assess the counter arguments. So the fact that we need to look at if it is suitable, if it is informative, how good is the cogency, and so on and so forth. And they also employ, in a way, their knowledge about the topic. Okay, because this is also how good a counter argumentation is with respect to racism or sexism is different. So that was because again, there is a part of this evaluation which could be in a way automatically assessed, or it could be judged as objective, but then there is a part in the counter-argumentation which is subjective. Yeah.
Any other questions? Can I have a last short question? So how sensitive are the results on the type of language model they're using? If you change the language model, how much change? Have you tried this different?
For this work in particular, not much. Not much on this work, and also on the others, as you might see, yes, there are some differences, but not really astonishing. Okay. Yeah.
Thank you. Any other questions? No. If not, we thank again Serena.
Thanks.
All right, our next speaker is Jimmy Lin. His research, let's wait a second, let's go, just to be sure that's on track. So his work basically goes around the use of artificial intelligence tools in many applications, in particular in information retrieval, natural language processing at large, databases with focus on large-scale distributed algorithms, and infrastructure for data analytics. It's coming.
Of course, this is Murphy's Law, right? My computer just decided to reboot right now.
Oh, okay, yeah. That's fine.
So in these cases, I guess I have to do stand-up and tell you funny jokes while my system reboots, right? Anybody want to prompt ChatGPT to say, tell me a funny joke about professors? Yeah. Okay. Yeah.
All right.
Just to show I was not lying, the computer restarted because of a problem, and you can see all the things that I'm working on right now. Oh, okay. All right, bear with me. Okay, so let's get started. Awesome.
All right, so Jim is from Waterloo. It's a great pleasure to have you with us.
Yeah. Okay, great. To compound problems, I also realize that this is my least favorite talk slot because I am the only person that's standing between you and lunch. So I hope you're not hungry. But let's get right into it. So I like to start at the top. All right, what's the problem we're trying to solve? And by we, I mean myself and my group of graduate students. All right, so the problem I say we tackle is how to connect users with relevant information. All right, and by that I mean, of course, search, traditional information retrieval, but also mean things like question answering, summarization, recommendation. And who do you want to do it for? Well, we falls under this rubric of information access. We want to do it on text, on images, on video, and we want to do it for everybody, everyday searchers to domain experts. Right, so that's a good starting point, but you're probably asking, who cares? Now, my answer to that is, well, information access is a fundamental human right. All right, so if you read the UN Charter on Declaration on Human Rights in Article 19, that says everyone has a right to freedom of opinion and expression, which includes the right to seek, receive, and impart information and ideas through any media, regardless of frontiers. So it's a pretty lofty goal that we're trying to aim for. Which brings us to, of course, this workshop that we're all at, right? And so it's a workshop on NLP and the era of generative AI, cognitive science, and societal transformation, with the focus on societal transformation today, right? So our esteemed organizers challenged us with this, right? To explore the transformative potential of language technologies and their implications for society. So I thought about this for a bit and was like, you know, this is actually what they mean. All right? I feel like this a lot of the time, and I'm sure you do too. I tweeted this out over a year ago. I think it's still relevant today. With so much noise on ChatGPT, LLMs, and we're all gonna die, my students have been asking me, you know, what does all this have to do with NLP and IR? Should we just all quit grad school and become prompt engineers? There's quite a bit of sort of existential angst, right? And I feel that all the time. It's nicely captured through this. Right? So the message I want to deliver has 3 parts. Here's a TLDR. Number 1 is systems make us smarter over time. Number 2, LLMs enable us to actually execute and realize visions we've had for a long time. And I'll end on an optimistic note. I'm really excited about the future. All right? And the rest of the talk is just an elaboration on these 3 points. Ultimately, I want to address this question of where are we going? And to address this question, I'm reminded and guided by 2 separate quotes. The first is by Carl Sagan, who says, you know, you have to know the past to understand the present. And this other quote by Peter Drucker, who says, well, you know, the best way to predict the future is to actually just go and invent it. So let's do that. Now, I want to structure it down into 2 questions I want to answer. So the first one is, where are we now? And how do we get here? And the second is, how do things work right now? Because that sets us up to understand what's going to happen in the future. Right. So my first assertion is that information access systems are nearly as old as civilization itself. So this is what I mean. Let me take you back to what I believe is the first information access problem. This is a clay tablet in cuneiform from ancient Sumeria, circa 700 BCE. And it's basically an accounting record. It says Jack owes John 2 sheep or something like that. They record it, they put it in the granary, and it's an information retrieval problem. How much do I owe? How many sheep do I owe? They pull it back. The first information retrieval problem. Moving forward a bit, we had books. We finally developed books in the medieval period. Books were chained to the shelves. Fast forward another few hundred years, we put them in monumental architecture. So this is the long room in Trinity College, Dublin. Those of you that are Star Wars fans might recognize this. This is the inspiration behind the Jedi archives. So fast forward another couple hundred years, we arrive at the modern library. And then there was this really weird period in time. Most of you probably don't remember this, but information was delivered to us on CD-ROMs that we put in slots on our disk, and we booted up and got stuff like this, Microsoft Encarta from Windows 95. And this shortly gave way to Google and the Tenbu links that we're all familiar with. And then finally, Bing search. So I'm using this as a representative of the new way of interacting with information via a chat-like interface, even though this screenshot itself is over a year old. All right, so this answers the question of, where are we and how do we get here? I'm going to turn my attention to the next question of, how things work now. So let's go back to this era. So about a couple decades ago. And at that time, this is fundamentally what we're trying to build. This black box. It's actually gray, but black box sounds more conventional. So on the one end, we have a lot of documents. On the other end, we have a query that comes in, and it goes into this black box, and at the bottom, we get some results, and they're wonderful, and we move on. Right, so how do we build this black box? Well, as it turns out, we've known how to do this for about 50 years. So Jeremy Sultan and his colleagues wrote this paper in 1975 called A Vector Space Model for Automatic Indexing. And if you actually go back and read it, it's pretty cool. A lot of the terminology it talks about is pretty modern. It talks about a vector space representing documents. It talks about representing each document with a t-dimensional vector that's weighted. And it talks about using inner products to compute similarity. Like, wow, that's remarkably modern. And that was 50 years ago. All right, so this black box, how do we build it? It's something like a vector space model. And so let me peel the covers a bit and go into the next level of detail. So what's happening is you have documents that come in, you run them through a term weighting function, you get back a bunch of term vectors. So here's an example, a snippet of text about the Manhattan Project. You tokenize it, you weight it, you get a vector that looks something like this. Right, you compile a bunch of these vectors, you throw it in an inverted index, and when the queries come in on the other side, well, they're just what we call today a multi-hot vector. You perform top K retrieval, which is just computing inner products, and lo and behold, you got your results. All right, so the TLDR is research and information retrieval from the 70s to the 90s. I would summarize, there's just lots of arguments on how to assign those term weights. So today, we've converged on something that's known as BM25. The formula's up there, but it's not very important. Just realize it's a combination of term frequencies, document frequencies, things like that. Statistics you compute over documents. All right, so at this point, I know your reaction. This is really, really boring stuff, right? Because this is literally so last millennium. What's cool today? Well, this is cool today. And what's behind it? Of course, large language models. You shove in a natural language query, and you get out an amazing answer. But of course, we know this alone doesn't do it. You need to rely on a retrieval model that the large language model talks to and gets results from. And ultimately, it's doing some type of retrieval from a bunch of documents. So this is what we know today as retrieval augmented generation, or RAG for short. All right, so let's focus on this bring box a bit. And I will zoom in. I spent a lot of time on these slides, so this is where you're supposed to say, ooh. All right. So that is exactly the gray box that we've been talking about. And here, I'll even color it for you to make it consistent. Right. So what's going on in here? Well, before I talk, well, you know, there are term weights that came in, and you had BM25 document vectors. So you had a passage, and it looks like this. But now all we've done is simply taken the same passage and represent it with a dense vector that tries to capture meaning, what we know as an embedding today. But we're basically doing the same thing. Of course, these embeddings now are generated by transformer-based models, but they're vectors nonetheless. So we still get these vectors, we shove them into an inverted index. We apply the encoder, the transformer-based encoder in this case, on the document end, and we still perform top K retrieval. And this is a big advance. This is what we call today vector search. So the TLDR here is we've taken the retrieval problem and kind of did a fake and reformulated into the problem of computing dot products on vector representations and doing it really fast. to fulfill the top K retrieval requirement, right? But there's one more trick in the book, and that's this notion of re-ranking. So once you get top K retrieval, you can take the results, shuffle them around, and bring the relevant information up to the top through a re-ranker. And guess what? This is typically done using some transformer model as well. So this is basically how it works today. And I'm gonna wow you with some more animation. I'm just rearranging the boxes. I'm gonna put a brewing box around it and zoom in back to the big picture of retrieval augmented generation with the LLM running on top of a retrieval model. Okay. So now when my students come in, express this to me, I say, no, this is great. Retrieval augmentation just means that your job is more important. We work on retrieval. We work on the foundation. And we all certainly know of garbage in, garbage out. So if retrieval isn't good, you're going to get garbage out on the other end. Right? So LLMs don't make us irrelevant. They make us that much more important. All right. So the takeaway here is that systems make us smarter over time. Back to this original question of what is it that I actually do? So I say I connect users with relevant information, but that's kind of a lie. It's a lie of omission because it didn't actually answer the question of, well, why are we actually doing that? And so after thinking about it, this is the answer I came up with, and this is credit to my colleague Justin Zobel, who was the first to articulate this. Where we're building systems to connect users with relevant information to aid in cognition. That sounds fancy, but cognition, it's the mental action or process of acquiring knowledge and understanding. It's exactly what we're doing. Right? So I would argue that information access systems are cognition aids. And this is where we're going, in my opinion. Let me drill down into the next level of detail. So I made a big deal about this gray box and basically how we've, as a community, as an IR community, spent several decades building it. But let me zoom out a bit, right? So you get great results at the end, but this is a smaller part of a broader ecosystem. Let me give you some examples. So for example, where do these queries come from? Well, at some point in time, I had like a need, I had an information need, right? I gotta translate my cognitive state into keywords. And surely, I don't get what I want from the first try. There has to be some interaction. I read the results, I make some sense of it. I'm doing this in the context of accomplishing some task that can be broken down into a tree-like structure, right? Planning a vacation breaks down into booking the transportation, booking the lodgings, and figuring out things to do that are spread over time. And so there's a lot of information synthesis going on. And all of this happens iteratively. That's the broader information access cycle. And as IR researcher, and then finally, of course, you get to the result. But as IR researchers, for most of the past several decades, we've been focused on building that box. Why? It's not because we didn't understand or cared about the broader picture. It's because we couldn't do anything about it. That box was the only thing that we could make meaningful progress on. But that's not true anymore. Large language models enable this broader vision of cognition aids that allows us to work on the entire problem. This is the manifestation of that. All right, so let me walk you through a few examples of what I mean. Right, so before this era, you had to come up with query terms. You had a question, you had to peck out a few keywords, and then the keyword terms weren't quite right. You had to add terms, you have to remove terms. You don't have to do that anymore. It's replaced with LLMs gives you natural language interactions. Before, you had to issue multiple queries, get multiple results, and manually synthesize all the results together, right? This is known as, I have too many browser tabs open. Yes? With LLMs, it starts to do some of that job for you, semi-automated synthesis of information. And then, with respect to task tracking, before I had to mentally go through all the steps. First I got to do this, then I got to do that. But with LLMs, it allows me to do sub-task tracking, which is pretty cool. Right? So where are we going? Information access systems make us smarter, and LLMs are helping us accelerate this process, as manifested in this new type of search interface. But the next point I want to make is that really, none of this is fundamentally new. So I went back to the literature and dug up some old papers. So here's one, generating natural language summaries from multiple online sources. That's that. This paper was written in 1998. This is a giveaway, it's from 2005, right? But that's nearly 20 years ago. If you zoom in, what was it talking about from the document understanding conferences? We want to synthesize from a set of 20 to 50 documents a brief, well-organized, fluent answer to an information need that could not be met by just stating a name, date, quantity, etc. Wow, that sounds awfully close to what we're trying to do today. And this entire notion of interacting with information through a chatbot, that's simply a reference interview. Most of you probably don't remember this, but there was a time when you were not allowed to use information retrieval systems. Only librarians could. And you actually had to go to a special place in the library called a reference desk, talk to a person that walked you through the task and actually did the searches on your behalf. We're just automating that today, right? And so information access systems over time are making us smarter, and LLMs are accelerating the process. And how are they doing it? By giving us tools we've never had before to realize these dreams that we've actually had for a decade. The roadmap of what we're executing on has been laid out for decades. But there's something standing in our way, and I'll take a slight detour to talk about it. And that, I believe, is evaluation. So this is one of the famous quotes, favorite quotes of information retrieval researchers. If you cannot measure it, you cannot improve it. This was uttered by William Thomson, also known as Lord Kelvin. And so evaluation is the unsung hero that drives progress in information retrieval and natural language processing. Things that we talk about today, precision, recall, F-measure, NDCG, right? These were painstakingly developed and vetted over the course of many decades. And that's what drives progress. As early as the 60s, information retrieval researchers were looking at evaluation from a rigorous basis, and it continues today. So the text retrieval conferences have been running since the 1990s. So 2024 is the 33rd edition, and I've been involved in this effort since the late 90s. This year, our research group and our collaborators are organizing a track and evaluation based on RAG at Trek 2024. So what's the fundamental problem that we're trying to solve? It goes something like this. So today, we want our search engines to answer complex questions like this. And you show this to a RAG system, and it gives you a pretty fluent paragraph that looks like this. Then you give it to another RAG system, and it gives you something like this. And you're like, well, which one is better? That's the problem that we're tackling. And I believe that this is the bottleneck that's holding up progress, our inability to effectively and quickly evaluate RAG answers. And this is the problem I'm focused on right now. And I'll leave this as a teaser because Trek will unveil its results in a couple months. All right. As they say, back to regularly scheduled programming, back to the focus of this workshop, right? So I don't think this is an accurate picture. I want to share a much more uplifting message, right? Systems make us smarter over time, and LLMs enable us to realize past visions, visions we've had for decades, right? Information access systems are cognition aids, and they're going to get better, and I think this is where we're going. But there might be a speed bump along the way, right? So is it possible that machines are going to take over? Not in a robots are going to kill us all type sense, but in the following sense. So we begin from information artifacts, clay tablets, books, CD-ROMs, now digital information. We go through some amount of manual effort to arrive at the process of cognition, figuring out what it is that we wanted to learn and know. Along the way, the systems help us more and more. So system assistance increases. It's going to make us more efficient. Now, the important question is, what's going to happen next? Well, one possibility, if you've seen Wall-E, we're all going to get fat and lazy. But I don't think that's what's going to happen. I think we're just going to work on harder problems. Okay? So what's exciting to me is that it's really not about AI. To me, it's really about intelligence augmentation. It's about assisting and augmenting, not replacing. And this is the third part of my message. All right, LLMs are going to make us smarter over time. They enable us to build these more powerful cognition aids. And I'm really excited about the future because there's so much left to do. So, don't worry. Keep calm and carry on. All right, that's all I have. Happy to take any questions.
Thank you for this fantastic talk and for being so optimistic, which I think is very important. Yeah, so we have time for questions. Yeah, please, Carter.
Hello. Remember, lunch is after, so.
Thank you very much for this great presentation. I have a lot of questions, but I'm going to stay with one. I'm actually working on information retrieval, modern information retrieval, doing a PhD on it. My question is about evaluation. So I'm seeing a lot of papers reporting a metrics, and the most popular one is the NDCG top 10, especially on dataset like beer. So my question is, do you think is it fair to use NDCG top 10 on some kind of dataset like beer? Because beer, it has some dataset who has like track COVID has about 50 query, and Quero got 10,000 queries. And then I will take the mean of NDCG of all the dataset. And some other datasets I got like 4 million documents, and other got 8,000. So how to make it fair?
So the general question is about evaluation, what to do. And my answer is, well, you know, how much time do you have and how much time do I have? So yes, I'll tell you what the community is doing, right? They're taking beer, they're running it, they're reporting the number goes up, yay. That's not what we should be doing. We should be taking a much more principled and measured look on what the metrics are actually measuring. And in order for that to be accurately reflected, we have to know that, like, you know, what the user wants, and sometimes we forget that. So at a high level principle, it all comes back to what is it you're trying to measure. And I'm happy to have this conversation in a lot more detail offline. Yeah.
Very much. Hi, thank you for the great talk. I just wanted to get maybe your view on something. So you talked about how LLMs have replaced or automated or made more efficient certain tools which are required in the entire pipeline, be it like query formulation or the retrieval or re-ranking and so on.
Yep.
In the future, do you see all that converging all into one where we don't need these separate components anymore? There's one giant, like a monolithic system you put in, everything happens internally, puts out, or do you still see this as like different components which will keep on getting optimized through LLMs and future progress?
Let's see. I don't know, because if I did, I'd be running my own startup, inventing the future, and trying to make a lot of money off of it also, right? But no, I think both possibilities may turn out to be the case. So the only comment I will offer is that this chat interface of one turn, one turn, one turn, one turn is a good start, but I don't think it's literally where we'll end up, because there are some things that are not easily conveyed through a chat-like interface. So whether or not it's explicit information organization, explicit hierarchies that get created, explicit query formulation, I don't know, but I think those would be very interesting things to explore.
Thank you so much.
Yeah.
Hello. Hi. Thank you for the excellent talk and very nice animations. So my question is about personalized search. So far, a lot of search systems are designed around kind of general purpose search. There is a little bit of personalization in some of them at Google, for example, but those are very rudimentary. So personalized search is something, you know, tailored for a specific user, memorizes what like their previous search terms are, their preferences. So do you think this is going to be an interesting area of research coming up? Do you think that people should, you know, focus on this area, or should just wait for LLMs to get good enough to let them handle it? And do you think that the current evaluation approaches would handle personalization well?
Okay. So the questions about personalization, the answer is yes, absolutely. Well, it's going to be important and we're going to need it, right? So I have a whole nother talk, as I'm sure many of you have, on agents, right? And so what's an agent? Well, agent, one form of it is a personalized avatar that represents my needs. And so of course it's got to be personalized. Now, with respect to technique, whether we're going to do in-context learning by taking my personal history and stuffing in the prompt, am I going to fine-tune it on my own email? I don't know. Once again, those are all reasonable approaches, and there's plenty of exploration along those lines. Yeah.
Awesome. Thank you. Thank you so much.
Yeah.
Thank you for the talk. I wanted to push a bit on this idea of information augmented cognition and around query generation and where our questions come from. I guess what I'm thinking about is, like, as researchers, often the most interesting questions are the ones that we stumble upon through the process of synthesis and so on that we didn't know we had.
Yep.
And so if we are to have this loop where the synthesis happens for us, will we still be able to, is there still a way that we can conceive of that will allow us to generate these questions we didn't yet know we had?
Oh yeah, that's an interesting observation. In fact, this has been studied in the information science literature. This is called the perfect query paradox, in the sense that, well, you can't exactly specify what you're looking for unless you found it, and if you found it, you wouldn't need to specify it anyway. So it is all part of that process. I think the iteration now going to be aided by LLMs is a very important part of it. But I also like to point out that eventually, hey, we may have telepathic retrieval interfaces. We just hold the thing up to our brains and, you know, whatever our thought comes out to be. I mean, this is not far-fetched in terms of BCI translating directly our mental states into what the LLM can recognize as a information need. Right? This might be science fiction today, but maybe not so much tomorrow. Does that help?
Yeah. I think it's the part that I'm wondering is how important is the information synthesis step to query generation, and if we automate that process, are we removing that?
I think that's sort of the final part of my slide, though, right? I mean, these systems are going to handle more and more things, but that doesn't mean that like we're just going to say, okay, you do everything and I'm going to be fat and lazy now, right? We're going to find more interesting things to do, more complex information synthesis tasks to work on. And so from that perspective, I'm not worried about these systems ultimately making us dumb. Yeah.
Yes, Steve.
Thanks, Jimmy. That was an inspiring talk. Thanks for that. See, this is a great vision. I really appreciate sharing that vision with us. So so far, like information search systems and information access systems, they are enabling us to search for information that people created, and like what you said. But now we are at this stage where, because of this augmentation, now our power has increased so much that we can create information at a much larger scale.
Yeah.
And also the things like these models, they know what are catchy, so that these opinions come on the top in some sense. Like they're also doing that, what is interesting for humans, and in some sense reverse engineer also your search information system, that these are the things that we want to. Yeah. So such systems are also places where you can spread a lot of harm. And so have you been thinking about what's the role of this side of things, like safety or misinformation in this vision?
Yeah, that's a great point, and it's something I think about a fair bit. As you pointed out, the assumption behind information retrieval is you're accessing already stored information, right? Information that somebody has saw fit to put on the internet, for example. But that's not so today. Today, you can synthesize as much data and as much information that you want, and if it all enters part of the ecosystem, including misinformation, including disinformation, and other malicious actors doing their thing, what's going to happen? It's a very important problem. I think about it a lot, but I don't have any good solutions yet.
François.
Yes, thank you for this great talk and for the optimistic stance. Maybe I had a follow-up questions, because I mean we know that systems, as we observe them, are not making us better in some way, or I mean as a community or as a society. And maybe one of the reasons is what you mentioned, is that information that is available on the internet is a lot of it is trash. And in fact, something that you haven't mentioned, that a lot of the energy of people designing information retrieval system is to remove this trash, to remove all the bad links and all the bad data that's come up. So my question would be, how can these new models that we have now help us get rid of this trash and make our internet better?
Wow, I'm getting a lot of tough questions. This is what happens if you give a short talk and invite the audience to participate. No, that's a very important question, and the answer is I don't know. Here's I will throw up my hands and say there's been a lot of work on it. It's an important problem, and we continue to try the best we can. But I think the thing I'll end with is that these things are not new problems. When I approach a situation, I like to sort of think about, like, what's changed, right? Misinformation, spam, garbage has been with us for decades, right? So Google got invented the first day, and the next day search engine optimizations got invented with people copying and creating link farms and everything, right? And so I'm really wondering how much worse, Gen AI is going to accelerate the creation of garbage, right? But I don't think it's a fundamentally new problem. And that fact kind of gives me hope on the future, and that's why I remain positive about this.
So yeah, we take 2 short questions, and please.
Or we can eat.
It's up to you.
A quick one. Thanks a lot for the amazing talk. So my question is also about this garbage, little bit hypothetical. I think we human beings are in this trouble now, information overload.
Yes.
So many information overwhelming us.
Yeah.
Do we need to learn from the machines, like how to make the right query and not to overburden us?
I think technological solutions are one direction, right? But I don't think information overload is a new problem. I mean, information overload is, at the end of World War II, the reason why information retrieval as a field developed. And you can trace through various newspaper articles over the years about the proliferation of garbage. So yes, Gen AI accelerates it, but I don't think it's a fundamentally new problem that we're coping with.
Thank you.
Yeah. All
right. Hi, thanks for a great talk with great animations indeed. I have a follow-up questions to the previous questions actually. One type of, I don't know whether it's garbage or not, but one type of content that is increasingly present on the internet, which is basically the basis, like the source from which the retrieval is done, is generated by models. And we already know that for some languages, the proportion of content that was generated by models on the internet are in the 20, 30, 40%, which is huge. So I like your very positive vision about the future, but isn't that a very big problem? I'm not necessarily speaking about model collapse, but still, when you do retrieval using models within a mass of content, a lot of which was generated by models, you can drift. I mean, the way valuable information is created by humans, does not keep the same importance as before, and all of this can result in really big problems, I think. What are your thoughts?
I think the answer is yes, you're absolutely right. And no, I don't know what to do about it, but as a good way of ending the session, I'll point to the Peter Drucker quote, right? Let's invent the future together and figure out how to solve this problem, because I believe we can make some headway on it.
Maybe lunch.
Yeah.
Okay, let's thank again Jimmy for this. So I would like you to try to go back by 2, so we have a bit less than an hour for lunch, so it should be doable. And remember that we have a very nice session this afternoon, so yep, looking forward to see you.
Very positive. Oh, thank you.
Yeah, very good.
Oh, thank you. Okay, was this better or? Okay, all right.
Et Mike 3, hello. Mike 2, hello. Et Mike 1, hey. Et finalement, micro-podium, test mic online.
Okay, so please come to the room. So we are going to start the last session of the workshop. So thank you for everybody for staying and after this full 3 days packed with presentation and discussion. And so we are going to end with a session quite diverse, so we call it application domain, doesn't mean much, but it's a session with 3 speakers, and we're going to start with Saif Mohammed, who is from the National Research Council Canada, Toronto, and he works in natural language processing, more specifically lexical modeling, sentiment analysis, and the talk today will be more on affective computing. And please, you have the floor.
Thank you so much. Thank you all for sticking by and coming to this final session. But really, what a good workshop this has been. Such wonderful talks and wonderful questions and lots of great one-on-one interaction. So big thank you to the organizers, really, Frederick, Pablo, and Jackie. Thank you. All right. We just heard the term affective computing, but there are a few different words that are swirling around there. And so I wanted to, being in the NLP world, we have heard of things like sentiment and sentiment analysis, and maybe you've heard of emotions work in NLP as well. But what is this affective science? And actually, affective science is not affective computing. That's different. But what I'm going to do, since it's late in this session as well, is I'm going to tell you a story about affective science, and it's going to have characters, and some of them are non-human animal characters. That's really big with my 8-year-old daughter. Stories need to have animals, but we'll see how that carries over here. All right. So at first I had this title, NLP for affective science. What are the big questions, and how do we get there? But then I thought something like this, it might be even more informative, that it's NLP for affective science, a window into emotions through language and computation, right? But emotions are a window into so many other things, like the mind, body, health, and behavior. So we're going to get into all of that as well. So let's start with the basic terms. What are affect and what are emotions? And I like to use Nemo as my mascot for emotions, because even though all of us are intimately familiar with emotions, whenever we try to get a handle on it, like try to define it or try to figure out where does this emotion end, where does that emotion begin, and things like that. Or even when you ask psychologists, no two psychologists agree with each other on what is the definition of some of these emotions. I thought a slippery character like Nemo might be a good mascot for that, right? To start with, let's think of it this way. Affect is the basic sense of feeling, and we'll talk more about that. And emotions are things like joy, sadness, fear, anger, etc. So we have a sense of that, right? To get into more details, let's look at the story of how some of these psychological models of emotions have developed over the years, because giving us some sort of context like that helps us understand and remember things better, right? So people have been thinking about emotions for thousands of years, but I'll go back to Charles Darwin, 1860s or so. I think he had his Origin of Species. But 10 years after that, he published this other book, The Expression of Emotions in Man and Animals. And at first I was like, why is Darwin interested in emotions? And it's quite obvious if you think about it. It's because when he was working on The Origin of Species, he was trying to find out all kinds of evidence that ties animals to humans, and to say that, animals are not something else, humans are animals, and we've all evolved from the same thing. And emotions were a particularly interesting aspect for him, because he was talking about how these various mechanisms of emotions in animals and humans are very similar. And so this is also where you start to get some of these ideas about universality of emotions. There's something common for not just all the people, but also with animals. But by the time things rolled on to the 1950s, you had cultural anthropologists like Margaret Mead, and the dominant idea there was that these emotions are not super universal, as in we don't all react the same way. Culture plays a big role in how these emotions are developed and how we perceive emotions. But go forward another 10 years, and you had Paul Ekman, renowned psychologist, who at the time was a bit of a Sean Connery-esque like character, right? So he comes out of the woods of Papua New Guinea, and he says, hello world, look, I went everywhere, even here in Papua New Guinea, and I've shown people these 6 different photographs of facial expressions, and wherever I go, everybody is very clear, this is fear, this is anger, this is sadness, this is surprise, and so on, for these 6 emotions. And even in Papua New Guinea, where these people have not encountered people from outside, so it's not like they've learned it, but we're all very clear on recognizing these emotions from photographs, right? And so there must be something fundamental about these 6 emotions, and there must be something very basic about these. And so, let's all work on these sort of things. And this sort of energized the psychology community for a while there. You had all kinds of theories about what is basic emotions. Oh, well, they said, oh, here are 2 other emotions. These are also basic, or here are 10 basic emotions, and things like that. That's where you have, Robert Plutchik's Wheel of Emotions, for example. You may have seen that. But parallel to this idea of basic emotions, there was also another line of work, and this was very interesting. And first, it wasn't even focused necessarily on emotions, done by Charles Osgood and colleagues in the 50s, but then later on by James Russell and his collaborators looking at emotion words specifically. And a lot of this work focused on this sort of factor analysis of words to find the core dimensions of connotative meaning, and all of them were ending up at roughly these same 3 dimensions. So you have valence, which is the pleasure, displeasure, or positive, negative dimension. You have arousal, which is the active, sluggish, or stimulated, bored dimension. And you have dominance, which is the powerful, powerless, strong, weak dimension, right? So when comparing the meanings of any 2 terms, for example, we can look at them across these dimensions, and we can say, for example, that banquet involves more positiveness than funeral, nervous indicates more arousal than lazy, queen indicates more dominance than delicate, and apart from these dimensions being very important in some way, they're also considered independent pheromones. So just because you're high valence doesn't mean you have to be high arousal. But there was still a twist to come in this story, and in the late 90s, you had Lisa Barrett, who was then a graduate student at our own University of Waterloo, where Jimmy Lin is right now. And Lisa is doing really fun experiments. Well, actually, she was replicating some of Paul Ekman's experiments in new different ways, and she was finding that many of these things were not really replicating. And so she went into this sort of thing about, what's going on, why is this not working out the way it is? And right now, she's got 25 years of fantastic work in this space, and in 2017, she came up with this new theory of constructed emotion. And one of the key things that she points out is that there were some ways in which those Paul Ekman experiments were done that if you were not quite appropriate to test this universality, and if you take them away, a lot of this structure falls off. And she postulates that the way we construct emotions from in our brain. These are not physical existing fundamental things like the way Ekman and others have argued. And so important tenets of the basic emotion theory are now, largely discredited. So, it's very clear, the evidence, that you cannot tell by looking at somebody's facial expression whether they're angry or sad or, and various such things. You can tell certain things like valence, like, is there a general sense of, positiveness or negativeness, or is there a general sense of arousal and things like that? But when you talk about specific emotions, there is huge variation person to person. Right? So there's a lot of stress with this theory on variability. All right, so let's put that together a bit. Affect, as I said, is the basic sense of feeling, and it's usually thought of in terms of these 3 dimensions of valence, arousal, and dominance. This affect, one of the other interesting things is also that for many decades now, people have thought that there is a role for these signals that we're getting from inside our body, what they call interoceptive signals, in determining our emotions and affect. And so the dominant idea now is that this affect, this sort of sense of pleasure or displeasure or arousal, is something that is transduced from these interoceptive signals, sensory representations of the interior of our body. Right? And this sort of summarizing is very important, because it's not like our brain can handle all kinds of detailed information about the state of our body, but getting this sort of summary information gives us this sort of evolutionary benefits to act appropriately in different situations. And affect is thought of as a feature of consciousness. It occurs in every moment, regardless of whether you're aware of it or not. Right? In contrast, emotions are constructed by the brain. This is a little bit of a higher level state. There's more cognitive processing involved. It also makes use of this affective and interoceptive signals, but additionally it makes use of certain concepts about the world. Right? So we have a sense of what various emotion concepts are, what anger is, and so on, that we learn from socialization and from the people around us and from culture, and that plays a big part along with predictive coding to finally figure out what is anger in our head. Right? So the brain takes in this sort of continuous dimensional signal of affect and then categorizes it into particular emotions like joy, sadness, fear, and anger. And this is not that different from how it is for color. Color, as we know, is a very continuous signal, but our brain categorizes that and perceives that as categories of green, red, yellow, and so on. All right, so affective science is the interdisciplinary field which is focused on understanding emotions and affect. And one of the reasons this is very exciting, and not just because it impacts our lives in various ways, is also because there is so much we still do not know about the field. So how do affect and emotions work exactly? What are the underlying mechanisms and processes? How do we regulate emotions? How do they impact our mental health, well-being, and behavior? And what agency do we have in managing our emotions, right? One of the nice parts about this constructed emotion thing is it gives back more of the agency to us because we are constructing these emotions in our head. So that's affective science in a whirlwind, but where does language come in, right? So we are NLP people, but language comes in a big way, I think, because language is a powerful way in which we express emotions. So affective science, traditionally interdisciplinary, but traditionally studied in psychology, still asks people various questions about things and uses language to some extent. And language is very interesting also because we can express numerous shades of these emotions, right? And we come up with terms which have fuzzy boundaries, overlapping meanings, all kinds of sociocultural influences on them. And we can be direct, we can be subtle in our emotions, we can be ambiguous, we can be deceptive, we can be creative, and we can be conscious of conveying certain emotions, and sometimes our language betrays our emotions, even though we might not want to put that across, right? So language is a really interesting way to look at emotions. And of course, then you come to the sort of what is NLP for affective science is the computational analysis of emotions through language, right? And this is challenging on the one hand because just see the previous slide, right? So all these tricky ways in which we use language and we ask machines to try and understand those subtleties and sarcasm and creativeness in there. But on the other hand, I would argue that NLP for affective science plays a big role and has certain powerful things at its disposal, right? So unlike some of the work in traditional psychology, we can make use of huge amounts of text to come up with our answers to these questions or shed light into these questions. We can use simple to complex NLP techniques, and as I also already said, language impacts our thought, and so if emotions are constructed emotions, language is playing a big role in how we construct these emotions. And last but not least, this NLP provides this sort of a complementary view to traditional affective science, where they might go and ask people, how are you feeling at various times, and draw conclusions from that. Here we can look at a more ecologically valid data, perhaps, where we are seeing how people behave, what language they use over periods of time, and from that get at these problems. Because it's also well known that people are not good at telling how they feel or how they felt earlier this morning or yesterday or last week. It's an important challenge. So with computational analysis for emotions through language, we inherit a bunch of questions that come from psychology, which is great. So, often I see sometimes we have this new tool and we start to think of our own new questions, but it does make a whole lot of sense to first go and see what are people who are actually studying affective science for a while now. There's a huge, body of literature out there. Look at what are the questions they think are compelling and interesting, and then use language or computational stuff to help with those questions. So we inherit a whole lot of great questions from them directly, but many of these questions also impact other fields like linguistics, right? How do we use language to convey emotions is a question that matters to linguistics as well. Or how does language impact emotions? Or to social science, how do emotions impact social cognition, morality, stereotypes, and behavior? Where is all of that playing a role? And as AI tool builders, for example, sometimes we can think about, what tools can we build to help people, help clinicians, help social scientists, and so on. So that was the sort of overview of the space. And so this talk, I'll just give you a quick outline. We talked about the theories already. I'm going to talk a little bit about word emotion associations because, when I start to work on things, I like to work on simplest things first. Words seemed like a great place to work on when I started in 2010. And I'll talk about recent work, though. And I'll also talk about tracking emotion arcs because this is, tracking the flow of change of emotions over a period of time is especially useful for a lot of these questions. And we'll look at things like emotion dynamics and granularity over there. And finally, I'll end with a brief blurb about ethical considerations. All right, just grab some water. Right, so I've been working in this space for a few years now, and I had the opportunity to create a bunch of these word emotion association lexicons, which are essentially lists of words with associated scores for joy, sadness, fear, or valence, arousal, dominance, and things like that. I mean, the earliest was in 2010. We had the NRC emotion lexicon. In 2018, we added intensity values to the scores. It was just 0, 1 for various emotions. And notably, that was the time I created also the valence, arousal, dominance lexicon, which is especially interesting to study affect and the psychological processes. We also had a word color association lexicon way back, in case somebody's interested in that. But today I want to talk something about much more recent, where I've been sort of fascinated with this idea of anxiety. It is defined as the anticipatory unease about a potential future negative outcome, right? So, and first I want to say how this is a common and beneficial human emotion. Sometimes as NLP people in health space, we go straight to the disorders, but I'm like, no, let's hold on. Anxiety is a, if you look at the stuff, anxiety is there for a reason. It helps us evolutionarily. Even in early stages of humanity, it was important to be afraid of dangerous wild animals, for example, that might come, right? So if you have anxiety about that, it's a good thing. But it can also manifest itself into disorders. And one of the theories about this is that our current environment is so different from what anxiety has slowly evolved to handle over millennia that it is causing this sort of constant extra triggers of anxiety, and too much of anxiety can lead to some of these disorders, right? So a lot of dopamine hacking by social media companies and things like that, and that might be a reason why this is becoming a bigger issue. I also found recently this nice little blurb, and I want to read out this little statement because it brings us back to the humanity of things a bit. Laura Turner writes, "I have some affection for my anxiety. When it does not have me in a swirl, I think of it as a little pet. A black cat who has gotten stuck in my house and who I keep feeding milk, even though I'm not sure what I wanted, even though I'm not sure that I wanted a pet. The cat's language is gentle, pawing, bringing me back to the things that matter: hospitality, service, compassion, kindness. The cat is my teacher." I really like this phrase, this sort of blurb, because it tells us how anxiety impacts us in various ways, and there are good and bad things about this thing, right? All right. So why create a language resources for anxiety? And it's, I wanted to outline quickly what are the various benefits. one of the things is to understand anxiety itself, like what are the underlying mechanisms, how it relates to various other emotions and affect, how it relates to our body, how anxiety changes with age, socioeconomic status, weather, green spaces, etc., and identifying coping mechanisms and things like that. Another aspect is to look at how anxiety manifests in language, how language shapes anxiety, how culture shapes anxiety. There's also this idea, useful aspect of tracking the degree of anxiety towards various targets of interest, like climate change, government policies, biological vectors. What are we anxious about? When are we anxious about them? Things like that. Developing automatic systems to detect anxiety, a very NLP-like task thing if you're interested in that. Studying how anxiety impacts behavior in physical and virtual environments, a social science sort of thing. Studying anxiety in stories, character development, and things like that. Digital humanities people care about this sort of thing, right? So earlier this year, we did some crowdsourcing work, and we annotated about 44,000 English words, commonly used English words, and about 10,000 bigrams, two-word sequences that were marked as interesting in some way. And we annotated them for a degree of anxiety, from a scale of extreme calmness, -3, to maximum anxiety, +3. And so you got some examples over there, and we used all the good quality control methods, like interspersing gold questions and control questions, and only keeping annotations from people who were answering very responsibly. And we show that the reliability is very good. So this is work that has just been accepted. It'll be published at EMNLP. But if you want to know more about it, some of the things we did and showed in the paper were looking at what is the rate at which children acquire anxiety terms as they're growing up, right? And it wasn't super clear from looking at the literature that, there's some known trends for these things. But this lexicon allowed us to explore these kinds of questions. And we find that, for example, in the first 5-year window, children are learning, a lot of words that are learning are calming words and less anxiety-inducing words. But from 5 years on, it's a steep downhill curve for the calmness words. We are essentially learning more and more anxiety-inducing words, kind of thing. Another thing that we did in that paper was looking to see how good can we track anxiety in streams of text. So let's say you have social media data about climate change or vaccines or whatever. Can we track how much anxiety is there in a stream of text in a time series using just the lexicons? And turns out you can do a really, really good job. In yellow is the gold arc for anxiety there, and in green is the arc that you can create just with counting up words from the anxiety lexicon. Of course, if you use different lexicons like valence and arousal, your results drop off quite a bit. So it was actually useful to show that, yes, anxiety lexicon particularly is helpful for tracking anxiety. All right, and that's a really nice segue to get into this third part of my talk, which is about emotion arcs. And emotion arcs, I think, are really cool because they're really quite pervasive. They're very useful, not just in commerce. For example, companies might want to track how are people feeling towards my particular product, how is that changing over time, but also in psychology, because we care about things like, how do people's emotions change over a period of time, how is that related to their well-being and things like that. And it's also useful in stories, because stories have emotional arcs and things like that. And many of you might know Kurt Vonnegut, one of the most notable authors of the 20th century. He has very well-known ideas, and there's a fun YouTube video you should Google and see if you haven't, where he talks about these various shapes of stories and things like Man in Whole and the Cinderella arc, and that different stories can have different shapes and things like that. So way back in 2011, soon after I created the emotion lexicon, we did some work on generating these emotion arcs for various stories and things like that. And this paper really took off, and there's a lot of work in that space since then. However, there is one issue, and this issue is about evaluation. I'll just jump through a bit here. People have been using it in various places, and you can use this lexicon approaches, or you can use machine learning approaches, you can use the latest transformers and things like that. But there hasn't been any or very little work on evaluating the kind of emotion arcs that you get from this. And that's good reason for that, right? So if you want to have gold emotion arcs, you need to annotate huge amounts of data, hundreds of thousands of instances, let's say, and that gives you one arc. You need to have multiple emotion arcs, and you want to evaluate these things. But there was a sense that when you're talking about aggregated tasks like emotion arc tracking, where you're saying, okay, let's take thousands of tweets every day and see how these emotions are changing from day to day, it's a much easier task. You just have to figure out whether the emotions in the next day have there's more anger or less anger. And so you're making use of thousands of pieces of instances, and so you're using a lot of context, and it generally works well. So when people come to NRC for these things, we normally tell them to use the simple methods, and they're usually happy with this. However, as I said, there hasn't been much of an evaluation, and I'm happy to report that last year, my student Daniela did some wonderful work where she makes use of existing emotion annotated data sets to create these sort of non-trivial but random emotional arcs, like what you saw for anxiety over there, and then tested out how good these various methods are at emotion arc tracking for a large number of emotions and also for many languages. So for example, here's an arc from that. This is for valence, and you can see that using standard good English lexicons, you can get correlations of even about 0.95 with the gold. And of course, if you translate the lexicons, or if your lexicons are of poorer quality, these results fall down furthermore. All right, so that was just a quick evaluation of that, but let me get to back to psychology again, right? So, because in psychology, they have been looking at these sort of emotion arcs, at the flow of emotions of individuals over a period of time. And they have this idea of home base and homeostasis, right? So you and I might differ in what our home base is for various affective dimensions. Like Jackie might be a generally cheerful guy. I might be a generally, less cheerful guy. Our home states might be different. But when things happen, something good or bad, our emotional states go up, go down, but we don't stay there. That's not how humans are designed. We come back to our home base. That's the homeostasis aspect of it. But we might differ in how our behavior is in these terms. Jackie might bounce back quickly from a negative thing. For me, it may take a longer time to come back from a negative event, for example, right? So these sort of things are called as emotion dynamics. And in psychology, people have been looking at these sort of things where they ask people again, how do you feel today? How do you feel tomorrow? At various times, you have to enter things like how you feel, and then you can start to get a sense of this sort of thing. But of course, another window into this is obviously through language and through our words. And this idea, I have to give credit to my student, Will Hipson. He's actually a psychology student then, and he got me interested in this space. And we started looking at how can we use, this sort of, the language that people use, let's say in tweets and so on, to create these sort of emotion arcs and capture emotion dynamics from that. And of course, one big advantage of this is that you can now take huge amounts of data and create these emotion arcs. Right? So we did some work on that, first on fictional characters and screenplays, because it's nice to get that data and test out some of these theories. And then we also did some work on tweets and looked at differences between US and Canada in terms of emotional dynamics. And there's some interesting, very interesting systematic differences across countries you can find this way. And it also looked at COVID and the impact of COVID and things like that. And later last year, we had a paper at NLP where we were looking at how these emotion dynamics metrics, this capturing of this mathematical quantization of how your emotions change over time, can be very useful biosocial markers for various mental health conditions. Okay, so far, I talked about, just now I talked about these individual emotion arcs, and we saw this emotion dynamics. I want to talk about one more psychology concept, which I think is super cool. It's called emotional granularity. How many here have heard of emotional granularity? Cool, one. Okay. It's not surprising because I talked to you yesterday and I know that you will know. And I didn't tell you this, so that's great. Okay. So it's a really fun concept. Let's talk about that. But quickly, I just want to also tell you that this one involves pairs of emotion arcs, and that's going to come later. But first, let's look at what is emotional granularity. And we come back to Lisa Barrett, our protagonist in this story. I should say she was awarded the Lifetime Achievement Award by the Association of Psychological Sciences just last month. Very well deserved. And in 2001, she came up with this idea of emotional granularity or emotion differentiation, where she talks about how some people can recognize and identify and describe their feelings very precisely, very systematically, and they can use these terms, emotion terms, in specific context, right? So they can say, they feel angry at certain contexts, and they can say that they are annoyed at certain other contexts. It's very fixed and systematic in that sense, for example. On the other hand, and it's very reliable. On the other hand, there are people who, for example, where this is not the case, and we might use terms in a much more broad way, right, to convey a general sense of I'm feeling bad or I'm feeling low, but we are not very precise with our terminology. And what might also happen in these cases is that we might tend to co-endorse multiple emotions at the same time. Like we might say, I'm elated and I'm content, or I might say I'm angry and I'm annoyed at the same sort of time. And so you're co-endorsing multiple emotions. And of course, this is not binary. There's a spectrum over here. We're all on that spectrum somewhere. And emotional granularity is defined as this ability to experience and categorize emotions in very specific terms, and the degree to which we do not co-endorse multiple emotions at the same time. And why does this matter, you would ask? And it turns out it matters a whole lot, at least if we look at some of the studies that are coming out of psychology since 2001, there have been a bunch of studies that are talking about how emotional granularity impacts mental health, it impacts physical health, and it even impacts behavior. So, and particularly the direction is such, if you are very careful and precise in how you use your emotions and you're using it systematically in different contexts, these people, this cohort has generally expected to have better health outcomes for mental health, physical health, and behavior than groups of people where they might not be using it as systematically, for example. So from depression, anxiety, to cardiovascular health, to school behavior, lashing out at people, maladaptive behaviors in general, the differences in all of these areas are being identified. All right, so again, being an NLP person, I'm like, okay, the traditional approach to do emotional granularity is, again, to ask people, how are you feeling, as I said, but we were interested then that can we figure out the degree of emotional granularity just from the text that you're using, right? So to what extent are you co-endorsing multiple emotions in text, and to what extent, and the thing about using text is that it's not just people don't go around telling I'm happy, I'm sad, I'm angry. We can infer these things from connotations rather than denotations and these associations and from these lexicons therefore that way. And so it seems like a powerful approach, but it was very unclear whether we'll get anything of the same sort or not. And this was a collaboration, I must say, with all these people that you've listed over here, but notably with Kirsten, who was a student of Lisa Barrett a while back and is a renowned, affective science researcher at University of North Carolina herself. So what did we do? We computed emotion arcs for various emotions, and then we sort of formulate this idea of emotional granularity, or we operationalize it as the correlation between pairs of emotion arcs. Because the more your anger and sadness arcs are correlated, it seems that more you're co-endorsing them over a period of time, and more systematically you're co-endorsing them. So the hypothesis was to test whether this is a good measure of emotional granularity in the sense. And of course, and the way we wanted to test this, so we did the experiments, created the emotional granularity scores, and then we looked at language from various groups, from people, and we found that the text by those who have self-disclosed to have certain mental health conditions, such as PTSD, ADHD, etc., depression, they have significantly lower emotional granularity, even using our method, than text by a control group. So this was starting to identify exactly the same sort of patterns that you can get, again, just with the text that people are using. This is also accepted at NLP, so it'll be coming out soon. Okay, 5 minutes, perfect. I'll take the last 5 minutes to talk about ethical considerations in emotion recognition. There was some discussion yesterday in the panel thing here, for example, about disassociated results, what happens if results for one group are worse than others and things like that. But I want to point out that looking at ethics for various tasks involves not just data, not just the final results, but looking at the task from beginning to end, right? And one of the key things for any task is, how are you defining the task? And let's take emotion recognition as an example, because for a lot of us, it might be something like, well, emotion recognition is sort of like inferring the emotions felt by a speaker. Right? And when I'm at NRC, I get a lot of people come to us for various sentiment and analysis things, and what I'm always amazed is at how different people can have different ideas of what emotion recognition can be. Right? So here are some more examples. Instead of that, number one, it could also be inferring emotions of the speaker as perceived by the reader or listener. Now, it's not quite the same, it's different. Or it could be inferring emotions that the speaker is attempting to convey. Or it could be the inferring emotions evoked in the reader, inferring emotions of people mentioned in the text, inferring whether what is described is good for a predetermined target or not. This is again very interesting. Commercial applications, when they come for sentiment analysis, they don't want whether you're using positive language or negative language. They want to know whether this person likes my product or my government policy or not, and that's a different thing. Right? And there can be a whole number of other different tasks as to how you define what a particular emotion recognition or sentiment analysis task can be. But it's important for us to think which task we want to do, how we want to formulate these, because all of these tasks, how we formulate them, come with associated benefits, but also potential harms and ethical considerations, and we should be thinking about that. And for this, I'll circle back to these theories that I talked about earlier. We should be very careful not to give the impression that just because you said this tweet, my LLM-based system can figure out what's going on in your head and what your emotion is there. That can lead to actual bad things like, companies using these systems and selling them to government organizations, for example, to say, oh, we can figure out whether this refugee is genuinely fearful of something or not, and things like that. We don't want machines to be doing that. We are not, as Lisa Barrett and all her work has shown, especially for facial expression, but even for language it applies, you cannot really know what's going on in somebody's head for a given instance. There are systematicities, and we can use that for finding broad trends, but there is a huge amount of person-to-person variation. Right? So the sort of computational analysis of emotion recognition can be a force that helps unlock lots of interesting research and answer lots of questions and help a lot of people, but be careful that it's also a tool for substantial harm. We've seen mass application of emotion recognition technologies on vulnerable populations. We've seen unreliable approaches. It does not matter whether the science is good or not, or whether the system actually works or not. If a company can sell an emotion recognition product to somebody, they will sell it. Right? So what can we do? Right? So our job is to be clear when we build these systems, to talk about what the science is and what is reliable and not reliable, so that we give the right signals to companies, to the people at large, and anybody who's looking into these sort of things. Right? And we also certainly want to avoid perpetuating ideas of physiognomy and things like that. All right, so in 2020, I was thinking a lot about this, and I decided to write up a list of various ethical considerations about emotion recognition, because I thought, as a person who's been working in this field, when somebody comes and asks me, hey, what are the ethical issues about this task that you work on, I don't want to give them an ad hoc answer. I want to say that I did think about this, and I wrote down, and here are my thoughts, and you can look at that, right? And so I was very happy that CL Journal accepted and published that work as well. I talk about 50 different ethical considerations and I group them into these various common phases of system development. And I will also humbly request all of you, because you are fantastic researchers working in really great problems, it'll be great if you could also write down some sort of documents about your own tasks and think about that and talk about what are the ethical considerations involved in this. And it doesn't matter even if you think, oh, there is nothing here or in this particular space. If you're putting your word down and saying that I don't think there is something here, that is useful as well for the future. And I'll end with this quick note that one of the key things with this space is also that, a lot of the work in affective science has been on English. So I was very happy that in 2023, I was part of this group where we did a shared task and created data sets for 14 different languages. And in 2025, next year, we are also, actually the data set is up already right now. If you're interested in a new shared task, which is focused on emotion-based questions, and we have data sets for 35 languages, and with most of them from Africa and Asia. All right, with that, I'll end my talk, and thank you for coming along in this journey of emotions, mind, body, behavior, and language. Hopefully you had fun. Thank you.
Thank you. Thank you very much for your talk. So we have time for a few questions. So please come to the mic and. Yes, Jackie.
Thank you, Seth. It was a great talk. I really enjoyed it. I actually formulated my question, and then you somehow read my mind, and then you already partially answered it, so I'll refine
Ask it again.
so my question had to do with, I guess, if you see a word that's emotion-bearing, it could be of the speaker or of the person being described and so forth. Right. And it seems to me that there are words where it's simultaneously maybe both at the same time, or maybe it's also ties into a stance as well. Like if I can think of adjectives like hysterical or flustered, and they probably correlate with and indicate some emotions or stance of both the speaker and the person being described. And I was wondering, in the lexicons you build, which one you target, or maybe both or something like that.
Right, that's a great question. Thank you for asking that. I think it's very important to think about these different kind of emotion-related tasks from a task perspective. What is the task that I want to do? And then you can build systems, and you can use certain resources and have some algorithms to focus on the particular task of interest, right? From the lexicon's perspective, so in 2009, when this work I did with Peter Turney, my mentor at NRC and a fantastic researcher himself, one of the key interesting things we found was that when I first asked people for what emotions are, give me an emotion score for this word, we used the term evoked. It just seemed like a very emotion-associated term, and we might want to ask that. But for some reason, we also decided to ask in a different way in a later study, soon after that, and this was still in early times, where we asked, instead of evoked, we asked associated. We said, how much is this word associated with anger? And that led to much higher inter-annotator agreement and things like that. And one of the things we think for that is because people are not bringing in their own idiosyncratic thing. Like, for me, this evokes like this, and so on. So associated is a good word, but it ties into your question in the sense that words by themselves can't tell you in this sentence what emotion is for which particular, whether it's for the agent or the reader or the speaker or somebody mentioned in it. But they can tell you that this emotion might be there. And even then, when we created the lexicon, we didn't want people to use the lexicon to determine the emotions of a sentence. That's just a few words. That's not how emotions are conveyed in a sentence. But it's very useful for this sort of aggregate level analysis, where you're using thousands of tweets every day coming in, and then you're tracking whether the emotions go up or not, and that tells us something. But again, there it is, if you simply use the lexicon, it's only telling you association. It's not telling you who is feeling or addressed to whom. But you can put in certain things in there in your algorithm as to how you use it to get the data or you look at certain windows where you try and get at whether this is the speaker's emotion, perceived emotion, or whether they're talking about something, vaccines. So if I take a bunch of vaccine data and look at all the anger words around it, I can sort of get a sense of anger in conversations about vaccines.
I see. So then would you get in that scheme words that are associated with multiple emotions because they're...
Yes,
okay.
and also individual words, maybe in our lexicon, we ask that you get multiple associations with multiple emotions. But if you're looking at anger, and if suddenly from this month to next month, there's a lot of anger, something has happened, there's a lot of anger in tweets about vaccines, there are a lot of words for whom one of the senses is associated with anger, but the other senses are dispersed, so a signal comes up. because of that. That's another way of using these lexicons.
Okay, thank you.
Thank you.
So please.
Thank you, Sai, for the very interesting talk. I am a bit curious about lexicon, emotion, and intergenerational effect. For example, now we have
intergenerational
changes.
Changes, okay.
With regards to the language, like right now we have Gen Z and Gen Alpha. They have their own words, own terms. So have you observed something like that? Just curious.
It's a great question. Some time back, I was interested in this idea that from the lexicon, you can get subword units that might be associated with one emotion or other. And then I wanted to look back in time and see whether that gives words an evolutionary edge when they're trying to fight out with other synonyms to represent a particular meaning. Like, a long time back, people used clearness, but then clarity won out at some point, and now we use clarity. Is there something in the subword unit that helps with this sort of thing? Right? But it's one of the tricky things is we can't get people from 100 years back to get their associations, but you can use certain techniques. I know Yang Su gave a fantastic talk yesterday. You should check out some of their work on looking at how things have changed over periods of time. I have particularly not looked beyond that.
Thank you.
Okay. Just had a small question. So I think in general, humans are not particularly good at recognizing emotion in text, especially, in spontaneous language, like with emails or text, because we had to add emoticon, otherwise, we couldn't really carry it very well. And so how do you feel, why is it so, if you can really detect emotion directly from text, can you help people writing texts which can really fit what they are feeling, and so they convey the right message to the people they are talking to?
Yeah, there's several layers in which one can answer that question. But one of the things I'll go back to is that we should be very careful about trying to say, I know what this person's feeling from one sentence or one paragraph kind of thing. There are admittedly a lot of systematicness to this, and humans are somewhat good at this. But language is tricky, and as you pointed out, there are ways in which language is sort of it's not a perfect ways of encapsulating what's in our brain, and then that goes on, and people have different perceptions, and then they can see something into that text that maybe you didn't have, and things. So automatic systems can play a certain role in this space, I think. But we have to be careful in navigating that to make sure people understand, well, it has these limitations, and you don't want to make use of it in, important life moment issues like I talked about the refugee status claim thing. You don't want to put a system to that and figure out, are they really fearful here, or is this false, and kind of things, right? So.
Yes, sure. Yeah. Okay, thank you. You have any more questions? No. So thanks you again for your very nice talk. So we are going to move to our next speaker. Okay. So next speaker is Frank Rudzik from the University of Dalhousie in Halifax. And so he works at the intersection of machine learning, natural language processing, and application to the health domain. And okay. First tokenized, no harm. That's the title. No, I was just reading the title you had in Latin. So, but you have the floor.
Thanks so much. I wanted to start by echoing how Saif started, by thanking the organizers of this very interesting event, and Mila for hosting us. I think it's been very interesting and inspiring over the past almost 3 entire days. So my talk's mostly going to be about what I work in, which is natural language processing in health. So in medicine, we have to start our talks with conflicts of interest, so I'm going to go through a couple. So first of all, a couple of us a long time ago started a company called Winter Light Labs, which used voice and speech as a biomarker for neurodegeneration. That company had a successful exit last year and is now part of Cambridge Cognition, and I have shares there. A little bit later, I started another company called Autumn. I didn't name that company. They were doing basically the same thing. Voice is a biomarker for mood disorders like depression and anxiety, and that company also had a successful exit a few months afterwards. I was then for several years at a company called Surgical Safety Technologies, where I was the director of AI. I did mostly computer vision, so we had like cameras in the walls of the operating room, inside the patient, to try to assess for surgical skill. More relevantly, we also had microphones, so we could listen to the surgical team and assess for kind of tone and workflow in the operating room. And I had a successful exit from that company last year, and then I'm still a shareholder of Mutual Health Solutions, which does speech recognition and large language models for scribing, which is going to be a little bit of a focus for today. So I like to think about natural language processing in healthcare kind of in three big categories. The first category is analyzing things that patients say. So you can use patient speech, self-reports, or social media posts, any of their language to kind of aid in diagnosis or make assessments on their individual conditions. The second category has to do with analyzing things that doctors say. So looking at medical notes, referrals, even kind of text messages between nurses and doctors to perform a variety of tasks, improving clinical outcomes, making workflows more efficient. And then finally, using natural language processing to sort of listen to the things that researchers are saying or the general public are saying, and to use those to try to find patterns that might be relevant to us, usually in research. So knowledge discovery from medical text, information retrieval in PubMed, and so on. So I'll talk about each of these, mostly the second one, but I'll talk about the first and the third for a brief moment. So this is kind of an old task we got into a long time ago, where you basically get individuals to kind of speak in a free-form fashion into their tablet, into consumer-grade equipment like Alexa. You ask them about their day, you ask them to describe a picture, and then you analyze various aspects of their speech in order to do what I said a moment ago and try to identify issues related to depression or neurodegeneration and so on. So this is really old work, and this is the basis for the company Winterlight. You know, we started off doing good old-fashioned feature extraction. We realized that certain features might be more common in people with dementia, so we extracted those, and we kind of used classical machine learning. Over time, we kind of graduated and started looking at transformer networks. We kept on setting higher and higher benchmarks for performance on detecting Alzheimer's disease from snippets of speech. So this first paper here was one of our states of the arts at one point. I kind of grew out of this area of research, and then a year or two ago, an intern joined my lab. He kind of picked up this research again. He went back in time, and he used word-to-vec and good old-fashioned machine learning. And he was able to get a new baseline that beat our previous baseline using word-to-vec, beating transformer networks. Because I think this is actually kind of a pretty easy task. Like most of these accuracy things are like 92, we're kind of hitting a ceiling. But the issue here is not really kind of trying to improve accuracy or F1 or recall or all that kind of stuff. If we want our tools that we're researching to be used in practice, we have to consider other kinds of key performance indicators. So nurses, gerontologists, speech-language pathologists, they don't really care about the difference between 0.92 F1 and 0.93 F1. And quite frankly, anything above 0.7 F1 might be perfectly fine for them. What they care about is how am I going to integrate this into the current work, how the patient's going to react to it, how can this tool kind of relate to all the other things I care about, such as comorbidity, the diversity of symptoms, the diversity of the patients I have in my long-term care facility. So I've kind of moved out of this area, but recently we started a new project with the NIH. Bridge to AI is a very massive project. Bridge to AI Voice is like this $15 million subset being run out of South Florida. And we're leading the neurological disorders kind of sub-area of this. I think this is really cool. So we're going to be trying to gather about 30,000 unique voices from across mostly North America, across 5 disease categories. So mood disorders, voice disorders, respiratory diseases. There's a PEDS team looking at children, and neurological disorders. They call it ethically sourced, which sounds kind of weird for data, but that's their term. So we're just at the very beginning of this process. We're nowhere near 30,000 voices yet, but like the app's been developed and it's integrating with hospital networks, and this data set should be available probably in about 4 years. So if you're interested in speech and demographics and all these different kinds of tasks, this would be a good resource. There's another network called CanBind. This is mostly across Canada. There's 11 health centers, 12 universities, and Dalhousie is the data science platform lead for this network. It's very similar. This is an old slide, so currently there's like about, I think, 40 different studies, many more papers. They're also looking specifically at mood disorders, specifically depression and self-harm. So yeah, there's at least 1,500 research participants, so on. I think the interesting thing about this data set is that it's extremely multimodal. So for all of these 1,500 individuals, we have lots of speech, we have conversations between them and their doctor. We also have EEG measurements, we have like digital health, so they have an app, they have actigraphy from smartwatches. We have blood samples from all of them, so we can do genomics. And this project's been going on for a number of years. I just joined it, but it exposes a lot of interesting things we can do with like multimodal models for the purposes of detecting depression and self-harm. And just like the NIH project, the whole point of what we're doing here is to make all these data open and available to whoever wants these data sets. So if you're interested in 30,000 voices on one hand or deeply multimodal data on the other in clinical settings, I welcome you to kind of talk to me about it, because we're very eager to share and follow open science for this sets of projects. I mentioned we can also analyze things that researchers and the public can say. This is not something I focus on too much, but I have a grad student at the University of Toronto who is trying to use information retrieval techniques to automate or improve the systematic review process. So especially in medicine, systematic reviews are extremely important, but to do them right, they take a very long time. They can take 67, like more than a year to run entirely. Again, to do it right, they can cost hundreds of thousands of dollars, and if you're a big institution, like a hospital network, it can be like almost $20 million a year just spent on this one task, on average. That being said, like even if you put all this energy and resources into systematic reviews, the error rates are still pretty high, so there's still a lot of false positives and a lot of false negatives, up to on the order of about 21%, which is not great. So can we kind of make some impact here by using NLP and information retrieval to help automate some of this process? So this student I'm talking about at U of T is focusing specifically on bumetanide, which is a sort of diuretic. So for her work, she's looking at adverse drug events. There's about 6 million papers on PubMed on adverse drug events. And within that massive amount of data, there's only about 140 or so that have anything to do with bumetanide. So it's a very much of a needle in the haystack kind of problem, but we all know that there's lots of solutions we can apply to this kind of problem. There's another researcher at University of Toronto, a postdoc, who is using almost identical techniques, so information retrieval techniques, to try to find patterns of abuse suffered by healthcare workers during the height of the pandemic. So she has lots of social media data, and as you might recall, there was a time where like nurses were being abused physically in some cases, but also definitely online. So she's basically looking for patterns. Who are posting these kinds of posts? What topics are they using? Who are they targeting? And so on. But here's the kind of the meat of what I wanted to talk about, analyzing what doctors say, which is kind of the focus of what my lab is doing these days. So this is definitely the case in Canada and the United States. I'm not sure what it's like in France, but I understand it's a very pervasive problem that frontline workers, so general physicians, nurses, are suffering a lot at their work, right? So about half of them are suffering burnout. Many of them are thinking of leaving the profession. More than half of them are so overburdened that they don't have enough time to interact with their patients, right? So they have very, very quick visits to your doctor, and that is not what the patient wants, it's not what the doctor wants. So part of the reason why this is a big problem is the amount of burden that these doctors have to do with unpaid administrative tasks. So, at the end of the workday, doctors go home and then they immediately go on the medical record and they kind of chart up all of the day's interactions. And that's about half of their time. And they're spending basically interacting with these medical record systems and not doing what they wanted to do in medicine in the first place, which is talking to patients and helping them get through their various issues. So part of the problem is there's just an incredible burden of this like data entry with medical records. And part of the problem also is that a lot of what doctors do is decision making, right? So a patient comes in, they have some labs, they talk about their symptoms, and doctors have to make decisions. And if they don't have much time with their patients, it's harder to gather enough data to make those decisions effectively. But we know that in machine learning, this is kind of what we've been doing for a very long time. We take data from various sources, like the structured data in a medical record, time series data from like an ECG, for example, and then text data. We feed all of this into a neural network, and then we can answer questions like, should this patient that I'm looking at right now be admitted into the intensive care unit? I'm going to focus obviously on the text side of things for now. One thing I like about working in this area is the challenge in healthcare data, right? So a couple of things. So noise is a problem in healthcare data generally, but in medicine, there's kind of these problems are amplified. So one issue is acronyms. So one thing I learned working in this area is that the acronym LOL in a medical note doesn't mean laughing out loud. It means little old lady. So if a doctor sees a note and LOL is written, they know it's a little old lady, and therefore they know what kind of condition she might be experiencing. Spelling errors are a massive problem. So I have a relatively small data set in which the word throat is spelled 5 different ways, and that's a pretty easy word. So spelling errors is a problem, and image to text. So in Nova Scotia, they have a lot of handwritten notes from doctors going back decades, and one of the initiatives is to try to digitize all of those notes. Those notes are, of course, written by doctors, so it's really hard to read. So it's a big problem. And then it's also kind of a deep problem because there's a lot of latent information we care about. We have to identify symptoms, so we have to kind of do information retrieval there. We have to identify medications, adverse events, and then we have to relate all of them, right? So like for this symptom, this drug might be the best thing to prescribe, but this drug has a counter effect with this other drug. This patient is also happening, so you have to relate all these things very carefully and very deeply. There's structural and long-term temporal things you have to care about, like when did the symptoms start, how long did they last, when did they stop, if they stopped at all. So these problems are general problems in natural language processing, but they're amplified in health. Data missingness is also generally a problem in machine learning. So that's when you're missing data, maybe you can impute it, there's a problem we all kind of face. There's interesting wrinkles in healthcare also. So, sometimes there's like not labels for certain things, or lab work is missing, or things that should have labels have like labels that don't make any sense. So that kind of task is always a big problem. 2 interesting things. Sometimes data missingness can actually be helpful. It can be the case that you care about whether or not a patient was intubated, like a tube was inserted down their throat so they could breathe if they're put under anesthetic or something like that. So you have a big database and you have lots of empty space where data on intubation should exist. And that would seem normally like that's a problem, like where we should be having labels here. They should be like no intubation occurred at this point, and that should be explicit. But there's an interesting paper from several years ago out of a PhD student from Waterloo who kind of noticed that the missing data in healthcare data actually serves a different purpose. It can actually tell you something about the patient. So if there's no data about a patient being intubated, it's not just missing data. That means that the doctor who visited with that patient didn't think that intubation was necessary. So you can use that information, that data missingness, to tell you something about the severity of the patient's symptoms. So, which I thought was interesting. It's something that you don't tend to see in other data missingness problems. Another thing I learned, which may be the only thing you might remember in this, is that so doctors don't like being sued, right? But doctors have to communicate to each other about patients, and patients have access to their medical records. And a little trick that doctors do sometimes is if you're a nice patient, they'll put at the bottom of your referral note, patient was listened to advice and was kind and friendly or something like that. And then the specialist who receives that referral note will know that this is someone they can deal with. The doctor does not want to write like Frank is a jerk or Frank didn't listen to anything I said and put that into their note because that opens up them to some kind of risk. So one thing I learned is that like in your referral note, if you don't have a special kind of line about how nice you are and how much of a good listener you are, that can mean that the one doctor is kind of secretly communicating something to the other doctor. So I'm going to walk through a couple of like this use case of Suzanne arriving at the emergency room. So she has trouble breathing, so she took herself to the emergency room entrance. And then I'm going to walk through a couple of use cases of natural language processing in the hospital. So there's a nurse there. Often they'll take vitals and they'll take a little history. So they'll talk to the patient. So this is where scribing comes in. I think you'll probably know what scribing is. Scribing is basically where you have a microphone or two between a doctor and a patient. And the two of them talk as they normally would. But then behind the scenes, there's speech recognition that listens to the conversation, transcribes it, like you can see here. This is one of our early works that founded the Mutuo company I mentioned in my COI. So you have the transcript, and then you have LLM or some other language model that goes through the transcript and looks for when the person is talking about their subjective symptoms, like I've been having trouble with a cough and so on. So you can find out here's where they're talking about their subjective issues. You could then either directly insert this into the medical record and hopefully save a little bit of time for the doctor, or you can save this transcript somewhere so the doctor can review it later to make sure their notes are correct, or you could do a summary and the same kind of outcomes happen. So there's lots of different approaches to this. We tend to use open models like Whisper or Wave2Vec2. Like those are speech recognition models that you can still run locally, and often that's a big issue in healthcare also. Whisper obviously is a very strong speech recognition system, but it still has trouble with diarization, so it still has trouble identifying when the patient is talking and when the doctor is talking. That's a subtask of speech technology that hasn't really improved much. So I have a PhD student currently who's working on that specific problem. So I mentioned this a moment ago. Generally how this works is you might have an open speech recognition system. Whisper is our favorite at the moment from OpenAI. You can fine-tune it because it's local, so you can fine-tune it to have low error in noisy environments. You can fine-tune it to be maybe better at medical terminology. Again, given the transcripts, clinical and BioBERT are still used quite a bit, but increasingly researchers are using large language models like Llama, again, as long as they can run it locally, to either kind of summarize these conversations or directly start making classifications. So I'll get to it in a second, but ICD stands for International Classification of Diseases. This is basically labels that we want to predict. So this patient has disease X or disease Y and so on. Named entity recognition is also a big deal, like I mentioned, like what are the symptoms, what are the drugs, what are the diseases and so on. And then there's also a part that a lot of companies, not Mutuo, but other companies I'm aware of that are doing scribes, they kind of add reinforcement learning on top of these large language models, sometimes seek-to-seek models, in order to make sure that the experience is appropriate and that the notes are maximizing things like clarity, conciseness, professional tone, and that sort of thing. So scribes have been around for a while, and it turns out that they're really useful. Even scribes that are like 5 years old at this point can reduce the amount of administrative burden that doctors face by about 50% by doing these kinds of tasks. So right off the bat, we're starting to make a bit of an improvement to workflow. There are lots of problems. So sometimes doctors want to use chatbots for absolutely everything, or they're just using scribes, but they're using scribes for tasks that they weren't originally built for. So doctors have a lot of things that they're doing, not just interacting with patients, and they're going to use scribes for doing different tasks. That's a bit of a problem. There's also a problem with evaluation. So how do we evaluate whether scribes are actively effective? Like if you're doing summarization, you might be tempted to do something like use a Rouge score or Meteor to kind of assess how well you're doing. And like I'm trying to emphasize here, the kind of computer science metrics we use to evaluate our models don't really apply in practice in healthcare. What they care more about, we still measure those things, but they care about issues like clinical accuracy, hallucinations, relevance, completeness, and so on. So this is a great paper that came out just a few weeks ago called MEDIC, that is like a platform in order to evaluate large language models specifically on a variety of tasks, mostly on scribing, but also on just like retrieving medical knowledge, like from the web, recommending treatments, giving some structured information, and so on. I don't have time to talk about it too much, but the way it works is you have a note, you generate a summary, you generate questions and answers from the original note and the summary. You see how the model for the general note would respond to questions for the summary and vice versa, which is this little cross bit over here. And then there is a scoring mechanism. They use Prometheus. Prometheus is a very common large language model that's meant to replace human judgments in various cases. And then they assess for things like consistency, coverage, conformity, conciseness, and so on. The results are kind of mixed. So again, this only came out a few weeks ago, so this is very new. So here this graph shows the scores according to a couple of these medically relevant metrics on large language models like GPT-4o, Llama 3.1, and so on. There's not very much difference that is shown in this paper across these different language models in terms of these scores. One thing that does stand out is that all of these large language models seem to do fairly well in terms of like monitoring for confidentiality and bias, making sure the structure is logical, making sure the language is clear. One area in which these large language models seem to fail pretty spectacularly is in terms of mitigating risk. So are they going to propose things that might actually be risky for the patient and other forms of patient safety? So again, this is very new work, so it's hard to really evaluate what this means. It's possible that the MEDIC giving the same scores more or less to all of the different large language models might reflect priors in Prometheus. The fact that it gives very low scores to patient safety might also be a prior in Prometheus. So more work needs to be done, and part of that involves getting more data. So another one of my students at DAL is focused on generating, again, another data set that we hope to make public in a few months, depending on the outcome of a review process. One problem in healthcare is that there's very few data sets, right? So either you work with a doctor and they give you data on like 20 or 30 patients, or you use a data set called MIMIC, which is a relatively large data set from MGH, from Massachusetts General Hospital, which has a lot of text in it, which is great, and a lot of patients, like on the order of tens of thousands of patients. But it's just for the ICU, and you can only predict things like sepsis and mortality. So if you care about any other condition or any other area of healthcare, like MIMIC is not really what you want to use. So what we're doing right now is trying to generate notes and questions and answers and dialogues synthetically using GPT-4o, and we've run some benchmarks on it. And again, the main thing is the data, so hopefully the data will be useful for people who want to do NLP and health, but are getting sick and tired of MIMIC. I want to point out a few things here, like, this looks a lot like what medical notes look like. So you have all these acronyms, like PUT means patient. CO would normally mean for you and I, care of, but in medicine it's complaining of. There's all these spelling mistakes, like doctors don't know how to spell, so trouble is written that way, breathe in is written that way, and so on. All right, so this is realistic. We showed this to a panel of family medicine doctors, and they all kind of confirmed the quality and correctness of these notes. Yeah, so this is under review right now, so we'll see what happens. So again, the use case is Suzanne. She went into the admission. She talked to a nurse or a doctor. We did all of the scribing. And then scribing, and the outcome of scribing was used to help schedule Suzanne to get x-ray. So now she has breathing problems. She went to get an x-ray. This is an old task at this point, but the idea is you can generate reports automatically from images also. I think we all know how to do this. So this old paper, there's obviously CNN, some RNNs, and then some reports that come out, and then you get a report that more or less describes the image as accurately as possible. The reason I mention this old kind of technology right now is just to emphasize that one of the quirks of natural language processing in medicine is that we tend to have a lot of these kind of bespoke lost terms, right? So in this paper, they wanted to make sure that they were coherent with regards to the diseases. So it doesn't matter as much that you're using language that sounds like a good English sentence. What matters is that the content of these medical notes really refer to the actual diseases that might be present in the CT scan. So this relatively simple lost term basically sums over all of the possible diseases and all the possible states of those diseases, and effectively tries to correlate the prediction of a state given a generated label and the probability of the state given the ground truth label. So it just basically it generates documents that are relatively coherent with the truth. So here's just a little example. The generated text is as compared to the previous radiograph. There is no relevant change, and the actual text is as compared to the previous radiograph. The monitoring and support devices are unchanged, which is what you want to see. Of course, these multimodal models can go in the other way. So I mentioned briefly yesterday that we're doing some work with some neuroscientists. Their problem is they do a lot of work with fMRI data of the brain, and there's not enough data for people. There's one particular disorder where there's a kind of a pressure on some of the nerves caused by some of the veins in the brain. So it creates pain in the patient. There aren't enough patients that we have so far, and the location of these infarctions are very small compared to the size of the overall image. So you could prompt a stable diffusion type model to generate all kinds of synthetic brains to have any parameters you want. I want a 60-year-old woman with this sort of lateralization. I want a 70-year-old man with this amount of white matter and so on. You can generate a lot of synthetic data that can be very helpful for you to do computer vision-based training for that side of things. So finally, what we want to do with Suzanne in the hospital is we want to identify what the challenge is. So what does she have? In other words, we want to assign the ICD code to her. What disease? The ICD, again, is International Classification of Diseases. It's not just diseases, it's also procedures. So there's a couple of problems here. The big problem is that there's more than 140,000 of these codes. So if you're just trying to make predictions as to what disease somebody has, that's a very extremely multi-label classification problem. And the other problem is that the labels themselves are very noisy. So the ICD is structured as a tree. like I kind of showed over here, and the tree gets more and more specific as you go down the tree. So you might have a code like F1025, alcohol dependence with alcohol-induced psychotic disorder, but there's all these subtypes of that, sometimes with delusions, with hallucinations, unspecified. So some doctors kind of overspecify, and they would, for a patient, say F10259. A more senior doctor maybe, or a lazier doctor would say F1025. Technically, these are different labels, to a naive kind of classification setup. So we just have to make, and so they all have different labels. Is this actually F10259 or is it F1025? So I have a patient at the University of Western, a PhD student at the University of Western Ontario who's trying to solve this problem. She has two solutions to it for the extreme multi-label classification problem. The first one is to incorporate that ICD tree directly into the large language model that's going to make these predictions. So the first thing she does is just represent that ICD tree as a graph, and then she does a couple of things on that graph. She looks at co-occurrence, for example, of diseases in a large body of literature. So you have like a nice interpretable graph CNN. And then that is paired with a regular large language model that looks at these notes that are coming in. And then together you make the prediction of the disease. Our numbers are better than their numbers. The second approach she took was to treat this as a two-stage process where the first thing she does is do this multi-stage retrieval. So she picks out a couple of documents. So this is more in line with like RAGs. She again applies auxiliary knowledge here, but it's basically this hybrid discrete retrieval method, and then she re-ranks ICD codes. There's some contrastive learning thrown in there. So this is more of like an information retrieval-based approach where she can triage a large number of ICD codes, which are definitely not the case, and that reduces the space of possible labels, making prediction a lot easier. And in this paper also, which also came out this year, again, her numbers are better than other people's numbers. But these numbers don't matter. Again, this is something I'm trying to emphasize, like F1, OROC, these things do not matter to doctors and nurses. They don't really care about this. What they care about is making sure that patients can go through the ICU quickly. They have resource constraints they're dealing with. So I wanted to highlight there's a group in a hospital in Toronto, St. Michael's Hospital, that use technology not that different from this to just optimize the provision of nurses in the emergency ward. It was extremely straightforward. It was based on a little bit of machine learning and a little bit of signals from structured data. But their approach to basically just figure out how many nurses they needed in the ER at a particular day saved that one hospital, just for that one task, on the order of like $1.5 million in terms of just provisioning how many nurses they needed to have available and how many nurses they would have waiting around. So the point is that that kind of thing matters more. So we have to kind of relate, all these metrics that we're getting from modeling to things that matter to our potential users. So this is the second and last part of this talk, which is like challenges we're dealing with. One of the first big challenges in NLP in health is bias, as you might expect. So in this paper, they're again looking at CT scans, or X-rays rather, of the lungs, and they're trying to make predictions about disease state. This paper is a bit confusing because in this case, a prediction of no finding is treated as a false positive, which would be underdiagnosis, which is kind of contrary to how we normally think about false positives and false negatives. The point is that they're kind of trying to figure out underdiagnosis. Right? So is a patient who has a disorder going to have a false negative and be sent home, right? Because that's something we want to avoid. If someone has cancer, you don't want to send them home without treatment. And just for the sake of time, I'll go through this quickly. I think you kind of already predict what the issue is. So women have higher rates of underdiagnosis. Young people aged 0 to 20 have a higher rate of underdiagnosis. People of color and people in lower socioeconomic statuses have more false negatives, right? So more underdiagnosis. They're not treated, and that's obviously a massive problem. This is also a problem when we're trying to integrate natural language processing into hospitals. Because doctors are aware of this idea of bias in machine learning, and then therefore they get a bit skittish about actually implementing this. And one thing we have to emphasize is that like AI and machine learning didn't invent bias. Like, the bias is not there because we're using a transformer. The bias is there because the bias is already there in the data, right? Maybe it's the case that machine learning exacerbates this bias, but it's not machine learning itself that's the issue. Like, the issue is the healthcare system. But there are lots of methods we can use to mitigate against this problem. Again, you're aware of this. So we had a paper a couple of years ago that basically applied equalized odds post-processing. So we, again, had a multimodal system of time series. We had text. We did hard debiasing of the embeddings in the model to remove sex, age, race factors from the model. And then we applied equalized odds post-processing, in which the chances of having a positive diagnosis really depends only on whether or not you actually have that diagnosis. And it does not depend on whether you belong to one of these various groups or another kind of these groups. So you can do post-processing to make sure that the true positive and the true negative rates are balanced across whatever groups you care about. And of course, there's like dozens, maybe hundreds of different approaches to debiasing these kinds of systems. The second big problem, of course, is privacy. Machine learning needs lots of data, more now than ever. But because of regulations, it's very hard to get this data in the first case. Like I mentioned before, we have either like a data set we have to get from a colleague, or we have this one public data set, and that's more or less it. So it's a big problem. One issue in language is that there are techniques to try to de-identify or anonymize text. And a lot of that involves looking at medical notes like this, identifying where names are and replacing it with a token name, identifying where ages are referenced and adding the word age and so on. So usually humans do this. The accuracy of kind of obfuscating personal health information in medical records has its accuracy is about 99.8% or something like that, which sounds wonderful. But if you have a population that's millions or tens of millions of people in size, that 0.1 or 0.2% can correspond to thousands or tens of thousands of people whose data is still out in the open if it's meant to be shared. So it's still a massive issue. One of my previous students at the University of Toronto developed a technique to using embeddings. So you'd read the whole document, you get embeddings for every word in the document, and then you'd kind of sample from around the individual words. So absolutely every word, not just like words that are identified as names and ages, were replaced with other words. So every single word in the note was something else. So this became completely unreadable, so it was not very explainable. Like, we couldn't look at that note and really understand what was going on. But these embeddings, these neighborhoods of embeddings were similar enough to what the actual data was that we could still feed that data in to fine-tuned models and still make pretty accurate predictions with that approach. It was a very straightforward approach. The student is great. He's now a faculty at the University of Alberta. So he's still interested in privacy and operations research. His name is Mohammed Abdallah. Another problem in privacy in healthcare is connecting auxiliary data. So this is kind of a cartoon example, but imagine you have information, like you have some information, you know a patient is 60 years of age, is a male, and so on. In this example, the patient comes in complaining of like an injury, right? Sometimes there's a news article that exists that has all the same information, 60-year-old male at the time that he entered the ER, et cetera, et cetera. So all the information between this public information and the private information sort of match up, and you can kind of correspond these two things together to identify that the person being talked about in this record over here was specifically Ronald Jameson, because that's what occurred in the news article, and therefore you can do all kinds of things behind the scenes with medical records if you have access to them. So the solution to this usually is differential privacy. I don't need to explain to you how differential privacy works. But as you know, it's a way to make sure that the model itself sort of forgets all the information about the patients so that we don't have to worry too much about that. So you apply noise to remove information about the patients. This came up yesterday also. So, we have techniques to remove bias. We have techniques to increase privacy. But unfortunately, these two things are kind of at odds with each other. Okay? It's hard to increase privacy and make these systems less biased. Another paper applied differential privacy to a task of making predictions based on radiology. So what this graph shows, every column of these x-axis refers to a particular patient, and the y-axis is their influence on decisions in the test set. Okay, so some of these patients have a lot of influence on decisions of patients that are held out later on. Applying differential privacy basically noises out information about these patients. So you kind of like at entropy, these red lines over here represent the influence of these individual training set patients on test set patients after differential privacy was applied. So it looks good. All the patients look the same to the model now, right? So you've increased privacy to the point where all the patients look the same. The problem is that most of the patients in this data set were white, very few of them were black, and when differential privacy was not applied, you would use information from patients who were demographically similar to the patient in the test set to make decisions. That actually resulted in better accuracy. If you remove demographic information from the model, all of a sudden, all these white people in the data set have an inordinate amount of influence on the decisions made for black patients in the test set, and the result was that the performance for black patients went down after differential privacy was applied. So I have a wonderful student in Dalhousie who has a couple of papers this year. This one's in Europe. There's a similar paper in EMNLP. He invented something called representation noising, which kind of combines these issues of privacy and debiasing. It's kind of complicated. The idea is you can train specific losses to reduce harmfulness while maintaining or increasing helpfulness. And one of the cool things about this is it also applies when only the attackers have the access to the weights. So imagine you open source a large language model, you apply differential privacy, you apply debiasing. It's often the case that you could rebias it, or you could re-identify people. But in this case, even if the attacker has the full model, and even if the defender never sees that model again, representation noising is a very effective way of debiasing and maintaining privacy. And this is my third to last slide. My main challenge as someone who is a computer scientist who's trying to get these technologies to be implemented as much as possible in healthcare, because I truly believe this is going to be really transformative, and like we saw with scribing technology, like improve efficiencies, improve outcomes. This is my existence. So people find out that you're an AI person who does health applications. They have a cool data set in whatever area that they're working in, psychology, cancer, or something like that. So you spend a lot of time, you get a grant together, you find a student, you apply for research ethics. That whole process can take like a year and a half or even longer sometimes. You do a bunch of work, so you get to the point where the master's student can get a paper out, your numbers are better than their numbers, and it looks good. But then the student graduates, and there's not really a way for the hospital in which these clinicians are working to receive this new model, right? So occasionally you can go from the research phase to the quality improvement phase, where your model is put into practice and actually run on real patient data. But that's usually a short-term thing. It's kind of just like research plus, and it's really difficult to get to the point where you can see these tools actually being put into practice. So there's systematic factors at play here. So the summary I want to emphasize is that in natural language processing in healthcare, bias is still a big challenge, but there are solutions. And privacy is a huge challenge, and there are solutions. Bias and privacy together is an interaction effect, but there probably are going to be solutions. I think representation noising is very interesting, and there are lots of real-world, mostly human challenges. But I work in this area for a couple of things. The data is super interesting. The challenges we have in NLP generally are amplified in a lot of ways in healthcare data. But if we can actually succeed in what we're trying to do, ideally we'll have NLP that can listen to patients, provide more personalized care, have better outcomes for patients. And then the kind of NLP that listens to doctors can be used to improve efficiency, avoid adverse events, and so on. So this is, I believe, very meaningful work. It's very a privileged area to work in. And again, we're generating a lot of data that's meant to be shared on the topics of mental health and neurodegeneration and voice disorders. So if you're interested in any of that stuff, please be in touch. Thanks so much.
So thank you very much for it's very complete, a lot of things in your presentation, and you covered a lot of topics. So thank you very much. Please, Mark.
So can you hear me?
Yes.
Thank you for the great talk. I also think that using speech as a biomarker for many different pathologies is a very good idea. I know you have a lot of experience with that. I just started diving into this field. And when we discuss that with clinicians, right, it always comes a problem, the interpretability, right? They don't trust black boxes. Do you also encounter this problem discussing with clinicians? And Do you see in the literature something promising that can improve this?
I've gone back and forth about explainability because for a long time when these new explainable methods were kind of coming on the scene, I was like, this is wonderful and this is going to solve this problem because like we were experiencing that exact same thing. Like clinicians, if you show them like we have 81% accuracy, they don't really care. Like they want to make sure that they have questions about, well, does it work in this language? Does it work for these patients? Would it work in this situation? And they also they have a lot of like theoretical background knowledge that they want to bring to the problem. So you want to have a model that can explain itself and kind of matches up with what they expect. So the classic example was when we were talking to neurologists who understood like Alzheimer's disease. When we showed them that the model was attending to things like the complexity of sentences, like how complex the sentences are, like less complex sentences might be one small indication of dementia. It resonated with them and they were happy with it, right? So around that time, like years ago, I thought explainable AI is going to be really important in machine learning and health generally and natural language processing specifically. But like over time, I'm starting to get more disillusioned from it. Part of it is like it's an ongoing issue there that like the machine learning community has started to demonstrate a lot of problems with like gradient-based methods. Attention is like not explanation and so on is a popular paper. My hesitation is with human factors, because sometimes you can apply explainable AI methods and you can say, well, the model is attending to this area of the video or this feature of language. And when it matches, I've kind of noticed that clinicians will be like, okay, that's great, it matches my expectation, we can move on to the next step in whatever we're doing. But then I kind of noticed that they're ignoring situations where there's like attention being paid to like spurious things that don't really make sense that we can't explain. So like a brain like scan lighting up in areas where it shouldn't light up. Okay, if Broca's area lights up when they're doing a language task, it's great. But if other areas are lighting up, they just don't explain it. But that's a problem, right? Like why aren't we attending to that? It seems like a false positive. And like so on and so on. Like it's an issue whether it's like Taylor expansion methods, gradient-based methods. Like I don't really trust them, so I'm hesitant.
That mostly as an open problem where we need more research.
Yeah, I think explainable AI is something that should happen, and like I didn't get to talk about it for time, but I think like we have to keep on pushing it forward a little bit. But we just have to be very careful about what we're promising. Like we can't take like a result from a paper and say we have an explainable model now, and this is going to generalize. And like the human factors are increasingly a part of it. So I think the trick is to work with people who do human-computer interaction research and try to identify like is the human in the loop integrating errors where there would otherwise be errors.
Thank you.
Just a small question. So do you think NLP can help? One of the issues in healthcare is communication between patient and doctors, because the level of knowledge a patient could have about medical domain varies a lot, among patients. And do you think NLP could be a tool which could translate, to the level of literacy of medical domain from the doctor to the patient? Do you have any experience on that?
I wanted to have like a Google Translate for doctors and patients for a long time. But we never actually got around to it. I think that's going to be a nice like solution. There is some statistics in how like patients don't usually know how to communicate with doctors in a couple of different ways. So they don't know how to explain their symptoms, but they also don't understand what's being told to them. So if a doctor says you need to take 2 of these pills every day for 2 weeks, if the patient starts feeling better after like 5 days, they'll just stop taking the medication, and they don't know that they're supposed to follow the instructions to the letter. So those kinds of issues aren't really like they wouldn't be solved with like a machine translation system. They'd have to do with like other like tools that could be used to monitor the performance of the patient.
Okay, so thank you very much again, and we are going to move to our last talk of the last session of. So for the last talk, our speaker will be Géraldine Namnati. She's a principal research scientist at Orange Innovation in Lannion in France, and she's been working on various aspects of natural language processing, from spoken language understanding to information retrieval on various domains. And she's going to talk today about evaluation and going from benchmark to real life. So please, you have the floor.
Thank you very much. And thank you for inviting me and for everyone to stay until the very last presentations after 3 long days. So just so to understand what would be my point of view, so I work in Orange, the French telecom operator, and we are in a branch that is called Orange Innovation. And in this entity, we do some research, but we also have we also do a lot of products. And so just so you understand, this is our division, and around us we have many entities like the countries and the finance entities. And all these are actually our customers, and we do products for our colleagues. So this is my point of view. I'm both a researcher, but also having this, thing in mind. So we are an international company with customers in several countries. So we are committed in multilingual NLP for sure. And so in this session, it was about how is this going to change the society. So I'm not really going to talk about society in its whole, but I think I can give some insights about how is this going to change the way we work in our company, which is in itself a small society of around 100,000 employees. So this is something we can talk about. So first, very early when ChatGPT went out, very quickly it was forbidden for us to use it to do anything about leaking our information and our data. But we managed to have our internal ChatGPT, which is called Dinu2, and it's a conversational assistant, and it was very successful. There are a lot of different users and many requests, and we have this interface, and we can choose the model we use to request, and it's all on a Microsoft dedicated tenant that is secure and deployed in Europe. And so we can analyze what the people do with that. So for instance, this is a work we are doing now. We are studying the logs and looking at the usage, and we can see we are doing some classifications in terms of tasks or domains. And for instance, one of the things we can have a look at is how it evolves over time. So we can see, for instance, that one of the tasks that has gained interest for people is like rewriting. So improve things and like that. And the domains are so diverse, and so this is the kind of thing we can look at. And why we are doing that? Well, it's just for monitoring, but also maybe to do some recommendations, to be able to use maybe not always the biggest model, to do some simple tasks and to sensibilize everyone about this, and maybe even recommend some smaller models or things like that. We are we work in a research program, so you can see the different contributors that are leading some topics. And we also have some partnerships with academia, some national projects, some European projects. But also, I am involved in delivery activities, and the main activities are, well, of course, the first one is customer relationship. This is why initially we are working on this. But also, we have a lot of activities in knowledge management, how to better handle our documents, our videos, our meetings. And of course, interaction is also one of the big things. And there is a new activity which is gaining interest. It's the importance of doing language model adaptation, because strategically we don't want, of course, to retrain our own foundation model, but we would like to have some good performance in our domain with smaller models. So we are doing a lot of things on language model adaptation. I will talk about it. So what is my point today is that now that the technology is getting more and more powerful, it's also getting more and more easy to use. And before, if you wanted to do like a dialogue system, you had to have some skills in dialogue management, and programming, etc. And for instance, when the tools like IBM Watson arrived, it became already easier to deploy a chatbot. And some operational teams with developers could do their own. And already it started to have a shift between, it's easy to use and to deploy, but then how do we really transfer the methodology? How do we evaluate properly? And now that it's even easier, that you just have to prompt basically, that if you have documents, it's very easy to deploy a RAG system and you can do very powerful things, which is good. But it's becoming even more difficult to evaluate and also to sensibilize all our colleagues and the end users on the methodology to properly evaluate what they are deploying. So I'm going to go through some use cases and to give you some insights about all the difficulties we have in this matter of evaluation. So the first one, very early, as soon as the LLMs came out, the first big use case was conversation summarization. Obviously, for all the contact center interactions, if you can easily summarize, you gain a lot of time and efficiency when the customer calls again. So it was very appealing. Everybody wanted to do that and to deploy that. And we say, okay, but we need to know exactly if we massively integrate some summaries in all our information system, what are we doing and what exactly, what is the risk of introducing erroneous data. So what we wanted to work at the beginning, it was on human annotation, and we decided to develop a annotation methodology to do fine-grained annotation. The objective was to have a reproducible methodology, to have reduced subjectivity, and also to have a notion of error rate. Not only is it good or bad, or maybe have a grade between 1 to 5, but to really have a fine-grained analysis of the errors that could be in a summary. So we designed an annotation protocol with linguistic errors, lexical, syntactic, and also repetitions. But also, more interestingly, on the semantic level. So we wanted to go beyond the simple notion of hallucinations. So we distinguish between pure hallucination, pure insertions, and also some substitution on a factual event like a date or an amount, or some approximation. For instance, if the customer said there has been 3 network cuts this morning and the summary says there has been several cuts today. Okay, it's not false, but it's an approximation. So this is different. It's not like a pure hallucination. And so we did that. We took samples of data. We have several annotators. So it was the context that we wanted to benchmark an external solution with. So it was particularly low quality transcriptions. And we compared summaries generated by GPT-4 and GPT-3.5. And we were able to have this kind of figures and to have some really fine-grained notions of how many substitution error span is there on average in the summaries. And so we believe that is something that is more insightful than just an overall grade. And also we could say to the business units that, okay, it's very good, of course, but if you do that, you must be aware that in 20% of the conversation, there would be at least one fully insertion error. So measure the impact of that. And in 60% of them, there is at least one substitution error. So have to be aware of that. So so that was the first thing. Then we wanted to extend this to another type of data. I'm going to be quick on that, but we worked on the meeting minute generation, and for instance, it was a challenge, and so you have the whole transcription of a meeting, and you need to generate some minutes in a structured way. And for this challenge, there were several participants. So we did a very simple system without any LLMs, without any even fine-tuning on the data. We wanted to evaluate some BART levels with a text simplification. But there were also systems that used LLM for augmenting data generation, and also pure LLMs for the task. And when we were working on this, we were struggling with using Rouge score, and it was very hard because it didn't mean anything, and every time we were trying to do something, we couldn't even understand the impact of it, so it was really complicated. And then the organizers, they did some manual annotation with the fluency, grammaticality, adequacy, relevance, and you can see some of the scores that were obtained. And one issue is that we took a sample of these data and we did, again, the same campaign with an external company that we paid to do that, and we had a lot of discrepancies. So even for this simple annotation, it's really hard to reproduce it, and it's really hard to have some simple guidelines. And so we wanted to apply our methodology. So it's a long work. It's very hard to do this, but eventually we could have this kind of information, which we believe are more interesting to have in terms of error rates also for these. Our system had some very bad grades, but it's okay, we know it was pre-LLM, but we want to know exactly what kind of errors it makes. So this is one thing, but it's very costly, and what we would like eventually is to be able to automate this kind of evaluation. So we have started to work on that. So we annotate summaries, and we are trying to learn how to detect these error spans. So it's ongoing work. So it's a very difficult task because you have to find the right span, and then there's only a few errors, and to characterize an approximation or an insertion. But it's the kind of topic we're working on because it's essential if we want to really deploy this at scale in the company. Okay, so now I'm going to switch on another use case. So we have a lot of use cases regarding long-form document question answering. So it could be legal documents, regulatory documents, financial documents with many people in the support function groups that need to better exploit their documents. And what we observe is that it was very easy for them whether they upload their document in the conversational assistant and ask their question, but they say, oh, I don't understand, it's not working, my document is too long, or how is it really? Or they do RAG and then they pose question and they say, oh, it's not working, what is the point? So we worked on a particular document, which is of interest, of course, for us, is the AI Act. So it's a very long document, almost 300 pages and many articles. And we work with a colleague which is particularly working in the ethics and the regulatory teams. And we designed a set of 37 questions of various difficulty. And we had some reference answers. And the important thing that we wanted to do to explain to all our colleagues who were doing this kind of manipulation is that there are different kinds of questions, factual questions that eventually you can handle with a classical RAG, but you can also have broad questions or even structure-related questions that for which you need to analyze the structure of the document, even to count the pages, to do things like that. So we evaluated several different systems and also several RAG systems with different approaches to do the chunking, different retrievals, different models in the end. The objective, again, was to sensibilize them on the sensitivity of all these approaches. And so we were, for evaluation, we used ground truth agreement, where we used LLM to compare the reference, the gold answer, which can be quite long. Sometimes the answer is a whole paragraph. So, and we were able to do this kind of evaluation and to show them that depending on the type of question, you can have a lot of variety in depending on the system you choose and the method. If you do RAG or graph RAG is when you first transform your document into a knowledge graph, and then you query the knowledge graph rather than directly querying the document. And sometimes it's easier to generalize because it can more easily retrieve information that are at different parts of the document. And also we implemented some agentic approaches with tools and showed them that this was much more powerful of course, for structural questions. And then eventually we implemented a routing agent with telling it to use such or such approach depending on the type of the question. And we could have some, so this is the way the tools are implemented in the prompts. And we could have some interesting results when the agents, so this is the results that we get, the accuracy that we get when we combine all of them with the routing agent. And just so you know, every time we do an experiment and we communicate internally on these experiments, we also include the price because it can vary a lot. And you see, agents is quite appealing and interesting, but for the moment, the models that are able to reason over tools are mostly the biggest ones, so it also comes with a cost. So all these is also a matter of efficiency, and when I say cost, of course, we also think about environmental costs, but that is obvious. Okay, so just to tell you about a challenge that is ongoing now. So there is a gain of interest regarding all these regulatory documents, and there will be a challenge in calling about regulatory documents. It's documents from the finance markets, and you have quite complex questions, so it includes retrieval and answering the questions. And what is interesting is that it's not only a matter of precision, it's also a matter of recall, because when you ask about a regulation like obligation, what do I have to do to be compliant? You just, if there are 4 obligations, it's not enough to retrieve 2 of the 4. So it has to be precise, and also we have to find all the obligations. And what I wanted to stress here is that the organizers, they provided the data, but they also came up with a very sophisticated metric. And I think this is going to be more and more the case now. If you have a complex task, you will have to design the metric. And so, but it's a bit complex because it implies to run some NLE and entailment models, also some classification models to compare the input and the output. So in itself, the metric is already, you need to apply 3 transformer models. So I'm quite curious about what this kind of task will give, and will the metric be consistent, and what results are we going to obtain? But I guess we don't have the choice, because it's we have to try this kind of metrics. Internally, we have a lot of use case with this document. It's a universal registration document. It's a very long 500-page that every company has to provide every year. And you can ask many complex, it contains figures, financial results, etc., etc. And we can have complex questions on these documents. But also, we have some requests, like a finance person. She says, okay, I would like to compare our document with the documents of other people from the CAC 40 or our competitors. Can you do a benchmark of these 20 documents of 500 pages each? So, okay, we can do things. We can design a complex system. We tag, we summarize, we then end up with one table with key insights on like 10 topics. So it is possible. It is really powerful and interesting. But again, how can we evaluate this is, of course, an open domain, open question. And for the moment, we don't. So, but it's beyond the notion of performance. We also have a lot of questions internally about the value that all this brings and the productivity. So, well, I won't go into details, but okay. So now I have another part. So I told you that we are also concerned about domain adaptation. So we did a work. There was a presentation in NVIDIA GTC early this year when we give a lot of details about the implementation. So I will summarize, but you can find this online. So basically, we gathered a large corpus of everything related to the telco domain, the network domain, like technical documents, normalization, etc., etc., scientific papers. So we had several pre-processing pipelines. So I won't go into details, but eventually we had 800 million tokens corpus, which is quite a big one. And then we also generated some instructions, and we managed to generate around 30,000 instructions in order to perform instruction tuning. So, and we also had some evaluation data sets, and today I'm going to focus on a particular kind of benchmark, which is the multiple choice question, because it's something that is quite interesting for several reasons. The first one is that it's easy to have an accuracy metric, so we're happy with that. And also, it seems an interesting way to evaluate if the model has acquired some knowledge. So it's like when we do multiple choice questions. We had several MCQ data sets that are more or less similar to the data that were used for the domain adaptation. And then we start from Llama 2 7B models. And the first thing we do is the pure domain adaptations is we continue the pre-training phase with the 800 million tokens. This is not very, it doesn't work. So it was not something enough, and it's even worse than the original models. But when we do instruction tuning, so whether with only the telco instructions or mixing with general instructions, and eventually when we mix both and we do the instruction tuning properly with a good methodology, we could achieve some interesting performance on the MCQ and even reach the performance of GPT 3.5 with the 7B model. So we were quite happy with that. And then we say, okay, now we tried with other models. So we went on with the Mistral 7B. We started with the Instruct model. And then, too bad, it was the opposite. We degraded the performance when we did our instruction tuning. So say, okay, I remember Philippe says, please open your benchmark and go and have a look at what is going on. So don't be afraid, there's a lot of text. You don't have to read everything, but what I want to show is, so this is the question. What is matching theory applied to FDO, FDMA cellular networks? So we have 4 possibilities. This is the 5 possibilities. This is the right answer. See, GPT-4 and GPT-3 are quite good. And the Llama 2 chat model is very confident. Based on my knowledge, I can say that the correct answer is B, which is wrong. And it also justifies with a long justification why it is B, but it's not B. So this is the thing, and therefore, again, it's B. Okay. With our model, adapted model, we were able to have some good, but we can see that in our instructions, we had this form. So first, we provided a justification, and then a conclusion. Therefore, the answer is D. Okay. Now, when you look at the Mistral 7B Instruct model, without any adaptation, it seems that it was trained to reason the other way, so it provides the correct answer first, and then it justifies itself. And when we did our instruction tuning, I think it seems that we broke everything, and the answer is completely blurred. So it begins with explaining itself, then we can find some insights that this was quite correct, because matching theory is applied, but in the end, so it explains that the answer is D, but it concludes, therefore, the correct answer is C, which is not consistent with the justification. And we have several cases like that. So this is just another example. I can confidently answer your question, the correct answer, it's not the right answer. And also, yeah, so just to show that this one was completely misleading, because you say, okay, the solution is C, which is not correct, and then it seemed to be an explanation about why it is C or D, but it's not correct, and then something not consistent too, so, okay. So, having seen that, we tried several strategies to extract the real letter. So from this whole justification, we used a model to extract the letter. So you can say it's a bit like a very big hammer to extract the letter, but actually it's not that easy. It's not just regex, it's not always sufficient. And we had 2 models to extract, one which is quite conservative that would really keep the letter, and one which reinterprets the justification, and sometimes, even if the model initially said the answer is D, if the justification is about C, it would output C. And for that, we used a small model that we fine-tuned for this task particularly. And you can see that we have very different results, especially for the Mistral Instruct. Actually, it was not that bad, but it's that our metric, the way we evaluated, was quite bad. So this is ongoing work, and in the moment we have we ask many questions. What are we exactly evaluating? Do we want to evaluate the knowledge, or do we want to evaluate the ability to correctly answer to MCQ? Was it the form, the substance? All this is ongoing, and it's not easy. So to conclude, I would just give some words about ongoing research activities, and just to point out the PhDs that we have at the moment, and most of them are with the Aix-Marseille University, where we have a framework agreement. So we are interested in understanding how the models behave and how we can easily adapt them. So there is a PhD about factual knowledge addition by Hichem Amarkodja, the PhD of Loic, who is over there, and maybe you saw his poster yesterday, who is working on a task comparison and going deeper understanding on the fine-tuning methods. There will be also a PhD on evaluation of decision-making, complex decision-making tasks. And just so you know, so there is this PhD that is about to start with ISIR and Sorbonne University about information extraction in these visually rich documents like the regulatory, financial documents, or technical documents. And to finish, if I have another 2 minutes, so this is a work that is particularly important for me, and it is the occasion to talk about a work that is also Frédéric is a lot involved in. So in the context of our agreement, we've built this corpus for 8 years now. And the idea is that it's an idea that Frédéric has pushed at several opportunities to put forward, is that we want to be able to do some evaluation that are grounded with linguistic knowledge. So we are trying to build this corpus. So initially it was about semantic analysis based on FrameNet. So we did annotate with French data with FrameNet. It's the biggest corpus annotated with FrameNet. So there we had a PhD on frame annotation, etc. And then we built upon it with question answering, for instance, coreference, conversational question answering, but every time we had some control, some semantic control of for instance, the questions that we ask. We know which frame they are related to, which verb they are related to, and the idea is that we want to do some experiments to understand what is really going on with this semantic control. And the last work that will be published in EMNLP is a methodology to evaluate and to try to find some linguistic intrinsic complexity factors that would make it more difficult for a question answering task, question answering data set. Whatever the model, is it an LLM or a fine-tuned model, whatever, are there some intrinsic difficulties in the data that make the task more difficult? So the first thing that was observed is that the performance of the MRQA systems in fact depended on the semantic frame that the question was related to. So there is something here, so we wanted to push that. So they designed several complexity factors, and the idea is that every time you divide your test set in whether it seems easier with this factor or whether it seems harder, and then you measure the difference in performance between the difficult subset and the easy subset. And there were some complexity factors that were consistently more difficult for each model that was evaluated. So in Marseille, they did some human evaluation at scale. So you can read this work further. But again, this is this idea that we need to properly evaluate. We need to understand what is really difficult or not, what is related to the task, what is related to the data. And this is something we are pushing. So this is the end of the talk. So I think the point is that it's important for us to have a clear evaluation methodologies and to transfer these methodologies also to operational business units. And we think we are going to go further in estimating the complexity, the difficulty of a request, to have some linguistically controlled benchmarks. And also, I think it has been said several times during these 3 days that you also asked the question that we were used to think in terms of tasks, but now we maybe go beyond the notion of task is getting more blur, and maybe to go from task evaluation, maybe to go to something more systematic about skills assessment, like you evaluate skills of children at school rather than putting them a grade. Maybe we could push that further and have a better methodologies. So, thank you.
Thank you, Geraldine, for this talk. So we have time for a few questions before closing the session.
Hello, I loved your talk, and I agree with many of your points. I love that you did the fine-grained assessment of the evaluation of summarization, and also that you integrated costs into the evaluation so directly rather than just as an afterthought. I love that. I guess I was wondering on the summarization side, what do you think about the potential of partially automated methods for evaluation? For example, I think there's some work from Ito Dagan's group on automating the pyramid method and using that to estimate the scores related to, that's from there you can derive scores about like deletion or omission or insertion and so forth. I was wondering what do you think about that type of approach?
Yeah, well, I don't know exactly about this approach, but we are quite struggling to define an automatic way of detecting these spans, because it's like globally the summary is very good and the source is quite big and difficult to analyze, and so there are some alignment issues, etc. But I think we really need to move along on this path. Yes.
Thank you.
Yeah.
Yes, please.
Hi, thank you. So my question is about the regulatory protection. We know then GPDR requires very restricted way to use customers' data. So when you are using like AI for extracting information, is there regulatory bindings, or maybe it's okay as long as you do in your own company?
Sorry?
Like it's about the GPDR and how you adapt with that, like the regulatory guidelines about using AI for telecom data, especially when you have customer information. So is there any specific requirement you need to follow, or like since you are doing it only within Orange, it's fine?
Yeah. Actually, we are using models that are deployed in Europe, and they are specifically for Orange. So we are paying to have this. So we have a guarantee that they don't use our data for improving the model. Hopefully, we hope it's, but it's the deal. And also, it was compulsory for our customers and for us that the models are deployed in Europe, because we can't depend on the what is it called, the First Act in the US. So we don't use any model that is deployed outside of Europe, and preferably in France. So this is only for us. So this
Thank you.
Yeah.
Okay. Yeah. Along this line, I was wondering if you can really trust an LLM querying the AI Act. If there's not some kind of conflict of interest between,
Yeah.
Probably. Okay. So thank you again for your talk.
Thank you.
And so this closes the session, and this closes as well, nearly the workshop. And so it's time to do a very, it won't be too long.
No, it won't be too long. So
wrap up.
I think it's time to acknowledge a lot of people that help us to make this happen. So first of all, I would like to acknowledge all the speakers, especially those that are coming from France and the rest of Canada, that they booked a full week to stay here, but all of them for the great job that they have done. So thank to all of them. I think the talks were amazing. Yeah. I would like to thank to all of you here today, to those that have been with us the last 2 days, to those that were online. I think without you, it's nice to speak, but it's even better if there's people listening to what I say. So thank to all of you for coming as well. Right? That's great. I would like to thank to Mila for hosting us. I think in this such a very nice spaces and environment, it's very important to be comfortable and to share all these interesting discussions that we have here. I would like to thank our sponsors. Ibado, that we have this introduction the first day, the F4Q, the Fonds de Recherche du Québec, they help us to also bring people to Montreal, the CNRS as well, as we said before, and the GDR, which is this regroupement of research that helped to bring a lot of French people to here. Thank to all of them for supporting us as well. I would like to thank all of the students that present such a fantastic poster. We were very, very happy to see how much interaction happens around the posters. I think that's very important to all of us. So thank to all of them again. I would like to thank then to those that help us to make this happen across these different weeks and months. So starting from the fantastic team at Mila. So I would like to thank Joël, Emily for putting in place the website, all this visual material that we have here. I would like to thank Ludovic, that's over there, that was taking care of all the logistics. Nadine as well, and Carl, that is, was taking care of all the visual, the work during this 3 days. So thanks, a big thanks to all of them. I would like to thank all our student volunteers for the great job that they have done. So I would like to thank Philippe, Loic, Céline, Sienna, LG, Ori, David, and Cesar for their help. Thank to all of them. And finally, I would like to thank my colleagues, both that have been working together for this, and the first time that we came to discuss with Jackie. Jackie was not even finishing to listen. We say, that's a great idea. Let's do it. Tell me what should I do. So, thank to Jackie for all this, work that we did together to come up with this fantastic event. I would like to thank Frederick as well. He was the one that basically was, putting all this fantastic scientific program, just making suggestions, trying to accommodate, not only in terms of topics, but also in terms of, timing and different requests. It's not always easy, but at the end was a great job. So thanks to both of them for this help. Yeah.
And we would like to also interject to thank Pablo. He was really the mastermind behind all of this. He pulled all of the strings together. Without him, this would never have happened. So thank you so much, Pablo.
Okay, so as far as I know, there was one bad speaker that suggests to have a follow-up of this workshop in Paris. So Benoit, thank you for the suggestion. We're looking forward for the next edition in Paris, and maybe we do 1 year and 1 year, as we said. That could be interesting. So thank you again to all. Looking forward to see you.